For maybe 5 minutes we can wait.
Yeah, I think we can wait.
Okay.
Let it go to at least 40 plus.
Yeah. So okay.
So it's 9:35. I think we can start. So people will be joining.
Yeah, I think we can start now.
Okay, over to foreign, sir.
So only 33 participants are there.
They will join, sir, eventually.
Okay.
If you want, we can wait for a few minutes more.
I
As you said.
think better to wait for another
Okay.
couple of minutes.
Yeah, so we can wait a few more minutes. Yeah.
So now people have started joining. So
Okay, sir, we will again announce today that they should join at 9:20. Yesterday we told that they should join at 9:20.
Yes, sir. We already are saying that you have to be ahead 10 minutes before. Students are not paying attention. Participants, please try to join by 9:20 so that we can begin the session on time, because otherwise our whole day gets delayed by 5-10 minutes.
Well, let's wait a few minutes more.
okay, sir. Right?
Is the program visible on the screen, today's program?
Yes, it is visible.
Yes, it's visible.
Sunil, can you hear me?
Yes, Foran, I can hear you.
And this there is RBS 1 and RBS 2, and you and Umapathy both are mentioned. So how you will manage?
RBS 1 will be given by me and RBS 2 will be given by Umapathy.
Okay. Okay, thank you.
Sure, thank you.
So I'm approaching my target of 40 plus.
You are within error bars.
Okay, so now I think we can start. Sir, can I start now?
Yes, sir, please go ahead.
Though number didn't increase much, but I think
No,
we
it reached, it reached.
Now
It's
it
40
is
now.
40. Sir.
So it's
Okay,
940 and 40 participants. Good number.
Okay, so good morning, you all, and welcome you all for this third day of our school. And today we had lecture on RBS, followed by some demonstration on SRIM trim, and in the afternoon there would be lecture on the fundamental aspects of particularly low energy interactions. I would say. So thank you all, and let me take this opportunity to introduce my dear friend Sunil Ojha, who joined Nuclear Science Center in 1998, January 1998, as a scientist trainee, and he did his MSc from Mumbai University, and also qualified the NET examination in those days, which were very difficult in those days indeed. And as he grown up in BRC, so he's having more inclination towards becoming a scientist. So he joined Nuclear Science Center in 1998, and he is mainly involved in the accelerator-related activities of IUAC, and mainly the tandem accelerator. And later he also involved in one of this facility of Rutherford backscattering spectrometry, and we all appreciate that he quickly learned all about the RBS, including the channeling, which is very complicated process to perform a good quality experiment and do the analysis of the same. And same has been appreciated by one of the pioneer, Professor Benki Venkateshan from USA, later from Singapore. So I welcome Mr. Sunil Ojha to deliver his lecture. Thank you.
Thank you, Foran, for encouraging introduction. And I am thankful to the organizer for giving me this opportunity to interact with young researchers and telling them or showcasing them the facilities that we have at IUAC. So as Foran said, that we have 2 lectures on RBS. So in the first part of the lecture, what we will be doing is we will be giving an introduction to the instrumentation part of RBS, and it will not be limited to the RBS instrumentation part. It will be instrumentation for ion beam facility in general. So it will be helpful to the young researchers who are coming to IUAC for doing the research and using the accelerator facility for their implantation or irradiation. That means using the ion beams. That is the idea of the first lecture. In second lecture, what we'll be doing is we'll be taking different cases and talking about the RBS in general in D. Okay, with these kind words, I thank once again the organizers and start my lecture. So to begin with, let's thank the Almighty for giving us knowledge, for giving because they are the one who architected the letter, word, and number, and made us capable of reading and writing. Okay, so once again, the idea is of the presentation to discuss the instrumentation required for IBA and ion beam labs in general, and how can Accelerator help research students to accelerate their research program. Okay, so before going forward, let me thank the group members who were involved in setting up and running of this facility: Dr. Sandeep Chopra, Satyanath, Devrani, Umapathy, myself, and there are many other labs like Pelletron labs, vacuum labs, mechanical group labs, who ensures that this facility run unhindered, and the users from different part of the country come and utilize this facility and do their research work. So what happens when I want to study or analyze my target with ion beam? So I shoot ion beam on my sample, on my target, and then various processes can occur. There can be either nuclear reactions, the nuclear products can be formed, or there can be gamma rays, which can be used to analyze the target. Or there can be some atomic excitations and the production of X-rays, which can once again give me information about the target that under analysis. Or what can happen is when I shoot the ion beam, the same ion beam can get backscattered, and if I can measure this backscattered beam or backscattered particles, once again this gives us information about this target or the sample. Similarly, these ions can recoil the atoms of target, and we can do ERDA and get some information. So there are various other techniques which, using the ion beam, I can analyze the target material or the substance what under analysis. So at IUAC right now, what we are mostly concentrating on RBS. We are doing ERDA, and some amount of TIXI we have tried, but in the future course we are trying to set up TIXI and this nuclear reaction part also to increase the scope of the study under what we can perform at IUAC. Many people complain, look here, IBA is not very fashionable, it's not glamorous, and the space mission studies are very glamorous, and we all understand Mangal mission, Chandrayaan, and NASA missions and orbiters and the thing. But all these space missions also use IBA techniques to analyze in situ analysis of the material. Like way back in 1967 as well, one of the space missions, Surveyor 5, had an IBA facility that it had a radioactive substance which were throwing alphas on the moon, and the backscattered gammas or the backscattered alphas were being measured, and the material of surface of the moon were analyzed using it. So IBA space missions are if in situ measurements, it's incomplete without IBA. So IBA is as glamorous, as important as other studies which are more glamorous and come to more into the knowledge of the common man. So going by the history of RBS, how it all started. It all started somewhere around 110 years ago when Rutherford's two students, they conducted this experiment. They were hitting this gold foil with alpha beam, and what they expected, this gold foil will get torn away by the hitting alpha beam, but to their surprise, this gold foil survived, and in fact some of the alphas were backscattered. And by this experiment only, Rutherford conclusion came that look here, things are not uniform. The mass of the atom is basically concentrated on the center and what we call as a nucleus, and other areas are empty. So there's people use this code, famous code, that most of the places are empty. Okay. So in RBS or Rutherford backscattering spectrometry, what we do is we basically measure the number and energy of ions of the beam which gets backscattered after collision. So what we have some energetic beams hitting our samples, and some beam, when coming very close to nuclei of the substance in the sample, gets backscattered. And using a particle detector, we are measuring the number of backscattered and also the energy. So earlier, during Rutherford time, people were using radioactive sources to get this MEV beams. But now more sophisticated instruments like accelerators have come into picture, where we can tune the MEV beams in the steps of KEVs. Very small step, fine tuning can be done, and analysis can be done more systematically, and we can have more better resolution. Okay. So what information that we get from these measurements? The kind of information that we get is, if suppose it's a thin film, we get the thickness of the thin film. We can get information about the composition of the film or the target or whatever it is. And if there is some kind of mixing or some transfer of atoms have taken place between the two junctions, so how does that depth, it changes with the depth. So all these measurements can be done only by RBS, especially the third one. So generally what we do is the beam that we use is alpha particle helium, and energy is around 1 to 3 MeV. And these MEV beams are produced by accelerators, and which will be basically core of the talk in the part 1 of this lecture. I will be talking more about the accelerators and how beams are produced, and giving you more information. What do you expect from accelerators when you come and perform experiment at IUAC? And this backscattered beams are basically measured in a via detector called by nuclear detectors, nuclear particle detectors, mostly solid state surface barrier detectors. So once again, the Rutherford lab were pioneer in conducting or constructing the first accelerator for doing the measurement nuclear experiment. So what they did, they made an instrument which is called a Cockcroft-Walton generator, where they used a sequence of diodes and capacitors, and using that they made got a high voltage of around 600,000 volt, that is 600 kilovolts. And using the 600 kilovolts, the hydrogen was accelerated, and it was hit in a lithium nuclei, and then they produced two alphas. For the first time, a nuclear transmutation was produced by means of entirely under human control. So this was a citation read for Cockcroft and Walton when they got Nobel Prize in 1951. So you can see Walton sir sitting inside the experimental chamber and doing the measurements. So what are accelerators? The accelerators are instruments to accelerate ions or electrons to very high velocity. And when they are moving with a high velocity, energy is associated with it. So as I said, it all started in the Rutherford's lab. So just deviating a bit from this talk, let me tell you something about Rutherford. Rutherford was a very versatile scientist. So he was a physicist. He got his Nobel Prize for chemistry, but he had a lot to give to other fields of physics as well. Like in 1910s and 20s, Rutherford had a lot of work to be done on this this decay chain, from uranium to lead decay chain. All these things were calculated by after Curie. Rutherford took over, and Rutherford did all these measurements. So Lord Kelvin, during that time, he was a very adamant figure. He did some calculation and said, look here, Earth is around 20 million years old. So Rutherford was the first one to challenge this theory by his radioactivity theories, and said, no, look here, Mr. Kelvin, you are wrong. Earth will be at least 0.5 billion years old. And later he once calculated, refined his calculation and said, no, look here, it is 2 billion years old. And now we know it is around 4.5 billion years old. But he was among the new scientists who broke the thought and shackles and of the older generation and ushered in the new physics. So we should all people from various field of physics or science are thankful to Rutherford for various information that he had provided. Okay, coming back to our basic subject, when this electron or singly charged particles, when they are moving with high velocity, as I said, there's a associated energy with it. But here, when we talk of energy, we don't talk in terms of joules. We talk in terms of EVs. So as you all know, that one EV is when one charged particle moves in the potential difference of, say, 1 volt. So E is equal to Q into V. Q is the charge state and V is the voltage. So like if there's a 10 EV, if I'm saying, so that means that energy of that particular particle will be 10 raised to minus 18 joules. And using this kind of number is certainly not a good idea. So it's better to use EVs. And if suppose the voltage is in thousands of volts, so energy we are using not 10 raised to 3 EV, but the terminology that we use is kilo electron volt. If the voltage is in millions of volts and energy is not 10 raised to 6 EV, we use million electrons of volts of ions when energy associated with that ion. So how to generate energetic ion and use for the experiment? The first part is, of course, there are 3 easy steps. First, you create ions at a place called ion source, okay, and accelerate these ions under the influence of very high voltage. So we know E is equal to Q into V, and if it is highly charged state, it is N into Q into V. So, and this voltage should be as stable as possible. And we know why we need a stable voltage. Suppose you need atoms to be buried somewhere, ions to be buried somewhere around 20 micrometer of thickness. So this energy is fluctuating, or the voltage is fluctuating, the energy will fluctuate. And when energy will fluctuate, the range of the ions that is going inside your material will not be same. So you always want this high voltage should be as stable as possible. And one important thing is we should require a high vacuum, which should be of order of 10 raised to minus 8 torque throughout the ion beam path. That is right from ion source to accelerator to the experimental chamber. The vacuum should be of order of 10 raised to minus 8 torque. Okay, so if I just make a block diagram, it looks like something like this. We have a ion source or electron source, whatever it is. And then we have an accelerating section where we accelerate the ions. And these ions are then fed to the experimental chamber when you conduct your experiments. And throughout the path from ion source to experimental chamber, we should have a good vacuum, 10 raised to minus 8 torque of vacuum. And it's always a good idea to get everything controlled from a remote location using some computer control, some interface and other thing. Because if it's a high energy, there will be radiation associated with it. And certainly for big accelerators, it's a not good idea to go here, put on the ion source, then go here, put on the accelerator, set the accelerator, then go to experimental chamber, stand there and conduct the experiment. It's always better to sit somewhere remotely and do all this thing. Okay, so I'll just show you one of the accelerator facilities at IUAC. So this is RBS facility. So you can clearly see we have ion source somewhere here, and then this is the accelerating section, which we call as accelerator. And here, after beam traveling through this path, here at the end we have experimental chamber where we put our samples and use the beam produced by source, accelerated by accelerator, and using this beam we analyze our samples. Now question is, why do we need high vacuum? There are various reasons why do we need high vacuum, but the easiest reason that I can give you is, suppose I produce an ion at ion source. So depending on the length of the accelerator, the path length could be anything between say 10 meters to hundreds of meters. So this charged particle, if the vacuum is poor or the pressure is high, will hit the stray gases and it will lose its charge and it might lose its sense of direction also. So these ion beams will never reach the target. So you see, if the pressure is around atmospheric pressure, the mean free path of an atom or an ion that we are producing is around 10 raised to minus 5 centimeter. And whereas if the pressure is around 10 raised to minus 8 torque, that means I have reduced the pressure and increased the vacuum, the mean free path is around 1 kilometer. So there's a chances that ion beam produced in the ion source will travel 1 kilometer without hitting any other stray beam, say a gas molecule in the vicinity. Okay, so as I said, ion source, accelerator, and experimental chamber. Let's take each of them one by one. So at IUAC, most of the ion sources that we are using with a big accelerator are negative ion sources. Okay, so let me talk about few of them. So this is outline of Sputter ion source. So suppose you want to do some experiment, say with a nickel beam. So what we do is we take nickel powder and then we press it into a capsule, okay, in the powder form, and we apply some negative voltage out here. Okay, and in the vicinity we have cesium vapors. Okay, there's a cesium reservoir which we heat, and the cesium vapors gets evaporated, and it comes into contact with a place called ionizer or filament. So cesium, being a group 1A element, become ionized very easily. It becomes cesium plus. So this cesium plus will get attracted towards this negative capsule, okay, and it hits the by powder. Okay, whatever it's, suppose it is a nickel powder. Okay, and then what happens is, in the process there's a momentum transfer and a few atoms of nickel will come out. And this process of ejecting of particle by hitting it by some foreign particle, in this case it is cesium, this process is called sputtering. Therefore, this kind of sources are called sputter source. Now, since we are using cesium for sputtering, and cesium is an electron donor, the chances of beam that is coming out will have with the negative ions will be more. Okay, if I was not using cesium, I would have been using oxygen. oxygen is an electron capturing atom or ion. So if I were using oxygen, the chances would have been the positive ions would have been coming out more as compared to negative ions. But since we are using cesium, we are getting negative ions more. Okay, and these negative ions are then repelled due to the negative potential of the cathode, and that's how we produce negative ions into the ion source. Now, what we have done or what we have installed at IUAC is something called multi-cathode sputter source. At one go, we can put 40 cathodes. By the way, this is in general for accelerator. This is not to do with RBS. I will channelize this and will come to RBS. Okay, this is for all the ion beam people who will be using ion beam at IUAC. Okay, so I can put 40 different species, and suppose people from different part of country who are coming to do the experiments, they want different material of beam. So I can change from one species to other species without opening up the source, and this reduces the time of changing the species or changing the cathode, as I say. So such kind of source is called source of negative ion by cesium sputtering. And since there are many cathodes, many beams can be possible. So I say it's a multi-cathode source of negative ion by cesium sputtering. So all these things are once again kept in a big deck, which is at some high voltage, and I produce negative ion somewhere inside this tube. All this sputtering process is occurring here, and then this deck is at negative voltage, pushes these ions to the forward direction. Okay, but there are certain beams that can't be in a solid form. For that, we have only in the gaseous form, in gaseous form, say helium or argon or xenon. So for that, we have to have a gas source. So we can have the plasma source. So in plasma source, what we can do is we have a glass tube where we can feed these gases. Okay, and then we can generate plasma by applying RF. And then there is a helium plus. Suppose if we have using helium ions and a helium plus and electrons. Then applying some high voltage, I can extract the helium ions, helium plus ions outside this glass tube. Okay, and then we make this positive helium to go through a small section where we have gas of group 1A element like rubidium, cesium, sodium, or potassium. They are in gaseous form, and this section is called charge exchange cell. And in charge exchange cell, I said that it contains a vapor of group 1 element, and mostly it is rubidium. And this positive helium, which comes out from the plasma, okay, it picks up electrons from this rubidium vapor, and then it converts into helium minus, and it can then fed to the accelerator. So these kind of sources are called RF, charge exchange ion source. Via RF, we produce ions, and via charge exchange, what we do is we produce these positive ions into negative ions. So it's called RF charge exchange ion source. So mostly beams like hydrogen, helium, oxygen, nitrogen, argon, such kind of beams can be produced using such kind of facilities, such kind of ion sources. So this is some picture of RF charge exchange ion source. You can see a glass tube out here, inside which the plasma is formed. There are RF bands out here. These are RF bands, and beam moves from here to this side. This is a beam direction, and here we have charge exchange cell, where the positive helium or positive beam is converted into negative, and then it is fed to the accelerator, which is somewhere out here. Okay, so this is how the plasma looks when the source is operational. Okay, so this is what I showed you is the quartz tube, which is outside during maintenance, and this is how it will look when it is in operation. Okay, so what kind of beams are generally demanded by users, or which are given to the users from the accelerator or the ion source that is at IUAC? So here are the list. Basically, all the ions which can be converted into negative ions can be produced using this source and can be accelerated with the accelerator and can be given to the user. So these is the some list of few ions which are delivered to the user. So as I said, they should have property of becoming negatively charged, but some atoms, they don't become negatively charged, like beryllium, nitrogen, magnesium, calcium, titanium. So what we do is we don't give ionic beam, we generate an ion source as a molecular beam. Like for titanium, we use titanium hydride. For beryllium, we use beryllium oxide, and so on and so forth. And using charge exchange ion source, we can produce alphas and, if required, oxygen, nitrogen, also argon, krypton, and so on and so forth. Okay, so such setups, like, such as ion source on some high voltage platform of 10 to 100 kilovolt, are also potential accelerators, and they can be used for, say, implanters or atomic physics and such kind of experiments. Okay, and energy, as I said, E is equal to Q into V, where the Q is a charge of ions that are being produced in the ion source, and V is the voltage that we have kept at the, in the ion source. So IUAC has many such facilities which you people can use and do your experiments, where the energies are in keV ranges. Like for example, we have, I don't know, I'm right or wrong, calling it a low energy keV ion accelerator facility, because it also gives MEV beams. So one of the facilities that we have is ECR ion source based positive ion beam facility, and it provides low energy, highly charged ions of wide range of energies. Energies can be from tens of keVs to few MeVs. So it's a highly utilized facility by users, and the young researchers who are planning to do some experiments can take the use of this facility, make use of this facility for their work. Okay, and we can get ions, say oxygen, argon, and xenon of such kind of charge states. And the ion currents can be from 100 nanoamperes to tens of microampere. Once again, it depends on what kind of charge state we are extracting from ion source. The high voltage on the ion source is around 200 kilovolt, and the beam energies that are produced depends on, as I said, on the high voltage on the charge state. E is equal to Q into V. So it is range from tens of keV to few MeVs. So similarly, if you don't like positive charge, positive ion beam facility for implantation, so we have negative ion beam implantation facility also for you. Here also what we have a deck with 200 kilovolts, and we have a same source as I explained, MC SNICS ion source, and maximum energy is around 200 keV, because negative ions are always singly negative charge. So the maximum energy is 1 into 200, that is 200 keV. And currents are once again into range of hundreds of nanoampere to tens of microampere. And the best part is easy to change the beam species. As I said, we can load many different species, and we can change from one species to different species. And we can perform implantation of insulators, ceramics, single crystals, and so on and so forth. There is one more small facility, that is a small accelerating system based on penning ion generator ion source. Okay, this is totally built in-house and can be assembled into very small section. Okay, so once again, I emphasize it is totally in-house production. And this is some old slide that I'm showing you. It can provide energy of a beam of hydrogen, 2 hydrogen, helium, nitrogen, oxygen, neon of energies of different ranges, and these are the currents. So if you want more information about such systems, you can go to our website iuac.trust.in, and that we have different accelerator parts, and for this we have the section is tabletop and accelerator. You can get more information about it. So just to tell you, all these 3 or 4 facilities that I have described till now are heavily utilized by the young researchers, and researchers who are being listening to this talk can plan their experiments using these facilities for their future work. Okay, now this is for the low energy, and now coming to the high energy. So the beam produced by ion source are now to be accelerated using some accelerator. Okay, so the kind of accelerator that we are using is electrostatic accelerator, which is a DC accelerator. Okay, accelerator can be of two types: DC accelerator and AC accelerator. DC accelerator is a an easy thing, so I will be dealing with it. And AC accelerators requires a lot of more dedicated workshops and more classrooms. So let's concentrate on DC accelerators. So the energies spread of the beam coming out of these accelerators are very small. So that's why becoming very heartthrob of researchers. It's few keVs, MeVs. Wide range of currents can be given from nanoamperes to few microamperes, and it's capable of accelerating all the elements. But in our case, the elements which can be form negative ions. So this is how the accelerator that we have looks like. So we have a small shell, and in this small shell we generate very high voltage by Van de Graaff principle. Or this high voltage can also be produced by the Cockcroft-Walton voltage multiplier, but mostly at IUAC we are generating this high voltage by Van de Graaff principle in this small shell, okay, what we call as terminal shell. And then there's one more cylinder which is covering this small cylinder, and which is basically stainless steel made, and in between this cylinder and this cylinder we have gas with high pressure. Okay, and this gas with high pressure, this gas is an insulating gas, and it ensures that the voltage that we are producing, this voltage, mind you, is in millions of volts, remains stable. It does not discharge. There should not be any spark between the cylinder, this cylinder and this cylinder. So it acts as a dielectric between the two cylinders. So it is like cylinder in cylinder, the famous Griffith's problem, and this gas acts as a dielectric. So once again, going into history of making such kind of accelerators. So in 1940s, when they started making this high voltage in open air. So they could never go above, say, 1 million volt or something like that. So what they did, they put it into a big cylinder and they evacuated the cylinder. So when this area became vacuum, so to their surprise, what they observed, earlier in open air it was going to 1 million volt. Now it is not even going to 300 or 400 kilovolts. So they understood that they are making a mistake, and then to increase the dielectric, what they did is they pressurized it with the insulating gas, and now they could get more voltage onto this cylinder because the high gases at high pressure has more dielectric as compared to the vacuum of 10 raised to minus 2 or 10 raised to minus 3 torque, which was achieved during that time. Okay, so at the geometrical center of this cylinder, there is a tube going through it, and inside this tube we have vacuum, and through which the ions goes. Okay, ion passes through. So we have a vacuum inside here, and we have gas at high pressure outside it. So negative ions formed by the ion source somewhere here are pushed into it. Okay, negative ions are attracted towards this high voltage. Here we play some trick. We convert this negative ion into positive ions. Now the positive ions get repelled by this high voltage, and then they are fed to the experimental areas. Okay, to the target. Okay, so this configuration can either be horizontal or that can be vertical. So at IUAC we have both kind of machine. We have accelerator which is horizontal. Okay, they are low energy machines. So the voltage that can go up in the terminal is around 1.5 to 1.7 million volt. And then we have a vertical machine where the voltage on this inside shell, inside cylinder can go up to 15 million volts. Okay, so this is sort of a rough sketch of the accelerator that we have at IUAC. Okay, so what can be done is, I have a high voltage, I can put a source inside it, and then I can generate positive ions, and these positive ions can be repelled and we can perform experiment. Or what can I do is, I can keep a negative ion source outside this high voltage area, okay, and this negative ions get attracted towards the positive voltage. Here, as I said, I do a trick, I convert negative to positive, and this positive ions are once again repelled, and we can do experiment. So both this configuration are possible, but usually people prefer this kind of configuration. And why people prefer this kind of configuration is, I'll tell you. You see, if I go back to my okay, if ion source were inside this accelerator, if I have to do any service of ion source or change of species, I have to open this accelerator and do the servicing. So it's always preferred to have ion source outside. This facility is around 10 years old, and in the 10 years old, this accelerator has been opened only once, whereas twice a year I have to open the ion source. So if the ion source was inside this accelerator, you see I had to open this accelerator at least twice a year, which is certainly not a right thing. And on top of it, what is the best part is, I can get provision for adding more ion source. Here I have a limited space, but if the ion source outside, I can put more ion source by putting a magnet somewhere out here. So ion source in our kind of facility, mostly we have ion source which are outside, and it has its own benefits. The best part is we have a flexibility to upgrade, and for the same beam energy we require low voltage. Okay, that is the best part why we should have ion source outside. So now moving towards the accelerator section. So from ion source we produce negative ions, and using a magnet I bend this negative ion by 90 degrees. And in the process, what I am doing, I am selecting the particular ion. Suppose I want to do experiments with, say, 58 nickel. So when I'm sputtering 58 nickel, not only 58 nickel, but other isotopes of nickel and other molecules which have like water molecule, oxygen, which are inside this will come out. So I don't want all those things to get accelerated and go to the experimental chamber. So this magnet filters out all different masses. So I can set a magnetic field so that it can select only a particular mass. So these negative ions are then attracted towards the high voltage, okay? And when it moves from ion source to the positive high voltage, it gains energy. E is equal to Q into V. But as I said, negative charges are always -1, not more than that. So the energy that we get are in MeVs. Okay, it's millions of electron volt, because the potential is in millions of volt. It can be 12 million volt, 10 million volt, 15 million volt. Okay, and what kind of potentials that have to be kept, that I will come in next few slides. So this negative ions, when it reaches here at high voltage area, so what we do is we remove the extra electrons which are attached to negative ions, and few more electrons are removed and convert into positive ions, and this positive ions can be of highly positive charge. Okay, and then there will be a repulsion, and energy that it gains when ion moves from here to here is Q into V, where Q is of higher charge state. So total energy ET is equal to E1 plus E2, where E1 is 1 into V and E2 is Q into V. The total energy is Q plus 1 into V. So before moving forward, let me tell you briefly about the stripping process. So what happens, what trick that we do is, when these ions are coming, it either passes through an area which has some gas, okay, where the vacuum is poor, or there is a thin foil of carbon. Okay, so when ion passes through it, there will be a lot of interaction between the ions and atoms and molecules out here. Okay, and because of it, the incoming ions will lose the electrons, and when it goes through it, there will be these ions will have more of a positive charge. But all the atoms will not be stripped to one particular charge. Say if I am passing a nickel at 12 million electron volt, 12 million electron volt through say a gas jet, I will get a distribution of charge state something like this. And if I want to going through the gas carbon foil, I will get a distribution of charge state something like this. So you see, with gas I get a lesser charge state, with foil I get a higher charge state. So lesser charge state means lesser energy, higher charge state it means high energy. So depending on the energy requirement of the user, I choose what charge state, what stripper medium I have to use. So if they need lower energy, I use gas stripper. If they need higher energy, I use higher charge state and I go for a foil stripper. Okay, so after so all this beam then gets accelerated, and a particular charge state is then chosen using this magnet, which I call as analyzer magnet. And the beam out here is highly monochromatic beam, which is characterized by mass m, charge state q, and energy E. And then there's a third magnet. Using this magnet, I can put the beam into one of the beam lines and do my measurements. We have dedicated facilities for, say, nuclear physics, for material science, for GDA, for GPSC, and all such kind of stuff. Just to give you a few examples, suppose you want to do experiment with a bigger machine, that is a 15 UD pelletron accelerator. Okay, and if you want, say, 87 MeV of 16 oxygen, what I will do is I will choose 6+ charge state of oxygen, and the voltage will be as can be calculated. Suppose energy is 87 MV. Okay, what I can do is I can do Q plus 1, 7 into 7 divided by 87.5. The potential will be 12.5 million volts. Similarly, at 12.5 million volt, if I am accelerating silver ions with charge state of, say, 9+, energy will be 9 plus 1 into 10, 9 plus 1, that is 10, 10 into 12.5, and energy will be around 125 MeV of beams can be delivered to the user. So just to give you some numbers, so if I say 1 nanoampere of beam current, that means there are around 6.25 into 10 raised to 9 charge particles that is hitting your sample per second. If an operator like me tells you that I am giving you 25 nanoampere of current of, say, 10+ charge state of, say, anything, say nickel. Okay, so that means what I'm delivering you actually is 25 by 10, 10 is the charge state of the beam, is 2.5 PNA of current, which means it is around 1.56 into 10 raised to 10 particles per second is falling onto your sample. I hope my calculations are right. I don't know. Okay, this can be checked. Okay, and if the fluence which is around 10 raised to 14 per centimeter square, the time taken for irradiation is around 10 raised to 14 divided by the number which is calculated out here, which is around 640 seconds, which is around 1 hour 45 minutes approximately. That time is required for if you want this kind of beam, this much fluence of beam, and the current that I'm giving you is around 25 nanoamperes of 10+ charge state. Okay, so once again, just showing you some numbers. If I'm delivering you, say, oxygen of 70 MeV, it will, in the silicon, it will have range of 58 microns. If I'm delivering you nickel of 150 MeV, then the range on your silicon is 27 micrometer. All these are calculated by SRIM. Okay. Similarly, for gold and silver, for energy is 200 MeVs. The range on your silicon is around 24 and 21 micrometer. So when you're planning your experiments, this is a typical energies which are delivered by our accelerator. Not this helium. Helium is for analysis. So these are the kind of range that we are giving beam that can be achieved using the beam of our accelerator. That is 15 UD pelletron accelerator. Now, very quickly, how do we generate this high voltage? We generate this high voltage by Van de Graaff principle. There's a chain on which we induce high voltage, and this the positive charge. And this positive charge is carried to the shell where we this high voltage are dumped, and that's how it becomes highly high voltage. Okay. Okay, now coming to our main thing, that is RBS facility. So this is the one of the facility, RBS accelerator based facility at IUAC. Once again, we have ion source, accelerator, and here we have our experimental chamber. Okay, just to show you the inside of this accelerator, what we did is we opened this accelerator. Okay, and you see this accelerator right now is into the beam line. Okay, we pulled it out, we opened it, and we pulled it out. Okay, and we took out the accelerating section. So this is say the terminal, high voltage terminal, where we can achieve high voltage. This can go up to 1.7 million volt. Okay, and through this pipe there is a tube through which the beam goes through, and this is the chain, the charging chain, which rotates, onto a pulley. This pulley rotates with a high RPM, and these pellets carry the charge, and the charge is dumped out here, and we can generate 1.7 million volt at this point. Okay, and the experimental end station, you can load your samples on the sample holder. This is how the sample holder look like. At one go, you can load somewhere around, say, 16, 17 samples. If the sample size is, say, less than 1 centimeter by 1 centimeter. And we have a 4-axis goniometer. This goniometer, we can change the position of sample and moving from one sample to one sample, or if you want to do channeling, as Foran said, we do a lot of channeling work. And in the facility, we have 2 detectors. One is fixed, which is a backscattering detector, which is used to do ERDA. And then is one more detector, which is a movable detector, and we can know what angle we have moved. So it can be used for RBS at lower angles, or it can be also moved forward in this direction, and we can do ERDA of hydrogen in our case, because we are using only helium beam. So the recoils can only be a hydrogen. So we can do ERDA using this detector and detect hydrogen into this detector. This is how the inside portion of the chamber looks like, or the experimental chamber looks like. The beam comes to this small collimator. Okay, the helium beam from the accelerator, it's come to this beam line. The sample holder out here, the samples are out here somewhere. Okay, and this is a fixed detector which is around at 166 degree backscattering. This is a second detector which is movable from 110 degree to forward degree. It can go up to 10 degrees in the forward mode, 20 degree in the forward mode. Okay, so if I keep it somewhere here, I can do RBS. If I move it like this, I can do ERDA by tilting the goniometer. Okay, so if the beam comes, hit the sample, some of the beam, and what things happen when the beam hits the sample is a part of the second talk, which will be soon starting. Okay, the beam hits the sample, and some of the beam which goes very close to the nuclei of the
excuse me, you have another 10 minutes.
Yeah, I will be finishing in 5 minutes. Okay. And some of the beams, the helium goes very close to the nuclei of the sample and gets backscattered. This backscattered are measured in the detector, the energy and the counts, and then using a data acquisition system, which consists of an amplifier, MCA, and ADCs and MCA, we can get the basically the counts of the particles which are coming into detector. So they are in form of, say, yield versus channel number. The channel number is nothing but energy, and yield is the number of particles hitting by the sample, hitting the detector after getting backscattered from the sample. Okay. So this is a typical spectra of RBS that we get. So spectra of RBS of a thin film of AU on silicon. Once again, it will be discussed in detail in our second talk. And since, as you see, just to show it, tell you very briefly, that we have a thin film of AU. This you can easily make out that if something thin, there's a thin peak, so this must be AU and higher energies. With higher energies, because it is associated with higher Z. So more the Z, more the backscattering energy. So we have this particular peak represents gold, and this particular continuum represents the silicon substrate. Okay, so this is how the spectra looks like, but the spectra will make more sense in the second part. So thankfully, there are good people around the world who are working a lot more in IBA as we do, and they have come up with more of simulation program that has made the analysis very easy. The simulation programs that we use is mostly SRIM and Seminare. There are at least 3-4 more that we know, Data Furnace and others. Okay, and in this, what generally we do is some parameters are fed, like incident energy that we know, detector solid angle that we know, and resolution of detector also we know that are fed, and the parameters like thickness of the sample, the target compositions, and all are varied, and then we get a simulated peak, and a good fit of simulated peak in experimental spectrum will provide us a necessary information about the samples. Okay, so just to summarize about the facility, okay, we have RBS facility in IUAC, which is accelerator-based facility. So I was speaking more of the accelerator part, more of the experimental chamber and experiments that can be conducted with it will be dealt in second chapter. It was installed and operational since 2010, and in our facility we have done more than 15,000 measurements, and the faculties from 100 different institutes, colleges, and universities have used our facilities to do their measurements. We do all these measurements using helium or alphas. Energy range from 2 to 3.5 MeV. Beam that we deliver is the thin beam, that is, we don't scan it, and it's around 2 millimeter is the beam spot size. So all your sample should be bigger than this. It should be around 5 m, at least 5 mm by 5 mm. Okay, and beam currents can vary from 5 nanoampere to 15 nanoamperes. Analysis time once again depends on sample to sample. It's 5 to 13 minutes per sample. And as I said, the backscattering angle is fixed, that is 166 degrees. Detectors that we use is SSBD around 20 kV resolution for the beam that is getting the particles that are getting backscattered from the surface of the sample. And the best part of this technique is, to a large extent, it is a non-destructive technique. That is, it doesn't damage your sample if I keep the analysis time and the charge, the number of particles hitting the sample. Yes. Okay, with this, I rest my case, and I hope it had been beneficial to the young researchers who would be using the ion beam facility at IUAC. And thank you.
Thank you, Sunil.
Thank you, sir.
Okay, so now the session is open for the discussion, or particularly some questions from the students.
Sir, 2 people have requested the same time versus fluence calculation in the chat box.
Okay, so my slides are visible?
Yeah, yes.
Okay, my mathematics can be wrong, but the numbers is correct. So as if I say that I'm delivering you 1 nanoampere of beam, so with 1 nanoampere of beam, I can do a simple calculation of singly charged state, that the number of particles associated with it is 6.25 to 10⁹ charged particles per second. So suppose you are doing an experiment, and I say it is around 25 nanoampere of 10 plus charge state. So this is for single charge state. So but here 25 nanoamperes what we are measuring, but the charge state of the beam can vary. Okay, so suppose you are doing measurement with a 10 plus charge state. So the actual number of particles that you are getting is not 25, not corresponding to 25 nanoamperes, it is corresponding to 2.5 nanoamperes. This 2.5 nanoamperes you have to multiply with this 6.25. Okay, I think I made a mistake in the units out here. So this 2.5 has to be multiplied into this 6.25. So this many particles per second is falling onto your sample. And if you're scanning it for area of 1 centimeter square by 1 centimeter square. Okay. So, and if suppose you are using the fluence of, you want a fluence of say, you want a total number of particles hitting the sample should be 10 raised to 14 particles per centimeter square. So what you have to do is you have to divide this by the numbers which, once again, I'm doubtful about this number. The number that you get by this calculation, this into 2.5, and 1 into 10 raised to 14 divided by, suppose this number is correct, 1.5 into 10 raised to 10, it comes around 6,400 seconds, which is around 1 hour, 45 minutes. For the total number of 10 raised to 14 particles hitting a sample per centimeter square. So this is kind of calculations that are performed.
Okay, thank you.
Okay, is it
Anybody
clear?
else? Yeah, I think it's. Taranga, is it okay?
Yes, sir.
Okay, thank you. Anybody else?
Okay, this is a very nice question. Okay, how can we confirm? What we do is, what we can do is, we can take before starting your experiment. All these experimentalists, what they do is they put a quartz, and on the quartz, what they do, they mark a square of 1 centimeter by 1 centimeter. And the accelerator guy like me, what we'll do, we'll focus the beam at the center of that particular square. Okay, very fine spot. And then using an optical element called scanner, I can move the beam in X direction and Y direction. And by controlling the voltage or current of the power supply, I can move that spot only in 1 centimeter in X direction and 1 centimeter in Y direction. And if the experimentalist and the accelerator guy are sure that now it is only in 1 centimeter by 1 centimeter square, then only they will bring their sample onto the beam path. So that's how we confirm that the beam scanner is 1 centimeter square.
Sanjay, maybe I can add little more to it. Whenever we are using this scanner, still there is a issue of the uniformity, because around the edges always we have a more fluence as compared to the you can say the major part of your sample. So anyway, that issue still remains. Thank you.
Sure, sir. Yeah.
Anybody else? Sir,
suitable, but once again, if the sample as small as 0.5 mm cross 5 mm can also be done. Okay, but the smaller than that is difficult.
is it okay? Okay, thank you. Anybody else? If not, let's thanks Mr. Sunil for such a wonderful lecture.
Thank you. Thank you, Param, and thank you all of you.
Maybe I can request Umapathy to continue, or we will take a little break, maybe 5 minutes. Indra, what is the idea? We need to take little break.
Sir, we have a break after Umapathy's
okay.
lecture,
So then
let him continue.
So okay, Umapathy.
Yes, sir.
So maybe I need to introduce Umapathy as well.
Please, sir, do the honors.
So Umapathy is the scientist again in the accelerator group, and is involved in many activities indeed, right from the RBS channeling and sometime in FESCM and other accelerator related activities as well. And recently maybe some activity to the negative ion implantation facility as well. And he is a very slow speaker, but he understands things quite nicely, and hope you will learn a lot from him. Okay, Umapathy.
Yes, sir.
So you are presenting something? Where are your slides?
Yes, sir. not able to share. No?
Umapathy, you are speaking or you are muted?
No, sir. I'm speaking, but I'm not able to share this.
Okay, okay. But try to speak a bit loudly, huh?
Umapathy, there is this arrow present now. Okay, you have to press this.
But yeah, present, but it is not taking.
Your
It's not
screen may be
taking?
minimized. You can see in the bottom.
You ask current permission in order to share your screen. Yes, some.
Some people have some message. Let me see. Umapathy, from where you are attending? You need some logistic support, then maybe we can send someone. Okay.
Something is coming up. You are presenting your screen.
You may be minimized in the bottom of your screen, so maybe you just click on that.
So maybe he can log out and log in again.
Ramcharan, try to help him out.
Where is he now?
I think I suppose in an engineering building, somebody told me. Rajbir is there, you can ask Rajbir to help him. I think he's around.
Rajveer is nearby, sir.
Umapathy is out.
Umapathy,
Meantime-
you have to first do the full screen of your presentation. Okay,
Now you
just
now
go to the slideshow in your presentation first, and then from here present now. Then select a window of your full screen.
first
Okay.
unmute yourself. Umapathy. Okay, yeah, something is coming. Yeah, click on your presentation. I suppose this is in the bottom. It may be minimized somewhere. Your PPT or PDF, whatever it is. Yeah, check in the bottom somewhere.
इसके भी नीचे देखो, जहाँ रिबन्स होते हैं ना, जब मिनिमाइज करके जाता है फाइल्स.
Sunil, are you there? हाँ ग्राउंड फ्लोर पर है कोई बात नहीं है Sunil? I think it came out. Yeah, somebody is there. Okay. Okay. But you know his room? अच्छा, okay. Then please help.
Okay, don't worry. We are sending someone. Okay, don't worry. So instead of maybe full screen, you just share some window. Select a window. Present now. Select a window, and then that presentation window you can select.
Umapathy, try to unmute so we can listen you also.
You are trying to say something, then unmute.
Sir, can I give it from my lab? I think it is not here. It is not.
As you wish, matlab, that is up to you.
Okay, sir. I will give from lab itself.
Either
that PC don't have camera.
Okay, just a moment. Saif sir may be reaching you in 2 minutes. So आप थोड़ी देर रुको. Then you decide. Okay.
Okay.
Participants, sorry for inconvenience. Shortly, I mean, everything would be okay.
हेलो सर यहाँ पे कुछ error आ रही है हाँ ठीक है इसको ले लीजिए नहीं कोई ओके ये
Yeah, it's coming up.
Yeah. Thank you.
Okay, all the best, Umapathy. I hope now there will be no problem.
Okay, thank you, Saif sir.
सैफ के आते ही गायब हो गया क्या?
Where is your slide?
अरे यार, maybe computer may be creating some issue.
Okay. Oh.
Meantime, you can keep speaking something.
Yes. Oh, stuck.
अरे Saif is a joint partner also. Umapathy, what happened? Your computer is hanged or what?
Yes, it's got hanged.
So what we can do is, see Umapathy, you gave from this mode only. Don't go to the full screen.
Full screen, okay.
So
Okay, just give from here. Go to the next slide like this.
Okay.
There is some issue in the full presentation or what?
I think the PC may be slow, so it's okay. This slide is visible enough. You have given a bigger font to the text, so start from here.
Okay.
If you can manage, it's
So,
fine.
yeah. So I am continuing the talk RBS 2. So from accelerator towards to the main measurements. So in my talk, I will cover a short history of RBS and other IBA techniques, RBS, Rutherford backscattering spectrometry, and non-Rutherford backscattering, that is resonance RBS, and few slides of channeling, and ERDA, few part of ERDA, then few references. So yeah, okay. So we can take the brief history, that is in 1911, structure of an atom. Hello.
Slide is not very clear, so maybe.
Sir, is it clear now?
Your slide is visible, but unable to read by participants.
So you can participants can pin that, so it will become bigger.
Yeah, now
Yeah,
okay,
it has
now
come. It has
okay.
come. Okay.
Okay. So taking to the brief history, so 1911, it's a Rutherford atomic structure model. So he proposed an atomic model, and that was it. Was a nucleus is in the center and electrons are revolving around it. So you can see the picture below. So that is Gregerson and Madison experiment. There is a gold foil and it is a fluorescent screen detecting at a different angle, and alpha source was used. And for that, he concluded that so nucleus is in the center, so where most of the alpha particles scattered back and partially they pass through. Sorry, the most of the alpha particles pass through the center and few detected in the backscattering angle. So 1957, so Rubin explained that this can also be utilized for analyzing the materials to the near surface, and this was also in the space mission Surveyor 4, where accelerator was not used and alpha source was used. So falling back again to the RBS, so this is one of the method in ion beam analysis techniques. So altogether, IBA stands for ion beam analysis. So this can be many things, including RBS and ERDA, or your PIXI, or your nuclear reactions, or your PIG. So the figure, that second that you see here, so you can have, so get this RBS, ERDA, PIXI, or PG, or NRA. So what we need is one accelerator which can accelerate beam, say around 500 keV to 5 MeV. So typical particle that we need, either it is helium or proton or any other ions, maybe heavier also accepted, like nitrogen and carbon. So here there are many phenomena included. So this is some sort of typical setup that we see in the previous talk. So this is we can consider this as a chamber, vacuum chamber. So you keep your target here and then you fix your detectors. What type of detector you want? You want to detect alpha particles, you want to detect your helium or hydrogen, you want to detect your gamma, or you want to detect your fission particles. So after your nuclear reaction, that is NRA. So basically I stick to this RBS and few part, and in my last slides I will be going for ERDA, that is hydrogen detection and depth profile using in the same setup. So we can go to the next slide. So what is Rutherford backscattering spectrometry? So Rutherford backscattering spectrometry is widely used nuclear method for near surface layer of the solids. So what is in this one? What is this one is a target is bombarded with the ion of typically energy say 500 keV to 500 MeV. So in our setup, so 500 keV is not possible if it is very less. Above 1 MeV we consider, and we can go up to 4 MeV. So once you have a projectile, either it is proton or helium, you project it and you accelerate and you hit it to your target. Then you detect backscattered helium with a suitable detector. That is your solid, either it is solid state detector or advanced detectors. So this will give you your information regarding your composition or material information or your depth profile of individual element. So the below figure you see is some setup. So this figure you can often find in internet. So this is a detector. This is a focused beam, helium beam, that or it may be proton also. This is goniometer. So where you can move this either X, Y, theta or phi, and you can detect your material. Okay. So this covers the basics, and few mathematical concept or physics concept which governs the complete RBS is kinematic factor, second is scattering cross section, third is energy loss, and fourth one is struggling. So somehow we can give less importance to struggling to the thin films in Rutherford backscattering, but we need to consider it again in ERDA, so where it is recoiled. So each of these factors, if you can recognize these three, this give you information with your RBS measurements. So kinematic factor will give you mass determination. It can identify what element it is coming from, and scattering cross section will give you qualitative information of atomic composition or your film composition. Energy loss will give you perception of depth, that is your thickness. So all concepts give, these concepts allow RBS analysis to give qualitative depth distribution of targets with different masses. Okay, going back to the next slide. So that is kinematic factor. First, which I selected is kinematic factor. So this is your collision kinematics that you are may be familiar with this. Okay, you can see in a laboratory setup. So here M1 and E1. E1 is a known energy. That means which energy you are just projecting it. M1 is the mass. So if we consider our system, it is helium. M1 can be helium. So once it hit a target, it may be gold or silver or thulium. Then it will lose some of its energy and it will move out as with energy E1. The ratio to E1 to E0, that is your emerging projectile to the incident projectile energy, gives you kinematic factor. And this is unique for each element. So such example, I have taken one spectra of thulium here. So I just identify half of the bit, that is at FWF position. So identify this energy is 1.822, that channel number 17648. Now I know this E0 is 2 MeV. So I know this E1, then you can calculate this K, then you can get this value. So this is well calculated. Now you can identify any surface mass by using this value. So next slide is mass resolution. Yeah, here we are using two different mass. One is helium and another one is thulium. So we may be having different mass in different elements. How good it can resolve two masses in a particular energy, that is mass resolution. The relationship between energy separation of any projectile energy and mass difference of target element is given by this equation delta M2, that is differential term of delta E divided by E0. Okay, so this is some of mathematical expression, so which is maybe difficult to understand. We come to the graph. So you can see that this is M2, that's it, target M2, and this is K. K is kinematic factor. So you can see three lines, gray, red, and green. So red is for helium, and gray is for hydrogen. So lower the projectile, you will have better resolution and better mass resolution in lower Z mass. That is M2 when M2 is less than 20. Suppose you go for higher lithium beam or carbon beam or oxygen beam. So your mass resolution goes better with higher region, but you cannot detect masses of lower. Suppose you are using lithium as a beam itself, you will not be able to detect your helium or your hydrogen. So what we can conclude is it decreases with the increasing term of E0, that is incident energy. And if M2 is greater than M1, so if you have a higher projectile mass like lithium, you will not be able to detect lower masses like hydrogen and helium. So delta K is much better for lighter target, so better mass resolution. So RBS is always best, and it goes with lower projectile, either helium or either hydrogen or with helium. So light elements may overlap in thick layers of substrate for heavier elements. This we can discuss in the energy loss section also, or in the composition. So coming to the practical reality situation, how good you can resolve two masses. So here I have taken one spectra of having different elements of gold, mercury, chromium, iron, and carbon and oxygen. So I have selected in different region higher energy, that is Z is high, and medium, and then small. So gold and mercury, you will not be able to differentiate. It looks like a single peak. And chromium, iron, yes, you are able to differentiate. And in case of carbon and oxygen, yes, you can clearly differentiate. Yeah, chromium and iron, when you expanded the graph, you can see. But gold and mercury, you will not be able to see. Lighter elements, yes, with helium beam, you can resolve it better. For heavier elements, you will not be able to resolve it better. So second thing that we can consider is Rutherford cross section. So this is the same equation that was given derived in 1911 by Rutherford itself. So this is basically probability of scattering collision between projectile and a target, and it gives a probability of how frequently your collision is occurring and how much amount of backscattering yield that you are getting. This is a differential cross scattering. So you can see the equation Z1 Z2 by 4e into 4 divided by sine to the power of. So you can see this Z1 Z2 E and theta. So this Rutherford cross section again is a theta dependent. We should be very careful because each of these theta, when you go to non-Rutherford cross section, this is very important, because suppose you may be Rutherford cross section at certain angle, it may not be Rutherford cross section at a different angle. So if in our system, if we fix many of the things, say that we are fixing detector at certain degree of 166 degree, and energy, say we are fixing at 2 MeV, and Z1 is our helium mass, that is 4. The only variable that is left is Z2, that is your target mass. So that is directly proportional to this is your target mass. That yield is always separate. The cross section yield is always proportional to your masses. Higher the mass, higher the yield you will have. So this you can see here. So oxygen, fluorine, silicon, sulfur, calcium, iron, and niobium, tantalum, and gold, bismuth, they go on increasing. So I've taken one more example here. So this is one random simulation that I have taken. So I have fed so many elements, say 8 elements of equal ratio in a film of, but the height of each element is different. Height of matrix height is so different, and silicon height is different. So why? Because it is directly proportional. Your cross section is directly proportional to Z2, that is square of your mass. That is, suppose we consider oxygen, this is somewhere around channel number 7. When you subtract silicon, you will look like this. And when you see a gold, so you have Z is gold heavier than, and you will have more backscattering. If you have more backscattering for gold, and you have less backscattering for oxygen. So why this is, oxygen is almost very much oxygen or carbon is very much compared with your helium nucleus, so it will partially transmit much of its energy to the target nucleus and less will be backscattered. Okay, so going to the next, the third concept, it is energy loss. This is bit important here. So to how you can estimate your thickness is basically from your energy loss. The energy difference delta E of a particle before and after transmission through the target is measured in terms of your energy loss, that is dE by dx. I think you have one lecture on your energy loss. I am not taking the equation itself. So I will consider, so you can see this slide. So you have E naught in the surface, and when it comes out, it is E1. Why? Because it will travel with certain energy loss in this path at a certain thickness T, and then you will have a collision or your head-on collision. Then it is backscattered, and it will again lose energy while coming out from the surface. So many times you will be confusing why there are two energy losses. It is towards inside and when it is coming back. So now you can see this equation. This is delta this delta E in, that is energy loss in the inward path, and you can see out, that is delta E, that is energy loss in your outward path. So the theta that comes in the picture is this, is but more than this one, you can have to consider theta, that is cos theta term. So if I consider E1 as emergent energy, that is, this term will give you what is the energy that is coming out. So E naught is incident energy, E in energy lost in, and this is kind of loss in the kinematic factor, this is energy loss in the coming out. So simply we can consider delta T into S. S still we can define as kinematic factor into energy loss in plus cost term into energy loss out. So suppose we estimate this, then it is easy that we can get this delta T. So thickness we can easily determine the difference between your energy and your your energy loss. Energy loss, sometimes you can do it directly from SRIM, or your programming you have already backed with your energy loss factors. So I have taken one example, what is E naught and what is E1, to get clarity in the film itself. So suppose your film, this is TIBS O. So this is the spectra. So this is E naught. E naught is here. So it will hit helium, basically will hit the surface and it will lose some partial energy. Then it comes by with 1.8 MeV energy in the surface. That is your E naught. So I will take to the FWHM, that is your E naught. And it will travel along that path, and you will have a silicon here. And before hitting the silicon, it will hit the last layer of your titanium, and it will come back. So that gives E1. The difference in your E1 and E2 will give you your delta E here, this term. Okay. So then you can estimate your energy loss in the, if since you know this material, what is this material, you can calculate using the SRIM. You can put it and you will get the thickness substituting in this formula. Okay. So I see different positions at see, this is one is having elements of oxygen and titanium and bismuth, but I see this is at three different positions. That is because of you have K is different for all three elements, and your cross section is different for all three elements. Finally, now energy loss, since it is a alloy or a uniform density, this energy loss is same. Suppose you have different energy loss, you have three different layers, then this spectra would have been different. So how it looks when you have a thin film or when you have multi-layer film. So when you have only one layer and any substrate or a freestanding layer, so when you hit an helium, you find this is yield, normalized yield or channel, or your counts, and then you will have a channels. Okay, so they look like this. And when it is a thick film, it is a continuation of combination of multi-thin film. So you can segregate this each layers, and this is a combination of yield that is coming from each layer. So when you combine this, you will have a spectra of continuous spectra of liquid. Okay. So again, moving to the next slide. So yes, composition analysis is important in this one. So this number of backscattered ions detected by particle detectors of solid angle uh, in angle theta called E. So this again, yield is your theta dependent and your solid angle, that is your detector solid angle dependent. These two factors plays important role. So my point of view, when I set an experiment, this plays very important. Since I know this, once I set these values, I will give you the data which already this embedded with these values. Okay. So if you want to calculate yield, you can area under the peak and how many helium backscattered atoms from your target. This is, you have y into your scattering cross section multiplied by your incident charge multiplied by your number of elements. So if you know the yield number of backscattering scattered, you can calculate your number of atom per centimeter square. So you will get always these numbers in atom per centimeter square. You want to convert it into 10 again nanometers, you have to divide it by your density. So energy loss struggling. So fourth concept that we need to consider here is energy loss struggling. So this is given by Bohr's struggling equation. So you can see these all terms are almost constant except this Tt is thickness dependent. Now you have more thickness, you will have more struggle. So finite result of your RBS always depends on your struggling. That is your resolution. That is your one. Sometimes you are, if you are a bit familiar, you use FWH between 28 to 25. So that is because of this one. So this is a term, but suppose you have very thin film, that doesn't matter. Suppose you have having thick film, you need to consider the struggling factor. Other factors that also include in struggling is, first thing you need to consider surface roughness of your film and agglomerations. Of course, you have multiple scattering or plural scattering, that you need to consider again this, because you will have scattering in different direction. Your yield may go or sometimes more or less, and energy fluctuation. This we need to consider. In our system, we have stable accelerator, energy fluctuation is less. But one thing we need to consider is that it is a macro beam, 2 millimeter diameter, and sometimes you need to consider this. Okay. So here I take some examples of RBS spectra that we have measured. This were there in Ojha's slides also. So this is substrate is silicon. Now you can see here this substrate is silicon. It has three layers. One is, first layer is platinum, second layer is cobalt, and third layer is again platinum. So you can see this is your first layer, and this is again third layer, and this is your second layer, that is cobalt, and this is your substrate. So why we have two peaks for your platinum is, your incident energy for platinum on the surface is different from incident energy of the platinum in the third layer. So that is why we have two different platinum layers. And suppose these masses are totally different, cobalt and platinum, the kinematic factor is totally different, they fall in different energy spectrum. So silicon around 1.1 MeV, and some cobalt around 1450, and platinum around 1840. So next we can take example of some alloy. So this was previous was multi-layers. Now you have only one layer of different elements, that it is has AU, AG, and SiO2. All three. So if you check the surface element of all three, they match with it. Okay. This is the position of your AU surface, and this is the position of course they are overlaying here. This is the, if you consider that FW of the silver and FW of silicon, even oxygen, all four surface elements you are having. This is the RBS spectra of co-sputtered silver, gold, and quartz. So let us take the better system. That means how good RBS is for multiple layer system. This is some consistent 5 nanometer films of gold and nickel. So first what you see is a gold, and second what you see is a nickel. Now each of these layers are well separated. So this is from layer 1 of gold, and this is layer 2, layer 3, layer 5, layer 7, and layer 9. So this is second and fourth, sixth, 8, and 10. This is nickel layers, and these are alternate layers. So okay, so this I can just conclude here that what we need to understand is four different mathematical concepts, mathematical equations, which you can easily recognize. One is your kinematic factor, second one is your scattering cross section, third is your energy loss. If you recognize these three, this becomes very evident that you became confident that you can look at the spectra, you can understand what is this element, and looking at this you can understand what is the effect of your post processing of your sample, that is your thermal treatment or even ion radiation. So channeling, I think channeling, there is a separate talk. I will cover only 2-3 slides I'm having here. So channeling, what it refers is, so it is when you see a single crystals, or so you see periodic arrangement of your atomic planes. So when you have a helium beam, helium is having very less mass, and a steering of beam energetic into an open space called channels between closed packed rows and planes of atom in a crystal. So you have a random arrangement. So most you will get the yield backscattered. You can see here. So suppose if it traveling in this direction, every direction you find an obstacle. Suppose you take, you consider it not, you are aligning your signal crystal exactly in the direction of your beam incident. So this is your helium beam. Helium is very less. So it sees a empty space here, and it is just like a tunnel, and it travels without any obstacles. So it don't see any obstacle to return it back, and it to come back it needs an Coulomb's reflection. You don't see, and it will travel through this tunnel or your channel. So your yield basically goes down to your 5%, of course. So you can see this spectra. This is gallium arsenide, sorry, gallium nitride. So this is the random spectra. When you see this, you can see this yield height is around 300. So when you exactly channel it, so you will have yield height say somewhere around 30. That is only you will get 5% of each one. And the surface peak, you will see that you will have some atoms left, and in the surface, which always you will get a backscatter. Once you cross the surface, there is no backscattering, and you see the channels, and it is just traveling. Backscattering, it is slowly reduced. So this is basically, if you have for impurities, you can detect it. Suppose you have amorphous nature, you can easily detect it, that is there. And two results that we did in our lab, I will take this, and quality of the epitaxial layers. So this is LaSrAl2 aluminum oxide, that is an TaTiO2. So this is doped in this one. So you can see when it is film is perfectly epitaxial, and your yield is reduced to 3%. Tantalum yield is reduced to 3%. So when you don't have a channeled, or when you don't have epitaxial layers, when it is not matching your crystalline axis, that your yield remains same. So you can check here, it is remains as 93% from pristine to your. So one more example, that is it perfectly crystalline, is this is an sapphire, gallium nitride and sapphire. So you can see the spectra. So this is random measurement, and when it is channeled, you will it epitaxial. So it reduced to 5%, that you can measure the quality of your epitaxial film. Second one, this is you have single crystals and you implant with low energy. So in this case, I have considered silicon, and it implanted with low energy silicon ions of 30, 60, 70 and 120 kV. So when you channel it and do it, so front layer will be of your, the implanted in region will be amorphous. So this basically the surface that you see is de-channeled. So you don't have any channeling here, and then you will have a channeling. So this is the pristine, and this is the random, and this is 30 kV implanted, this is 60 kV implanted, and this is 70 kV implanted, and this is 120 kV implanted. So when you convert this into surface into depth, so I've used the code Decada to convert your energy loss to the depth. So I can define this, how much is the D channel length, that is your in nanometers, it is for 30 kV is 20, and 60 it is 40 nanometers, and 70 it is 50, and 120 it is 80 nanometer. Similar way, we can also, I have noted down the chi minimum also here. So with increase in the energy, your defect density increases, which almost increases your chi minimum. That means your channeling factor is decreased here. So you can see here in a red line. So this goes chi minimum around 46%, that you have more de-channeled factor in this sample as compared to that of your pristine or 30 kV, because your defect density is high. So again, the same samples, when you anneal it and you give thermal treatment to recover the your crystalline nature. So when I do the same samples for annealing and do channeling, so most of these are recovered, and you can see that that's, yes, it has grown your recovered your epitaxial layers, but it is grown by layer by layer. So here I have used a different temperature. I used 500, where your nucleation almost starts, and 650 uh, So 550, you can see this blue line where your nucleation starts at your amorphous crystalline interface, and then it goes at 650. You can see that it is already, you have a crystalline nature grown, and in 840, some defects may be left that also you can probe here, interfacial, that is called, they are called end range defects, which we could not recover after annealing. So this second concept, I am just skipping it because it is more detailed there in another talk. So we can go to the resonance reactions. So in my first content topic, I started with Rutherford backscattering and Rutherford cross section. So resonance is refers to the non-Rutherford scattering. So that is elastic resonance scattering, non-Rutherford backscattering spectrally. Sometimes you may read it as NRRBS or resonance RBS. Generally, I use this term resonance RBS. So what is this resonance? So in RBS, it is pure Coulomb process. The scattering occurs between two completely unscreened nuclear point charges. So yes, when it reaches, you can go to this slide, and this I have taken from Ojha's presentation. You can remember, you can recognize this. So it is easy when you have your projectile has traveled up to here and it is returned and it is now detected in your detector. Yes, this is Rutherford cross section. Suppose you give more energy and it reaches just close, because if it is helium is having very less mass, it can just go near to your target, and there when it that distance, the closest approach became the sum of your radii of your target and the projectile. Then you will have a nuclear force interaction that leads to the deviation in the Rutherford crossing section. Once you have a deviation in Rutherford scattering cross section, that is your non-Rutherford cross section. So for MEVNs, so if I consider typical example of helium resonance with oxygen, oxygen is somewhat comparable to the helium in terms of mass as compared to that of heavier elements like gold and mercury. So it can go very close at when you project it at 3.045 MeV. So it will have nearest radius of approach, and then you will have non-Rutherford cross section for scattering. Where here in this oxygen resonance, you will have your yield increased from 4 to 16 times. So in different you have so this is basically possible in low Z elements like hydrogen, helium, lithium, silicon and all. So this becomes advantage. So if I take this slide, if this is the normal RBS, this has surface as oxygen, and this is a normal RBS spectra. So you will not be able to detect your oxygen content on the surface. So this is 700, region around 700. This is where it is expected to appear, but it is very small. We are not able to detect it. We can take advantage of such situation to tune energy, tune it to resonance energy, and find these carbon, nitrogen, or oxygen, or silicon in heavier metal. Basically, so in general, we use substrate like silicon, quartz, or gallium nitride are different element. Your film will be some different element. So I have few examples where we can consider this situation as more advantageous. So your oxygen resonance will be at 3.045 MeV. So if I do, let me explain with this sample. This is a ZNO film grown on a sapphire. So if I do a 2 MeV, you're looking at the spectra, so you can identify this is Zn. So when you want to identify or quantify oxygen, it is bit confusing whether this oxygen is coming from your Zn or it is coming from your substrate itself, and it is somewhat overlaying here because you have we have aluminum signals here, you have oxygen signals here, oxygen coming from your aluminum oxide, oxygen coming from your Zn. How clearly you want to differentiate? So I will tune the accelerator to the energy 3.045 MeV. Once I have a gain set, electronic set for the detection of that one, you will have a resonance reaction where your yield goes very high. Now you can see here alpha cross alpha for oxygen 16 at 3.5. your oxygen is just detectable at the surface. And this is exactly a small window will be there for your energy. So you can see the first figure, this is cross section ratio to the Rutherford, and this is the energy. You can see the width of this one, this energy width is very less. So when you tune exactly the 3.045, you will have the resonance. Suppose your energy is not 3.245, it is bit less than that, you will not have any resonance here. Okay. And yeah, in one more example here with multi-layers, so you can see a very small hump in the silicon, that is your oxygen, but when you tune it to 3.05 MeV, yes, you have a clear separation and you can quantify this one. So similar way, we have nitrogen resonances. So this I've taken from the sigma calculator. So it basically depends on yeah, it is, now we should remember that is an theta dependent. Your cross section is theta dependent. Now this here it is written is 177. So energy I have selected in a wide range. So resonance, the best resonance I can get here is 3.6. So this is, and when energy width is bit high, or I can go somewhere around here also, they are very narrow, which may not be able to tune, and this is very less, cross section is less, and here it is also less. So better I will opt at 3.6. So one of the example that I have considered here is oxygen and nitrogen implanted silicon. So black color that you represent the bare silicon, that is, it is having zero nitrogen, so there is no resonance here. And oxygen implanted, and I'm tuning it at a nitrogen resonance. Yes, there is no nitrogen, so that means your surface is clean, you don't have any nitrogen. And third example, that is in the green color that you see, it is implanted with nitrogen, and now I'm detecting it. So for implantation case, so you will have energy, you will have nitrogen just in the buried surface layer of your, sorry. So you need to keep your energy just a bit higher than this 3.6, an exact energy that more than the way 3.065 or 3.7, so that your nitrogen is detected. So similar way how it detects, yeah. Now not to get confused, so it is this was there in the previous slides also. For thin film, when you see that when you have helium here, it is 3.60, and you will have a resonance spectrum like this. Suppose your nitrogen is not there in your first layer, that is your first layer, and you will have in the second layer. So now you need to increase so that when this helium reaches to the second layer, so you need to have a sufficient energy, that is 3.6, to have resonance. Okay, this example, I will have one more example here that I will explain you. So this is one more carbon resonance at 4.25 MeV. Yeah, so this is a graphene oxide and sapphire. Again, if you see the first spectra, you see almost this is everything is overlapping, and you will not be able to find your carbon and oxygen content also. So yeah, here it is oxygen, it is seen, but you are not able to see any carbon. So in such cases, if you want to find the ratio between carbon and oxygen, then it is not possible. So tune your accelerator energy to 4.258, and then you will have carbon signals here. So you can get this. This is very high, and this cross section yield height is 120 times more than that one. You may have different resonances also, like 3.2, it is carbon, the resonance for carbon 13, you can also do it, but it is very less, but better to do. Right now we are in our system, we are not able to go up to 4.2, but we can go with the conditioning or other things. So this one, yeah, can we probe depth profiling in resonance mode? Is yes, it is possible. This we did a few time back. So this was one of the sample of TiO2 on silicon substrate, and they were trying to push your oxygen vacancies to deeper inside, and they wanted to know how much deep the oxygen has been pushed. So the idea that came out with the resonance experiments is, okay, So oxygen resonance is 3.045 MeV. So on the surface, we get a good yield of oxygen, that is your oxygen is more. So now I want to probe this oxygen content along the depth. So I select different energies. That means each time I'm tuning the accelerator to higher energy, so that when it reaches just next layer in the depth, so there the energy is 3.4 MeV, so that you have a oxygen resonance at each of the point. So you can see that in second your yield is reduced, and when you increase further energy, again your yield is reduced, and that means your oxygen content at the surface is more as compared to the top your deeper layers. And finally, when you reach a substrate, you have almost no oxygen content. Okay, so yes, these are some aspects which I understand better and you understand less. So how to know this resonances is you can go to always the directory database. So INBL website, you have a link. You have a link here. You can go this, or you can search within the Google and you will get it. And on the left hand side, you see here, so INBA, so you see the nucleus, what is your projectile and what is your type, what type of reaction you want, whether you are EVS, that is RBS, whether you are having NRA, RPXC, or bio. So I have taken one example, such example here is a summary. The first figure that you see, it is a summary. So you will have all reactions, you projectile, different projectile, that it is your proton, deuterium, helium, alpha, lithium, and you have different target elements here. So this uh, I have taken, used sigma calculator, that will basically send a directory that you will has a lot of database you can check. So for oxygen you have so many resonances. So I have chosen it 3.045 because it is very clear and my energy is a flexible range in this one. I can tune my accelerator between 2 MeV to 4 MeV, so I select. So if my accelerator permits me to go higher energy is at 10 MeV, then I will choose this one because this width is more. Suppose you have a low concentration in that range, that means your struggling will be more for helium, then it can detect this, and if that may not be possible in this sharp resonances. So second topic, we can conclude that this plays very important. We don't often do it. Suppose if somebody requests this, so we go for resonance, or sometimes we suggest you can go for a resonance when you can't detect a carbon or oxygen or nitrogen and exactly on the surfaces or in the
How
bulky
much,
surfaces.
Umapathy, excuse me, how much more time you need?
Sir, 2 to 3 minutes,
Okay,
maximum 5 minutes.
okay, continue.
Okay, so let us go to ERDA, that is elastic recoil detection and analysis. Yes, in RBS, so low Z elements is not possible to detect. When they are going, and then we discussed it can be overcome by your resonance. But suppose you have hydrogen in your samples and your projectile is helium, you will not be able to detect. Yes, somehow they find a way. In Equer in 1976, he proposed how to detect hydrogen and hydrogen depth foiling in Doyle frequency in 1979. So in our case, we consider only helium beam because the permitted beam is only helium. So lesser than helium is hydrogen and deuterium. We can detect this hydrogen and deuterium in the same RBS setup, just altering some experimental setup. So there are three things to be altered. One is you need to put stopper file, change the incident angle and detector angle. So why we need to change the detector angle is, so now you are no more detecting backscattering, you are detecting recoil. That is your hydrogen. You need to put at a forward angle so that you can detect your recoils easily. So why we change to incidence angle is, suppose that you are incidentating perpendicular, then you will have your projectile will transfer, get energy from your from helium. That means helium will transfer much of energy to the hydrogen and it will go much deeper. Suppose you incidence in a grazing angle, it is emerging out, it's coming out. And stopper foil, we need this one because your recoils will have both hydrogen and helium. Then we are not interested in helium, we are only interested in hydrogen. So we need to stop this helium. So we can put a stopper foil. Typically in our setup, I use aluminum foil of say 11 to 14 micron. So this I can have this setup, I will tell you. So these are the areas where hydrogen importance relevance is there. It is most common impurity and is having high diffusion coefficient, and it changes many chemical and physical properties of the films or the material. And especially hydrogen is studied in your nuclear industry, that is your shielding materials, where what is the effect of your hydrogen in your material, and of course in the energy storage device in solar cells. That I have few examples of this one. So again, to the mathematics or the physics concept, again this is 4: kinematic factor, differential cross section, stopping power, and energy loss. Now in the previous one we ignored energy loss, not much considered, but we need to consider because it is traveling to your stopper foil, which is very thick. This is around 14 micron, and you have to consider this. Stopping power, again it is stopping power for not for helium, stopping power for hydrogen. So differential cross section and kinematic factor both for your recoils, not for your projectiles. Yes, this is simple kinematic factor. Now you are calculating it for recoil, that is for your hydrogen, that is your 4 m1 m2 cos divided by m1 plus m2 square. So again, recoil difference cross section, that ERD cross section, it is again Z1 Z2 divided by theta. If you fix it, it is almost energy. If say I am fixing at 2.8 MeV or 3 MeV, so Z1 is fixed, Z2 is fixed, and theta is I'm incidentally or exiting at 30 angles. This is you can also calculate, and it is more level energy dependent. Okay, resolution. Yes, concentration, you can get how much percentage it is there in your film or how much percentage it is there in your surface. Yes, you can also probe along the depth as in case of RBS. Now you see the diagram here. So this alpha is incident angle. Suppose if it is coming from here, the energy will be different. Suppose it is coming from here, it will be different. And it is coming from your end of your sample, it will be different. So this gives you, and yes, we need to consider this foil because we are stopping all our helium here, and we are only detecting our hydrogen. We need to consider this energy loss in your foil also. So this is RBS and ERDA at IUC our lab. So this is the diagram. This is set for both RBS and ERDA. So simultaneously, if you can do RBS as well as ERDA and this setup, in earlier slide was Ojha's law. So Ojha's only for RBS, which is your best resolution is at 180 degrees. So we keep this at your 166 degree. Now it is altered. Now I have grazing angle incident and detector at forward angle is 30 degree. And I have used this. You can see this picture. This is the stopper foil. So initially I started here at 2.8 MeV and it was 11 micron foil, and we may have to increase the energy, then you will have your most of helium passing through the film. Then I selected a stopper foil of 14 micron. 14 micron will completely stop your uh, helium and it will only permit your hydrogen. So yes, so energy we can vary in the range 2.8 to 3 MeV at the present, and RBG, which this is the grazing angle detector, this is the movable detector, this will be generally at 110 degree. So I can move and fix here at 30 degree. This is your now it works as an ERDA detector. At 166 is an RBS detector. So few of the examples that we did as hydrogen implanted and hydrogenated. Hydrogenated thin films are the bulk surfaces. This is one of the initial measurement that we did in graphene oxide and say grown on a silicon. So how it is exposed, you see here that initially during beginning of the experiment, we are trying to increase the hydrogen counts. We made the aperture more. Yes, hydrogen count started increasing, and this one is taken. And you can see the black line, it is not visible. When you clean the surface properly in the silicon surface, you don't see any hydrogen. This is coming from your oil vapors, which is deposition and our calibration sample. So this is the spectra of geofilms treated with, you can check this paper and the so you have more oxygen content in your graphene oxide with the time that you are exposing it to the hydrogen atmosphere. So just taking to the detection. So this one was an IBM film, niobium material. Then when it is exposed to normal atmosphere, it will absorb some of the hydrogen. And when you treat with the thermal, when you bake it, and some of your hydrogen content will be reduced. That you can directly get it from ERDA measurements. The red one is your baked one. It is a normal one. And this one is again tungsten. Second spectra is a tungsten material. This is used in nuclear shielding and and many other purpose. They have implanted with the deuterium. So you can see the black one, that is deuterium is less than your hydrogen. You see this one is D and this one is your pristine, that you can see that this is a hydrogen and this is deuterium, that you can detect both hydrogen and deuterium, and this you can also use for calibration also. This one example in the surface hydrogenated surface on silicon. So this I try to analyze this one, how much it is having. You can calculate the yield with same equation that I've shown in RBS and reverse. And this one is one of the best result that we got when you have a platinum islands on a Fe2 iron oxide, and when they were trying to attach this hydrogen to those platinum islands.
Umapathy, you may conclude now.
Yes, sir. This is the last reference, and thank you. And if you have, you can just one or two questions we can take.
Sir, Foreign sir, there are a few questions in chat box.
Yes.
Okay, you can read those questions.
Why helium ion with energy 1 to 3 MeV is used in RBS, not any other ion or energy?
Yeah, getting less than 1 MeV is difficult. Yeah, you can use it, but we need sufficient energy so that it is backscattered. You need a good resolution. You need better count. You need to go for higher energy. So 2 MeV. Suppose you go very high energy, so you will have a lot of resonances. Suppose you have silicon, so above 4 heavily, you will have many silicon resonances, though it fits to even lesser energy. Yes, you can do it with other beams also. Yes, you can refer with many papers they use with the other energy or other beam. Yeah, it is best, always best and suitable with 2 MeV or in the range of 2 MeV. Yeah.
So Amandeep Sharma wants to ask, one of your slide it was counts and in the other one it is normalized yield. Could you elaborate the similarity and dissimilarity between these terms? Rather, how fluence is different from these? What will be the units of all of these quantities?
Okay. Basically, your RBS will yield is counts. You can refer it as a yield, backscattering yield. When it is normalized, when you know that normalization factor is there, or you can simply normalize when you use it maximum to minimum. So when you compare with different elements, you can different spectra, you can normalize. Suppose you are having, so I use two different softwares. So one is normalized, that is rump. You see normalized yield always, that is itself it gives you normalization. And when you plot in Seminara, you will see the count. As such, there is no difference. When you use normalized yield, you can put arbitrary unit, or you can leave it as it is. Otherwise, counts is also okay. Both are accepted. How fluence is different from this? What is there's no? See, you can normalize here. You can convert into counts itself. No issue. They are almost same.
And Jorian would like to know how about the natural width of a resonance reaction?
Some we can say, but that will be very less, and you will have other electronic setup. Of course, we will not be able to do that one. We have to tune to particular energy. That may not we can, but I also understand less with this because it is purely in nuclear physics phenomena.
For the resonant reaction, you need a good detector, because otherwise the natural width of the detector also affects the quality of your resonant spectra.
Okay, any other question, participants? So if not,
Can I
yes.
say
somebody, yeah, please.
Excuse me.
yes, this.
Yeah, Professor Kant.
Yes, hi. Just to add on to the resonance, of course, if the resonance is narrow, it's fine, but some resonance might be wider. Then, of course, then you need to add that onto it. It depends, of course, on your. You just look up the resonance width. I guess I didn't look up this table you had, but I guess the width of those resonances. Hopefully, they're also in this table. And of course, if they're very small, then it's no issue. But if they're getting wider, then you might have to. Then you have to, of course, take that into account.
Okay, yeah.
Yeah.
And
Thank
one more thing. Sorry, the range for helium backscattering depends what you want to do. Because in our center we have a high resolution system, which I will not discuss tomorrow, but just wanted to make one remark on that, since we're now talking about Rutherford backscattering. That system was designed by Kobelko with a sector magnet to have a resolution of detecting backscattered particles of 1 keV, then the energy resolution. So then, of course, you can have very good surface depth resolution down to 1 angstrom, but then the energy of the helium would be more appropriate to be at lower energies, at maybe half an MeV or so. But it's just I mean, depends, of course, on your facility and what you want to do exactly. There's just a remark. Sorry.
Okay. Thank you.
Okay.
Thank you for a nice remark.
That is a high resolution RBS system. You can refer that one.
Anybody else have some query or some comment? If not, maybe we can thank Mr. Umapathy for such a elaborated talk. Now we'll take a 5-minute break before going to the next talk, or your demonstration rather, by Dr. S.A. Khan.
So there will be a hands-on training on SRIM. So keep your computers ready for that session. He will be explaining you how you can use the SRIM to calculate the energy loss and how you can select the ion to bombard your target. Okay. So participants, keep your computers with the SRIM code installed on it ready. So we'll break for it is 47. So let us break for 5 minutes and then come back. Okay, sir. Thank you.
Umapathy, can you remove your presentation now?
Umapathy, are you there?
Yeah.
You have to stop presenting. यहाँ से arrow को नीचे stop presenting press करो.
Yeah. Yes. Ma'am.
Okay, thank you.
Am I audible? Yeah, direct one or through this mic?
The mic only, I am listening.
Okay. Okay, thank you.
अब 50% है सिर्फ attendance.
60 है सर.
हम लोग भी तो हैं.
10 people if they can learn that is
So welcome back after the break. Foreign sir, would you like to? Hello. Okay, so today we have with us Dr. Saif Ahmad Khan. He is working in IUAC as a scientist F, and he has a vast experience with the simulation, an expert of SRIM trim codes. So today he will be giving you hands-on session on SRIM and trim. So let me welcome Saif sir. Saif sir, over to you.
Thanks, Indra. So you have said so many good things about me. Actually, everyone is learning each day, and so we cannot say we are expert, but you can say that I have been working a little longer than you, but that's all. And I am sure that within few days, within few months, you will also be able to use these programs. Even today, I'm hopeful that by today also you will be able to use it, and that is the objective of this hands-on session. That during this session, you will have options. You will have opportunity to run on your computer these two programs. Actually, these are bundled into a single one, and which is called SRIM. So in the last 2 days, you have seen that there were lectures in which it was highlighted what are the theories behind ion energy loss in a material. And you were also shown that there are some programs which can help you in calculating the energy loss per unit length or stopping power. And you were also told why it is important. See, in the previous lecture, you saw that for depth profiling of elements using RBS or ERDA, we need energy loss per unit length calculations also. So it is not very easy to do hand calculation all the time. So it is useful if we have some software which can do this type of calculation for us. And if we are running on a computer, that will be very fast and accurate also, depending upon the coding. So in this session, we'll take up one of the program, which is called SRIM. And with this, you can find out energy loss per unit length or stopping power. You can find out other features like how much damage is there due to ions, and what is the sputter yield. Although Professor House has told you that SRIM is not the best option to calculate sputter yield, but this option is there if you want to have rough estimate or you want to see some trend. And also you can find out other things like ion distribution inside a material. So these things will cover in this hands-on session. So foremost, I would like to ask you whether you have been able to install SRIM on your computer or not. So because this is very essential, if you are not able to install it, then you'll not be able to follow the hands-on session. So I see that one of the participant, Vinayak, has not been able to install. Second one, or third, oh, okay. If you have been able to install, then very good, and no need to tell us. But for those people who have not been able to install, please let us know what are the problems you are facing in the installation. So if we can help you, then it is good. So Vinayak, what was the problem?
I faced a problem when I was trying to install on Windows. There was an error just coming for extracting the file. So at that time, the error was showing. So that's the problem I had faced.
Okay. you have the exe file, right?
Yeah. When I was trying to extract the files from the zip folder, the window has shown that there is some error.
This is because either you don't have full downloaded file, means it is corrupted sort of, or if you are extracting to some folder where you don't have permission, then that is also an issue. So you can do one thing, you can make a temporary folder in, for example, another drive. Suppose you have C and D drive, then you can copy that exe file into a temporary folder in D drive, and let us call it SRIM or something, and then again you just try to extract the files. Maybe that will help.
I think I just do it later on, because right now I think it will be I think your time will be just going to waste it through this way.
But you are as important as others, so I don't want that you lose out. But anyways, yeah, but side by side you can work on it.
I will try.
Thanks. And regarding one more person.
Sir, good morning, sir. I'm Cynthia, but I couldn't download it, sir, because the format is coming like box. There is no letters.
Actually, what is happening? This is what is happening. Your internet browser is actually showing you in a text format. So actually, you can try to right-click on the link and save and select the option save file as or something like that. So try to do from there. Instead of clicking on the link, you try to right-click and select the option to download on your computer. Maybe that can help.
Okay, sir.
Just give a try and let us know.
Okay, sir.
So meanwhile, you can listen to some of the little introduction I have prepared for you.
Okay, sir.
Okay. So SRIM and TRIM are very useful for understanding the ion-solid interaction, because if you want to correlate some property changes due to ion irradiation, then you want to correlate with the stopping power, for example. And in that case, this is very useful. And if you want to prepare some energy degrader, then also you can use it. You can use it for various other things like implantation, doping, and other things. This has been covered in the theory lectures. So let us focus here how to use it, and we'll take up some examples. So Professor Hofstad yesterday told you that stopping and range of ion in matter is a program which calculates energy loss based on the fitting and extrapolation of experimental data. Okay, and also there is a TRIM program which is transport of ions in matter, which is bundled with it. So it is a Monte Carlo program which simulates the ion irradiation of amorphous solids. And he also told you that it is based on binary collision approximation. Actually, he also told you that it was developed by James F. Ziegler and BSF, and now it is being taken over by his son, MD Ziegler. So this was launched in 1983. Then several refinements came into existence, and the latest version is SRIM 2013. And so for energy loss measurements, IUAC is also been contributing to provide more tables. So here I have listed some of the publications where researchers carried out energy loss measurements at IUAC, and some of them have been included in the SRIM database also. So in this session, we'll require mainly 3 programs. SRIM 2008. This is the easiest one to install, because SRIM 2013, when you install SRIM 2013, there are some error messages, like some 4 or 5 files are missing. So this is a little bit problematic. But if you want to install SRIM 2008, it will be very smooth. And I think you can run on Linux and Macintosh also using Wine program. Then to plot the curves, you will need microcalorigin or something like that. Okay, so whatever graphing software you are familiar with, you can start, because we'll be getting some text file from the SRIM program, and that you can export, or sorry, import into your graphing software, and then you can plot the graphs. And you may also require to edit the output files. So for that, you may use a Notepad, WordPad, or gedit or VI in Linux. Okay. So I think now we can start with a little introduction, like from where you can get it. So most of you people, we have here 61 participants. Many of them are have already installed it. So you already know where which site you have to go for to downloading these programs. So this is the interface there. So after that, once you download SRIM, it can be installed on your computer, and first screen is like this. So on the left side, many people don't focus. Like here it is showing calculation 18. So that means after installation, I have performed 18 calculations. Okay, so this is the first window you'll get. Also, if you are installing it or running it for the first time, you will also get some message like which will be a description of this program, and that you can read and then click OK, like that. So here we have 2-3 tabs. So first one is for calculating energy loss per unit length, stopping power, ranges, etc. Then trim is, as we already discussed, this is Monte Carlo program. And the last one is experimental stopping power. You can see what are the experimental data available. Some of them can be accessed through this. And also, we are going to cover some of the examples, but there are many SRIM tutorials available which you can get from here. SRIM tutorial tab. Okay, and this also shows you which version it is. Like on the left bottom side, it is showing SRIM 2008 is the version I'm running, and of course some legal notice things. And there you can notice there are some question marks on the screen. So if you need help regarding the text over there, click on the icon, click on this question mark, and you will be provided with description. So these descriptions are very useful for understanding this program. Okay, and last option is quit if you don't want to carry on the calculation. So if you click on SRIM, stopping and range tables, then you will land up on this window. Okay, so this window has different portions. First one is for ion description, like what is the atomic symbol of the ion, then what is the atomic number and mass, atomic mass, and since you are going to generate a table, so lowest energy and highest energy you have to mention here. Somewhere it was written that highest one is 2 GeV, so and lowest one is 10 eV. But here these are these are in kV, so you have to keep in mind. Suppose you are going to put MeV, then you have to adjust there. Then there is a block for target. There you can write the name of the target, okay, and its density, whether the target is in gaseous form or not, that you can check from there. And in the lower portion here, here you can describe what are the elements in your target. So you can build up a compound also. And so now we come to the lower side. This is the unit of stopping power which you would like to use. And last is the compound correction. Okay, so in lighter compounds of lighter ions, you have to put some correction factors. And after everything we have put here, then we can click on calculate table to generate the stopping power and range table. So with this brief description, let us actually perform some calculations. So we'll take up few examples. Like we'll check the values provided in this paper. So here they have calculated different parameters, different values for different parameters for nitrogen and phosphorus ion in silicon. Okay, so are you able to follow it? I hope everyone is able to see my screen. Actually, this is a hands-on session and I'm not able to see whether you are able to do it yourself. So one option is that one of you can share your screen and we'll see whether you are okay with it or not. So first I will demonstrate, I will take up one example and then probably we'll call one of you and that person can share his screen and perform calculation for the second set of ion. Okay. So here you can see the ion energy is 80 MeV and material is silicon. Okay. So let us check how much we get from our software. So just you can note down on your paper because swapping different screen will be little time consuming. So range is 89.23 micrometer and electronic stopping power is 2.62 into 10 to the power 3. Nuclear stopping power is 1.45 and units is MeV centimeter square per gram. Okay. So now we'll go to the SRIM program. So first we have to put information about the ion. So the ion is nitrogen. So this we can specify from here. We can select the periodic table and then select nitrogen from there. Or we can write the symbol here, or we can select from this drop down. Okay, so we have already input nitrogen and all the data has already been filled here automatically. And now we have to put the energy. So here it is written 80 MeV. So this is 80 MeV. 80,000 kV means 80 MeV. I hope everyone is able to see this because the fonts are small. Okay. Then now we have to put information about the target. So here you can write silicon, for example. It is up to you. This is for your information. Then from here we have to tell the computer that the target is silicon. So silicon. Okay. So atomic number is 14. Its mass is 28.086 mu, and then stoichiometry is 1. Means what is the fraction, atomic fraction? So it is 100% silicon. So here also you can see 100% silicon. So automatically the density came here 2.32 because this is inbuilt. But suppose you, for some material you have different density for different phases, for example, then you can put that density there. Okay, so now let us click on stopping unit. Okay, this is already matching with the unit used in the paper, so we'll not change it. Then since this is heavier material, so there is no need to perform any compound correction. Okay, so now let us click on calculate table. So it will ask you what is the name of the file you want. So I agree with whatever this is telling, because this already contains what is the ion, what is the material. So I'll stick with this. After that I press OK. Now if we see this table, it shows that SRIM version, etc. This says then about ion, then target density, etc. About, so all the information about ion and target is here. Then Bragg correction or the compound correction, that is 0. After that the stopping power unit is mentioned. Then we get a table. Okay, so in this table you can see values for different ion energy. So I think we need only this last one. Maybe, and so I don't know whether you are able to see this. Yes. So electronic stopping power is 2.62. Nuclear stopping power is 1.45, 10 to the power minus 3, and projected range is 89.23. Okay. So this thing we can check with from the paper. So I think I see that these values are matching with the ones mentioned in the paper. Actually, we are not here to find fault in the paper. This is just for illustration. I guess everybody now knows how to find energy loss values and also the stopping power. Sorry, this projected range. Next two columns are regarding straggling. So this is nothing but like you have standard deviation in some values. So you can say like error. This is because not all ions are going to have same interaction in the material. So they will not stop at the same depth and so on. So that is why there is a variation. So this is also given. So with this you can see what is the type of depth distribution laterally and longitudinally. So Indra, can we ask one of the participants to calculate for phosphorus ion?
Okay, so one of the participants can try for phosphorus ion on their PCs. Who is trying? Will somebody give a try to calculate for phosphorus ion? Yes, Razia, you would like to try? This is a hands-on training session. If we keep on speaking and you are not at all responding, then there is no use of having such sessions. We are keeping it. Yeah, Punita, please share your screen. That Taranga.
I am trying.
Yeah, Taranga, 100 MeV phosphorus and silicon, you try to calculate. Okay. Very good.
MeV phosphorus.
100 MeV phosphorus in silicon. So you select the ion from here, phosphorus. Nitrogen ke niche, haan. Yes. And write the energy there.
Energy.
So you can see 100. That it is in keV, okay? So you have to add zeros accordingly. Yeah. Very good. So you now select the target. Yes. Silicon is already chosen. Yeah. Good. Now you can. Sorry.
Where to will be same in ME?
This will come default because it is from the periodic table. It is taking the silicon ke liye. This is the weight. So you can, Saif sir, you can tell them to select the unit. Have you already told them what to select as units? Okay, so you calculate.
We are going by. Sorry.
Exactly. So you can see here that this is in MeV per mg. So you click here and you go to EV per angstrom or something like that, so that it will.
EV per angstrom.
keV per micron is also okay. So you will know that how much energy is lost per micron.
Okay.
Okay.
Then I am trying keV per micron.
Okay, you try this.
Okay.
And then calculate table.
Calculate table.
Yes. So okay, it will save the details. Yeah, fine.
These are the details. So we have to see for 100 MeV.
So you can see that how how your energy is getting lost inside your material. Okay. So this unit, if you go to the top of this table, go to the top of this table.
Yes, ma'am.
Okay, so you can see that dE by dx, electronic and nuclear energy losses in the second and third table, they are in keV per micron.
Yes.
Okay.
We have to keV per micron.
Right. So 9.05 into 10 to the power 1 energy keV is lost per micron when this ion is traveling.
10 keV ion.
10 keV ion, right. So is it clear to other participants? And this is the range, 10 keV ion is actually moving inside your material, 169 angstrom. So you all other participants, you also please try to do some calculations, so that if you have some doubts or some problem or understanding issues, then you will be able to rectify it here. Okay, so other participants, I request all of you, please try some energy and some target. Arbitrarily you can choose. Saif sir, is it okay? Now we can proceed. So you stop presenting, Taranga. Very good. Okay.
Thank you, Indra.
Welcome, sir.
So I guess everybody is now familiar with how to calculate stopping power, right? Vinayak is asking whether he can calculate for carbon.
Yeah, so you try it in your system, you can try for carbon, and the Santosh has written that 100 MeV is losing 1.23 into 10 to the power 1 keV per micron as per his table. So it is fine. Okay, so since we were on the top of that table, so we could only see the keV.
Right, right. So depending upon the unit, no, the values will be different. So, but I think the range is correct from the table.
So you can proceed further then.
Yes, we can now go to the next example.
So Amardeep has requested for a composite material.
Okay. Sure, I think we'll cover some of them. So all the people, you can see this screen and just you can verify whether phosphorus and you got the same numbers. But keep in mind the unit should be this one. Okay, so next, how to find out what is the energy of the transmitted ion? Because this is sometimes useful, like if you are designing some energy degrader, or if you want to find out what is the energy loss or stopping power at the interface. So that time also you need to know what is the energy at the interface. And also for RBS and similar techniques, they have to find out what is the energy lost in different lengths, different depths. So let us see from our table how we can calculate what is the energy left after passing through certain depth. So here we take example, previous example, 80 MeV nitrogen in silicon, but here let us assume that the width of the thickness of the silicon layer is just 60 micron. So after passing through 60 micron, what is the energy left of nitrogen, that we can find out from same table. For this, you can go to the row corresponding to the incident energy, 80 MeV. Here the projected range is 89.23. From this value, you can subtract 60 micron. Okay, 60 micron if you subtract, then its value comes out to be 29.23, which is very close to this number. So we can say that after passing through 60 micron, the energy of nitrogen will be 35 MeV. Okay, so this is one of the easy way to calculate what is the energy left after passing through certain depth. So that's why, suppose our intention was to find out what is the energy lost at the interface of silicon and some other, let's say next layer is some other material, then you know that after 60 micron the energy will be 35 MeV, then the energy stopping power of nitrogen will be this much in silicon. Similarly, if you know the energy of this ion at the interface, you can find out the stopping power in the beginning of the second layer. Okay, and this can help you in planning experiments. Suppose you want narrower depth profile in certain material, then you can put some foil in front of the material and then do irradiation. That way some energy will be spent in the foil, and you will be having lower energy of the ions left, and they will not go that much deep in the material. Okay. So some people were asking what should be, how should we put some information about compound. So that can be done using SRIM again. Like if you have SiO2, then we can add element, and here we can select oxygen. Oxygen in SiO2, oxygen is twice, so we'll put 2 here. Automatically the atomic fraction is calculated. Now from literature we can find out what is the energy, what is the density of SiO2. That density we can input here, and after that we have to proceed like we have been doing earlier. I think this answers some of the question. So Amandeep had asked this, so I think now he knows how to put information about compound targets. Now let us move to TRIM. In TRIM also you will, sorry, in TRIM also you will find okay, just a minute. Before that we can find out how to draw these type of curves, where we want to show what is the stopping power as a function of depth. So here we can take another compound which is BGO and try to find a way how to plot these type of graphs. We'll take only one of the case. Let us say we take 17 MeV carbon and then plot the stopping power in BGO. Okay. So this involves a few other programs, so just be careful. Our ion in this case is carbon. Energy is 17 MeV. Okay. And target is a complex one. So bismuth the projected range of the incident ion. So projected range of the incident ion is 10.02. That value you can put here. Then after that, you subtract values from column E. Okay. Okay, so now we have generated depth scale, in fact. Now, the last step is just to plot.
Okay, may I, sir, say something? So
Sure.
participants, you can see that there are some curves which are shown here. Okay, so these curves in column number C, D, etc. These actually are representing the DE by DX curves. In your present in the ion matter interaction presentation and the Hofsa sir's talk, you have seen that there are SE and SN curves. Okay, so same thing they are also representing. So if you plot the energy versus the SE by SN which you get in SRIM, the same kind of behavior you will be able to observe. Just for the correlation, I am saying this.
So you can see that I have now plotted it. On x-axis is the depth column we have just now generated, and then there are two curves. First one is electronic stopping power. Second one is nuclear stopping power. And the color you can change, so just to distinguish. I think I selected the wrong color. Okay.
Is it clear to you all that how your ion is actually losing energy when it is going down? It means inside your target material in terms of your SE and SN.
Okay, so you can see that SE values in the paper and what we have generated from origin looks similar, right? Only thing is the values are not matching. This is because in our graph it is in EV per angstrom, and in the paper it is keV per nanometer. That's all. So once we change the units, it will be same. So there is no problem with electronic stopping power, but we can see that nuclear stopping power is not matching with our, because we had calculated only for 10 keV. If we calculate for smaller energies also, then we'll get a peak like this. Okay.
So here in this energy regime, electronic energy loss is very minimal. That is why it is only stopped. That means it's not shooting up like shown in A or B. So Taranga wants to know how you calculated depth. So basically, he showed you in this origin last column.
Yes.
Where you subtracted the range, highest range from the range table. So this is how you calculated the depth.
Correct.
And one more question was there, how to choose the compound correction factor for lighter ions. So this question you have taken up already, sir?
No, I haven't taken.
SRIM NJ.
Actually,
compound correction factor.
That is true. Actually, the SRIM has some of the known compounds already listed. So they have a compound directory from there we can select some of the known compounds. For those compounds, they have already have mentioned what is the correction factor, but for other things we have to verify through with experimental data, otherwise we'll not be able to know.
So maybe you can tell them where it is, so that ready-made compounds, if somebody is working on, they can take it from there.
So this is in the first window. So if you click on compound dictionary, you will see a list of compounds. Actually, I am not able to understand why it is not displayed in my computer. Maybe because it is Microsoft, Windows 10 Home Edition. If other people are also facing the same problem, then it may be the common problem. Otherwise, it may be because of only for me.
Okay, so if suppose your program is compatible, then you will see some names of the compounds and alloys here in the common under common name. Okay, so you can directly choose whatever is suitable for you, and you can calculate the tables accordingly. The Shanmuga wants to know why you subtracted the ion energy. So we have not subtracted the ion energy. We have subtracted the range. Range is how much your ion is going inside your target material in which you are working on. Suppose we have calculated this oxygen in silicon or something. So how much this oxygen is going into silicon, that is called the range. Average distance it travels. Okay, so we have, since we want to know how your ion is losing energy with death, that is why we have subtracted the highest range from the range table.
Right.
So how much is finished, sir? How much more you want?
SRIM is completed. So
okay.
Now we can go to trim portion.
Okay, so it is already 12:47. So would you like be able to finish in 10 minutes?
Actually, we have to finish because if we actually calculate for 10,000 ions or so, then it will take long. So I will just show you.
Just give a simple example so that they can be able to run on it on their computer.
Yes. By the way, when you run SRIM, then we get many. The trim. If we run trim, then we get many files which give different types of information. So the outputs are available in these type of files. So let us see how we calculate this type of graph from trim. Okay, so here in this example, 190 kV phosphorus is implanted in silicon, and our interest is to see how it is these implanted phosphorus ions are distributed depth-wise in the silicon. Okay, so we'll go to main menu, and from there we can select trim this time. Okay, after that we have to select the ion. Ion is phosphorus here, and energy is 190 kV. Incident angle is 0. Okay, and after that the layer is silicon. This name I have just written for my information. And depth we can choose as 3500 angstrom, 3500. After that we have to specify what is the element in the target. Our element is silicon. And then if you want just ion ranges, then we can select ion distribution and quick calculation of damage. That is good enough for ion ranges. But if you want to calculate damages in the material, like displacements, vacancies, for that we have to select detailed calculation with full damage cascade. Okay, for this example, ion distribution and quick calculation can be chosen. After all this, we can specify after how many ions the file should be saved. Usually people run for 10,000 at least. So 10,000 we can put here. Total number of ions which can be simulated is given here, and help is available here. What is the maximum you can put, all those things. And for display, what is the depth window you want, that we can specify. Here it is written which SRIM stopping power version is used. After that, we can select which output files we want to save on our computer. Let us say we want ion range. Then after that, we press save input and run trim. So everything we have already input, so we can press here. Okay, so now it has started calculating. It has, you can see at the top, 55, 56 ions have been simulated. This window gives you about ion information about ion. Then here plot windows, and from here we can choose which plots we want. This is XY window. X is along the ion direction, and Y is perpendicular. Y and Z are perpendicular planes. So XY, in XY plane we can see this is the distribution. So all the trajectories are projected on this plane. So this is how it looks like this. So this is the graph we were already referring to. So from here we can see that ion range is average ion range is 2.392. I think it is not visible here. Ion range is 237 nanometer with a straggling of 66 nanometer, and other higher moments are mentioned here. This defines how the peaks look like. Okay. Yesterday, Professor Hofstede also told you what is the meaning of different values displayed in this window. Like he told you what about the ranges. So range can be three types: longitudinal means along the depth, lateral means perpendicular to that, and radial means square root of these two. Sorry, squares of these two. Then here you can see what is the percentage of energy lost for ionization and for vacancy production and phonons. So our energy was 190 kV. So if you go to this window, then from you can sum up these two, 45 plus 16. So this is roughly 60, 61, 62. 62% of energy is going for ionization. And for vacancy, this is the percentage which is going for vacancy creation and phonons. Phonons means for thermal vibration. So this is the portion which is going to heat up your sample. Then there is also sputtering yield, but this is not available with quick calculation. Last one is random number, because this is Monte Carlo based, so there are many random numbers which are required to calculate the trajectory. So the present number is being displayed over there. Then there are some of the files which you can save, and some of the graphs which you can visualize right now. I think we can take some questions because we are running short of time also. So Paramita is asking, if it is 100 MeV incident ion at the surface, then ion will gradually lose its energy with depth of the material. To match the energy corresponding to the depth, we need to subtract reverse depth. Correct. I think this was a comment. Now Paramita is asking another question, that when we have higher energy, then the calculation is very slow. So how we can solve this problem? I think this program is not cannot be run in parallel mode, but sdtrim.sp, which Professor Hofs has told us last time and yesterday, that can be run on parallel machine. So if we use that, I think it will be faster. But personally, I haven't used it, so I cannot comment. But she is right. When we increase energy, then this is very slow. Paramita? Paramita? Would you like to show us how to calculate similar type of depth profile for some other ion? Okay. So if somebody wants to volunteer, he or she is most welcome.
No answer from participants, I suppose.
Okay. So what should we do, sir?
You can, I think you can summarize.
I think they have understood, no?
Hopefully. you can summarize and I think close the session.
Okay.
Whoever is interested, they can.
Yes.
Hello. Hello, sir.
Yes. Sir. Do you want to say something?
Yes. I want to calculate in an Python trim software.
Sorry, can you repeat, please?
I want to calculate it on trim software.
Okay. Please go ahead.
I have to present my screen.
Correct. I have stopped my sharing.
Okay. Is it visible now, sir?
Yes.
So, for what I have to calculate? Please.
Let us go by the same example, 190 kV phosphorus in silicon, but this time we'll perform detailed calculation so that we get vacancy distribution also.
190 kV phosphorus. 190 kV, na, sir?
Yes, sir. Incidence angle is okay. But only thing you have to change in the first drop down where it is written damage, no, that you can change from ion distribution to detailed distribution, detailed calculation.
I have to add here, no?
Yes, that also you can add.
Phosphorus,
this is regarding the target. So target is silicon.
Nothing I have to change in this one.
And layer width you can change.
What is this one?
Let us use 4000 angstrom. 4000 or 4500. Let us take 4500.
Substrate thickness, no?
Yes, this is the layer thickness.
Okay. I have used 4000.
Okay.
Then I have to calculate.
Detailed calculation.
Detailed calculation with full damage cascades.
Yes, correct. I think now we can go and click save input and run frame.
Okay, sir.
Okay, we have already seen how to visualize ion distribution. Now let us see what is the depth distribution of vacancies. So you can select, I think, from damage distribution, damage events. There is a checkbox on the left side, bottom side.
Okay, sir. Damage events.
Select damage events. From there you take silicon atom target vacancies.
This one.
Actually, this is single target, a single element target. So if you take total vacancies, it will be the same as silicon atom target vacancy.
So I can choose this one or fourth one?
You can select vacancy one. Actually, displacement means some displacement has happened, but those displacements can be filled by some incident ion or nearby atoms. So some of the displacements are refilled. So these are called replacement. So whatever is left is called vacancies. So vacancies are actually the damages.
So I am choosing for
yes.
Then
show plot.
Show plot number 4. I can save this also.
You can save as and also you can print. And if you click on the box next to damage event, no, there you can save the file also. There is a another box left to that one.
This one?
Yes, engrossed one. Yes, that one. If you click there, no, then you can save the file also.
This whole file will be saved.
It will save in the SRIM output directory, and its name will be, I think.
Can I see there from there? I think this one, vacancy one.
Correct, correct.
Okay. From this data we can plot in horizontal.
Yes.
Okay. Thank you.
And if you go back to that plot, vacancy distribution plot.
Yes, sir.
If you want to know what is the displacement per atom, no, that also you can calculate. Let us see what is the value at the peak. This is 1.2 number per angstrom per ion, right? So this value, if you divide by the density, atomic density of the material, atomic density of silicon is I think 5 into 10 to power 22 atoms per centimeter cube. Okay, so 1.2 is divided by 5 into 10 to power 22 and then multiplied with the fluence. So at that phase, what is the displacement per atom? That number you can get from this.
The number of displaced, number of atoms displaced.
Displaced per atom. Per atom means in the material there are atoms, no? So how many times that atom has been displaced? So this is what it is. So suppose you the criteria is that one displacement per atom should occur for amorphization, then we have to find out what is the fluence for which the number comes out to be 1 dPa. So I think you understood how to calculate dPa. This number you have to multiply with fluence and divide by atomic density of the material.
Yes, sir. This number divided by density of the material into fluence.
Yes, and because this is in angstrom, so we have to multiply by 10 to the power 8 also.
Okay.
Because I think density you will be putting in per centimeter cube.
Okay,
And
according
fluence
to
will
that,
also.
Units.
Correct.
Okay.
Sir, I think we should close.
Yeah,
Otherwise,
I
the
think
next
we have
session will
covered
be
many
late.
things, I think.
Yeah. So anything else you want to say?
I think they should practice. That is how they will come to know more features about this program. And if there is any question, we can help them.
Contact you by email.
Yes.
Okay, sir. Thank you. Thank you for taking out your time and giving this 1 hour practice to all the participants. And
I
we'll
hope
close this
that,
and meet at 1:55, 1:50 around. Okay.
Okay, sir. Okay, sir. Thank you. Thank you. Thanks everybody for joining this hands-on session. हाँ
So, sir, it is over. Any question from the audience? Okay, thank you all. See you in the next session.
Hi. Hi. Nice to see you.
Nice to see you. And
yeah. Thank you for accepting the talk in short time and making it possible.
Thank you for your invitation. It's
yes,
a great pleasure.
Yes, yes. Yeah, it's fine. Maybe you can make it full screen.
Hello, Dr.
Yes.
Asoka, can you see
Yes.
my screen?
Yeah, maybe you can make it full screen.
It's a full screen already?
No.
Okay, I will try.
Yeah, yes.
Yeah.
I think in your computer itself you make full screen, then you make present, then it will come.
It's the full screen already?
Yeah, wait. Yes, it is full screen now.
Yeah, okay.
Yeah.
Great.
Okay. So we'll wait for some more time. So let the number increase to 40, 45, then we'll start. So Dr. Avasi will be introducing you. So he'll also join maybe another 5 minutes. Okay.
Yeah, okay. And yeah, I have another question. It's in the conference. Yeah, it's the program already signed out.
Conference, yeah, it is getting ready. Maybe tomorrow it will be available. Tomorrow or maybe Saturday we will send it.
Because yeah, I'm not sure how much adjustment I need. I have another meeting, and next let me check because next next Monday I have one meeting. Next Thursday also a meeting. Yeah, so the best could be Tuesday at this moment.
So you also send invited talk you in a conference?
Yeah, I think I remember it is. So because maybe I should check the email.
Maybe you can just drop an email mentioning that you are available. I think that will be good.
Okay. Yeah.
Dr. Avasi has joined, so maybe we'll wait for another.
Hi, Shengqiang. How are you? This is Tabo.
Yeah, hello. Tabo, thank you for your invitation, and I'm fine now. So
yeah. Nice to see you.
Okay, because I'm presenting the full screen, I cannot see it. Okay, I can move a little. Yeah.
Well, good afternoon to all of you. This is Devesh here. Welcome, Dr. Zhou. Marcel Tuleman, nice to see you. And Dr. Som.
Thank you.
So, Ashokan, how long, I mean, when do we start? I mean, how much do we see that?
Just wait for a few more minutes. Let other people also join. So, because we completed the morning session around 1:10, so people may take some time. And we have sufficient buffer time, so another 10 minutes we can wait also, but we'll try to start early.
So good afternoon to Dr. Wan Khan also. And Dr. Zhou, you are currently in Dresden?
Shengqiang, the question is for you, whether you are still in Dresden or not.
Yes, I'm
Okay.
in Dresden. You see my office,
Okay.
I think.
Okay. All right.
Marcel, good afternoon.
Yeah. So it is very nice to see you, Marcel. Yeah. Okay.
Okay. Hello to everybody.
Oh, yeah. Great to hear from you. Yeah.
Yes.
Hello.
Sorry, but I will cut my micro because there will be some noise around, so I don't want to disturb.
Yeah.
So
when it starts, then you can switch off at that time.
Yeah. I will do that.
Yeah. So when you plan to come next time to India? Yeah? Waiting for
when you
pandemic
want,
to be over?
when you want, if I am in a good shape.
Okay. You are in good shape. Yes. Yeah.
Wow. Not so. That's it. We have to be careful, whatever it is.
Yeah. Right. So we all have to be careful with the pandemic.
Yeah, this is a big problem for me.
But now the info it's going to start already next week in UK.
Okay. Yes. They did not finish a test.
I think vaccination will start in US also very soon. So things should get in control fast. And
Just waiting for Ambush to join. Once Ambush joins,
sure. Maybe 2 minutes more. We have already 54%. So this is a good number. Marcel, just for your information, I have changed my coordinates. Now I am I have joined as a Dean R&D in UPES, University of Petroleum and Energy Studies in Dehradun. It's a capital city of one of the state called Uttarakhand. So,
okay. Please send me your new email address, please.
Yeah, I will send. And although I'll be 3 weeks in a month, I will be in Delhi, and 1 week I will be in Dehradun. So that is the deal. And it's a nice place. So when you come next, so that is your next destination. Yeah.
No. I begin to be. Well, okay, we will see. Whatever.
Yeah.
Sorry, but now we have to be careful, whatever it is.
Yeah. So my invitation is to other colleagues also, Dr. Zhou and Dr. Wankan, whenever coming to India, so you are welcome to visit Dehradun. Is a nice city, and we have very active research groups. IBM is a small group, but then very interesting areas we are working on, including plastic to energy is one of the hot areas there, converting polymers, waste plastics into energy, creating oil from it. And we have gone into the pilot scale. That means not only research lab only, but there is a pilot plant for that. And we are interacting with industries to take up such things. So it's very challenging, very interesting. So
thank you for your invitation, Devesh.
Thank you.
We will see how things will go on.
Yeah.
Sure. Yeah. So, Dr. Awasthi?
Yeah.
Should I meet you in Delhi?
Delhi and Dehradun. When you come to Delhi, you must come to Dehradun.
Sure.
So you are more than welcome.
Thank you.
Yeah. But most of the time in Delhi. So I joined there in September, but I am yet to go there because they are saying that you stay there only, and when the situation is better, then you come. So mostly it is online meetings and online coordinations are going on.
Yeah, in these days, that is the best mode.
So next 10 days or 15 days, I am planning to go there because it is slightly getting better.
Correct. So, Shengqiang, is this already freezing in Rossendorf?
It's today, this morning it was, I think it's somehow the first snow of this year.
Oh, I guess rightly.
Yeah, so in principle.
No, yes.
So I think in France, not yet.
No, in the mountain, yes.
I see white road.
Not where I am.
Yeah. Okay.
You are close to building number 13. Is this now?
Sorry?
The view you showed us, that is outside building number 13?
No. I'm in a new building, and no, this just outside is a small forest, and further outside it's this number 7. It was
okay.
Yeah,
Got it. Yeah. Looks like near that same place. Yeah.
I'm in a new office in a new building. The lab is still there at the original place.
Yeah. Okay.
Yeah.
That's the basement one, correct? That you took me last time.
Yeah.
So, Dr. Ashokan, I wait for your signal to start.
I think now you can start.
You can start.
So, having some other work. Yeah.
Well,
you can introduce the speaker. Yeah.
Very good afternoon to all of you, and warm welcome to this afternoon session, and especially Dr. Zhou and other esteemed senior persons, Dr. Suleiman and Dr. Taranga. And so this in this session, we have three lectures, and first lecture is by Dr. Shengqiang Zhou. He is currently at Institute of Ion Beam Physics Material Research, Helmholtz-Zentrum, Dresden-Rossendorf, and speaking on pushing the doping limit for future FETs, a very important topic and very exciting. And although he is known, I would like to, for the young researchers, like to say something about him. So he had his MSc degree from Peking University in 2002, and then he did his doctorate from Technical University Dresden Research Center in 2007, and during that time he has been at University of Leuven, Belgium also. And then his thesis problem was correlation between structure and magnetism in transition metal implanted ZNO. And subsequently, then he had postdoctoral positions at Rossendorf, and he got a position of research professor in Peking University in 2010, and then he got Helmholtz Young Investigators, and he was a group leader at Helmholtz-Zentrum Dresden-Rossendorf from 2011 to 2016. And after that, he became group leader in Helmholtz-Zentrum Dresden. And and currently, he is department head of semiconductor materials, Helmholtz-Zentrum Dresden-Rossendorf. And there are awards also to his credit. He got IBMM prize at the 18th International Conference on ion beam modification of materials, which is a very prestigious conference for ion beam in materials, especially dealing with the materials modification. So with this brief introduction of Dr. Shengqiang Zhou, I'd like to request him to proceed for his lecture. And may I request others to mute their mics? Yeah. Okay. Thank you.
Okay. Thank you, Dr. Avesti, and for your kind introduction. And for me, it's a very great pleasure to present some result, also my point of view of about the ion implantation in semiconductor application. And it's my great pleasure to see many friends. And we, in the past years, we meet in conference. Also, some of we meet in Dresden-Rossendorf. Yeah. So I will start my presentation, and it's the topic is how to use how to push. Let me say why we increasing or pushing the doping limit for future microelectronics for field effect transistor. Yeah. So before my introduction, the scientific part, I want to basically for the young researcher, I want to introduce you about where I'm working. It's in Dresden. It's a city in the east part of Germany, and so it was a very beautiful place, and it's to call it the Florence on the Elbe River. So I hope the epidemic will go away soon, and you are all welcome and to visit the city. And meanwhile, you can, of course, welcome to visit our research center. So, and compare with the inter-university accelerator center in India, our ion beam center basically focus on the a little bit low energy range. And as you can see from this map, we have basically 3 MeV tandem accelerator. And the maximum energy we can go if you use highly charged ions, go to it's below 100 MeV. Yeah, and basically for semiconductor and for the ion implantation, we mainly concentrate on low energy ion implanter. You see, we have from low energy implanter, the lowest energy it's around several hundred electron volts, and then go to the highest go to 500 keV. Yeah, and of course the high energy accelerator also used for high energy implantation for basically for power electronics. Yeah, so that is the ion beam center, the map of the center, and you see it's basically 3 accelerator. They are altogether around 20 to 30 beam lines, and it's worth to point out. It's actually, since we are belong to a Helmholtz association, so basically it's an international user facility. So for all the research, I mean from all over the world, one can apply for beam time and perform your experiment here. And also include also you see RBS and ERDA and nuclear reaction analysis. Yeah, so in my group, basically we are focusing on semiconductors, and on one hand, we are trying to dope semiconductor go to very high concentration. That's what I'm going to discuss about for today. And on the other hand, after we got those after we get those highly doped semiconductor, and we want to use them for instance, for infrared electronics, optoelectronics. Yeah. Meanwhile, and we also use the defects created by ions in semiconductors, basically wide bandgap semiconductors like silicon carbide. And with these defects, some of the defects carry a spin and also can be a single photo emitter. So now it's we can use them for quantum technology. So to realize this doping and to go to above the solubility limits and to avoid diffusion, at the same time we are also working on annealing technology, like to use flash lamp and also pulse laser. So you know, flash lamp something like it's a white light and like the flash in the sky, and it's the duration, it's in milliseconds, one can control down to milliseconds. So it's around 1,000 times shorter, faster than rapid thermal annealing. And for pulse laser annealing, we can go to use milliseconds or go to nanoseconds. Yeah. Okay, that's the topic we are working on, and that's the method. I mean, besides the ion beam center in our group, we are basically have this processing method using laser or flash lamp, and then we measure the low temperature magnetic or transport property and also optical properties. Yeah. So of course, all this we are very welcome for cooperation. Yeah, so that's a short introduction about where I'm working and also what I'm doing in our whole group. And now we come to the main topic of today. So I try to divide the discussion in two parts. One is in general about implantation for doping, and it's very basically it's very fundamental or very basic knowledge or information, and I hope this is not so boring for the experienced researcher here, but it's basically for beginner. Then half of the time will be, for instance, for the future or now, what the technology requirement and what are the challenges and how we can try to tackle these challenges. Yeah. Okay. So for doping semiconductor, I think we comes back around 100 years ago, actually from Wolfgang Pauli. We all know this guy from quantum mechanics, and you know him he had a very big mistake, and he said one shouldn't work on semiconductor. That's a mess. Who knows if they really exist? And of course, from a theoretician, he think if for pure semiconductor, so they are at 0 Kelvin, so they are insulated. Or if you have impurities, then they are not pure material anymore. So in his point of view, semiconductor will not have future. However, we know if we dope semiconductor, so what is doping? And mostly we know, I mean, from the inject a little bit something, and you can improve the performance. So that's actually exactly the analogy of semiconductor, but we are doing this in a legal way. And basically it's to introduce controllable amounts of impurity into semiconductor. Then we can very scale and modify and control the electronic property of semiconductor. So of course also can control the optical and magnetic property that's found out in the last decades. Yeah, so I mean the key message is if we put controllable amount of impurity, you can have the, for instance, the resistance change of over several order of magnitude. So that is not for metal. So for doping, basically there are two different methods. One is diffusion, and it was the predominant method until 40 years ago, 80s, in 1980s. And ion implantation become more and more popular after 1980s, and it's actually used continuously in our information technology. So yeah, for doping, if for diffusion, and when you have to think about the transport phenomenon, and the diffusion, you will always have a profile because of the nature. And if we do it at a high temperature, the dopant also can be redistributed. Yeah, for ion implantation, some phenomena we have to take concern. It's you use ion implantation, you have a profile of your impurity, and you have to know the ions how they stop inside your matrix, and how what's the consequence to your crystalline material, basically the lattice damage. And in order to remove lattice damage, we work on annealing. And there also we have to keep in mind, it's for single crystal samples, you can have channeling effect, and sometimes it's positive. And in order to have unified profile, you have to think about multiple energy implantation. And more challenging, it's for very shallow implantation or very deep implantation. So that is some issue related with these two technology. And so yeah, like we say, elastic way, it's for diffusion, one can basically work at high temperature, and you have a source, and the ions, the impurity, diffuse inside. And if the source is constant, so it's at the surface, and you have highest concentration, then dramatically decrease when it goes too deep. That's generally the profile. And for ion implantation, you can determine the depth by energy. You can determine the concentration by the dose, by the influence. So that's we can decide the profile. And one of these advantages is what you can see here for diffusion, since it works generally at high temperature. Even you have a mask, you want only have a doping here, but you always have diffusion in the lateral, and you don't have a sharp interface. For ion implantation, of course, we know from the basic the interaction between ion, you also have lateral straggling, but the effect is much reduced compared with diffusion. So that's the basic idea about ion implantation. And for doping semiconductors, it is actually, as I said, become predominant since the 1980s, and it meets the requirement for small feature size microelectronics. We can have mask and to produce very small structure to have lateral and locally implantation. So basically, it's the introduction of a charged energetic particle into substrate. The energy can be keV to MeV or even higher tens of MeV. Then the ion distribution, the impurity distribution, can be varied between nanometer and meter. So the dose, it's also can be varied somehow between 10 times to 12 or 10, and to 18. So it's go to very high. So that means this is much below 1%. This is much above 1%. So it goes to varied by 10 order of magnitude. And here we have to keep in mind, it's to go to very low dose, it's challenging. Of course, go to very high, also challenging. So basically here is what we are going to talk about. And the main advantage is you have flexibility in dopant species, and you can choose from the element table any element into almost to any substrate. And you can control the spatial location, and you have more precise control and reproducibility of the doping profile. So, and it can be done at low temperature. So the drawback is you have to make two steps. So first implant, then you have to anneal and to repair the lattice and to move the impurity into the substitutional place. So yeah, and afterwards, you know, since the 1980s, implantation actually becomes a very, I mean, it's one of the key technology in the chip production. So here is an example for of a transistor, and you can see how many steps, how many place the implantation is involved. For instance, in channel, you have implantation, and you have also super steep in the channel, another implantation, and in the source or drain implantation, you also to produce a deep well implantation, and also the pocket, and yeah, many place. So it's a kind of unavoidable method in IC production, and it's a very high throughput. Actually, the production is very fast and in the clean room. And so here it's a summary about the application of ion in different range in the IC production. For instance, of course, here for SOI, it's not so popular anymore, but it was used in 90s, in last century. And now, of course, you will probably you have heard the talk from the colleague in France. You have smart card, and yeah, here is the smart card. For instance, to have cutting silicon on insulator, and yeah, depend on the dose. With dose, it goes to lower. And for instance, for the SE contact, you need high dose and generally low energy. And for the channel, you need generally relatively low dose. And for CCD, for instance, or power electronics, you need high energy. So this gives us a summary. And for different application, you need different ion fluence and energy. Yeah, and another very important advantage of ion implantation is the isotope selectivity. So if we use the mass spectrometer, you can select down to with the resolution to select different isotopes. You know, this is very important for quantum technology. If you want to implant, for instance, phosphor 30 to silicon 28, so by MBE you will not get it because of the you don't have, if you want to have isotope poor targets, then the cost is very high. But for ion implantation, what you can see here, it's very easy to achieve. So remember this, and in the future, I think for using ion implantation for quantum technology, this is a big advantage here. So as I said, after the ion implanted, you need to see what's the consequence and in the wafer, and how to basically the most of the important next step is subsequent damage and to move dopant into lattice side and to become active. So you already know, for generally, if you have high energy, you have light ions, you produce generally less damage, but heavy ions, you produce more damage. You can introduce amorphization. So, and here gives actually an idea how the amorphization happens. For instance, this is silicon, 300 keV silicon implanted into silicon, and to produce amorphization. You see here it's TM result, and here you see the contrast, and below it's a single crystalline, and with increase the dose, the top layer, you see the implanted layer become less contrast, it's amorphous. So this is basically almost the full amorphization happened around 2 times 10 to 15 square centimeter, because around this dose and the top layer is fully amorphized. So let's give you an idea how the amorphous happen. So now the question is, so we need annealing to activate the dopants. And the question is at which temperature, how? So it's already a very well developed technology. It's solid phase architectural rigorous, and since we implant to top from the top, only the surface is damaged. So below it's still single crystalline silicon. And if we warm up a little bit, basically to something like the half of the melting temperature, generally you already can start the recrystallization. For instance, for silicon, if one do it at around 500 degrees C, you already can start to grow. So the underlayer at the template, because it's still single crystalline interface, it's grow layer by layer. So yeah, here it's basically from the past summarize for if you want to anneal or recrystallize implanted silicon, when depend on the dopant, the temperature, the needed temperature is also different, because if they also change the melting point. For instance, if the doping goes to very high concentration, something like phosphor goes to a higher dose, and you don't need so high temperature. And basically what you can see, it's somehow 700, 800 degrees C, you anneal for 30 minutes. It's somehow enough to recrystallize this several hundred nanometer. Yeah, one can use also rapid thermal annealing from something like 100 seconds. And of course, it should add a little bit higher temperature. Yeah, and here give you a visualization what it means. This solid phase epitaxy. This is an implanted layer. You see this the impurity, and the surface is damaged, and you have a crystalline interface. And when you warm up, so it starts. The atom will find its best place with the lowest energy, and one of the impurity is trapped in the substitution site. So with time, and it's layer by layer, and it grows to almost single crystalline, and you have the impurity randomly and homogeneously distributed inside your matrix, so that they can active as dopants. So in experiments, this is how it was done for fully amorphous silicon. If you anneal at 525 degrees C, and 5 minutes, you see it from it's still amorphous, but it starts to grow. And 10 minutes, you see the interface moves up. And 15 minutes, it moves up again. And around 20 minutes, it's fully recrystallized. So that's actually the visualization of the annealing procedure. So we can use, after implantation, we can use thermal annealing, like either furnace or rapid thermal annealing, and to repair. And another consequence for after the annealing is the redistribution. What you see here, for after implantation, it's a kind of Gaussian-like distribution, but after annealing, it can diffuse. So that's we should keep in mind, because this will influence, of course, the application. So basically, the distribution will become broader. So depend, of course, on the temperature and because on the time. Yeah, temperature will decide this diffusion coefficient. So that's another consequence of for the general annealing. Of course, I will ask you how to avoid or how to minimize the diffusion. So think about that. And so far we are talking about elementary semiconductor, basically for silicon or germanium. So just think about, I give you these questions for compound semiconductor, like gallium arsenide or gallium nitride. And what's the difference here? So, and what could be the further problem? And when you anneal this. So this I would like to leave it for you to think about this. And maybe you already have the problem, and or And also for the annealing, what I mean to be taken into caution. Of course, I'm also happy to, if you have more questions from your research, I'm happy to answer or by email or after the lecture. Yeah, okay, so that's very basic knowledge about the implantation and annealing. And for more, of course, you also always can read the books already published in the last decades. And now comes to the new challenge for doping for the future or for now, the very small structure. So what are the requirements? So we know it must be small. Now it's we go to you see it's maybe the mainstream it's 7 nanometer already, and the next year you will have 5 or 3 nanometer. So the structure become more and more small, and you know, if it's small, then in order to have dopants in each transistor, that means you have to have higher doping concentration. And since it's small, then you have to limit the diffusion, because otherwise, if it's after your processing, when you want to have ultra-shallow junction, something like 10 nanometer, but after annealing, you have 30 nanometer junction. So then the junction already bad. So what are the challenges? So the challenge is to introduce so high concentration and to keep them there. So to fix them in the position you want. So, and they should be active, of course, should be in the substitutional side. So that's the requirement under the challenge. Okay, and from industry, actually this has been such a challenge already being arise, and also in the continuous discussion. And so what I'm talking about, if the gate length, and you want to have smaller, because and the smaller, that means you should have the smaller structure we talk about, and the channel also and the resistance, we want to have lower resistance. So and also in the contact area. So and for the junction depth, we want to have for shallower. So we want to have for avoid to minimize the diffusion. And you know, when you have for shallower, basically the resistance will be higher, but the requirement we want to have for lower resistance. Otherwise, you will have heating and you will have many parasitic effects. So actually, this is the driven, and to have high speed, you want to have the currents on and current saturation to increase, and the resistance should decrease. So you need high dose implantation. You need high annealing temperature in order to keep them active. And if you want to reduce the leakage current, and you the junction depth to decrease, and you need lower implantation energy, and you know, the higher annealing temperature it's a contradict here, because higher temperature means more diffusion. So in order to overcome, one try to have shorter annealing time. So that's the challenge and the possible solution. So basically, and for this purpose, and the parameter to change, it's what we have at hand. It's we can increase the dose, increase the fluence to have high concentration. So we can try to reduce the annealing time. You know, for rapid thermal annealing, we have a second. If we can go below. So the difficulty, of course, the technology, we have to overcome those to have, and also something is, for instance, the diffusion. It's naturally decided already for the diffusion coefficient at particular temperature. So also the solubility limits, for instance. Okay, it was efficiently solved to reduce, to confine, to have a shallow junction, when by co-implantation, when it's an AMAC and an applied material. carbon and with boron or fluoride. With this, you see with co-implantation, you can use this dopants to block, basically use the co-dopant for the carbon to increase the to block the diffusion and to increase the abruptness. So this is using carbon co-implants and using short time. This is spike annealing in seconds, and you can have relatively good shallow junction. To further reduce the time, so here I give you a scheme about the time for the annealing, for rapid thermal annealing. Basically, the mainstream in industry, it's like this. You see, in the first 20-30 seconds, you pre-warm up to several hundred degrees, and in few seconds you go short to something like 1000 for silicon. And by this, now you're cooling down also very fast, so you reduce the diffusion, and basically you have keep at high temperature only several seconds, and to allow the allow the repairing of the lattice. And this is in second scale. For flash lamp, what do you see here? This is the seconds, and here this is the amplifier of this peak. You also need to pre-warm by second, and then you have a very big shot in somehow 30-20 milliseconds, and you go to more than much above, I mean nearly the melting temperature, so much above the rapid thermal annealing. So that means we again reduce the time for diffusion and again increase the temperature, and to minimize the redistribution, maximize the activation. Yeah, how it looks like of the flash lamp annealing, and basically it's you have external lamp on top, and this is the energy and provider. Basically, the flash comes from here, and you have your wafer, and below we have a halogen lamp to pre-warm up, and from the backside of the wafer, and this will pre-warm up within several seconds, goes to several hundred degrees C. Then we apply flash from the top, and goes to more than 1000 degrees C. So that's how it looks like in reality. And we can also at the same time have nitrogen flow or argon flow, depending on our needs. We don't have vacuum yet. Okay, here give you examples. For instance, the implants, boron implanted into silicon, and as implanted, we want to have a shallow junction, like 10 below 20 nanometer. You see after basically rapid thermal annealing in seconds, at 1000 you see the diffusion, and 1500 degrees C you see the diffusion even much more. So we don't have a shallow junction, you have a junction of 40 nanometer, 30 nanometer. And here is the annealing by flash. If we go to above, you see the temperature is higher, 1200 or 1300 degrees C, and the scale is different here. Here you see this is as implanted, and this is the after annealing. You see the diffusion compared with the spike annealing, it's much reduced. So we can somehow create an ultra shallow junction by this reducing annealing time. So that's actually the example from applied material, and this is as implanted, the black one, and you see after millisecond annealing, we have already have the very good activation, something like 500 ohm per square, and you have more or less the same profile of your implantation profile. So basically there's no diffusion. This is a spike annealing at lower temperature. So because it's very thick, you see, and the junction comes to diffuse to 30 nanometer. So it's become thick. That's why even it has a relatively smaller resistance, but if you consider the thickness, and here you have much smaller resistivity. So with to produce ultra shallow junction, we can either try, for instance, one solution is a co-implant, for instance, to block the diffusion, and or you use a very short time and we reduce from second to millisecond or even to nanosecond. So we can somehow already solve the problem. So the second challenge is go to very high concentration. So up to, let me say, %. You see, this is it's go to 10 times 10 to 21. It's a few percent of the impurity. So what is the challenge here? And you see, it's as I said, for the further device. This is a talk this year from IMAC, and we further minimize the device if you have 753 nanometer, and at least if we think about one carrier in each transistor, somehow to estimate, you see if 1 over nanometer cubic is already 10 times 10 to 21 per cubic centimeter. So that's the doping concentration we need. And also, you know, from previous at when it's above 22 nanometer, and we have planar transistor, and now we have thin FET, and in the future we will have gate all around, and all these we have what we need. It's the source and the drain resistance should be smaller, and this all require a higher doping concentration. So when here is a summary, like from planar to gate all around, and you have we need, and the problem is you have additional reduction in contact area. The contact area becomes smaller. If the doping concentration is the same as before, that means the resistance is large. So we won't have we don't want large resistance. So even the contact area is smaller. So that means we have to dope it higher. So yeah, because of this, you see the contact area reduce and the series resistance increase, and we have to avoid this. We have to minimize this effect. So need for additional material research to increase the doping concentration and to reduce the source and drain resistance. So we see, I mean, the physical problem probably is not so serious, and because the solubility limit, what you see here, for instance, for phosphor or boron or arsenic, you see here, it's actually in the range of 10 times 10 to 21. So it's quite high. If we go to higher temperature. So in principle, we could achieve this, such a doping concentration, and at the same time, we want, of course, have the same activation concentration. So there was a lot of effort in the industry, also in research, in the last, very recently, and to grow phosphor doped silicon. It's possible. You see, by reduce the pressure chemical vapor deposition. This is a paper published last year, actually, South Korea group. And you see the phosphor concentration from 2% even to 6%. And also from the X-ray diffraction, you see the incorporation of phosphor introduce a lattice contraction. The lattice parameter becomes smaller, and this is the highly doped phosphor high doped silicon layer. And with the doping concentration, it's the contraction become more and more, and it has a proportional distribution dependence. The lattice parameter reduce with increasing phosphor concentration. So, and by SIMS, I also can measure the concentration. You see it really go above 10 to 21 per cubic centimeter. And the crystal quality you also can see here, it's not bad. However, you see, if we measure, we won't have a higher electron concentration here. And here it's the phosphor concentration. You see this the XX, it's goes to 3 times 10 to 21. But the carrier concentration, what we hope is to have this 1.1, this dashed line. But what we have is the blue line, the blue symbols, the carrier concentration. So you see the phosphor is inside, but they are dead. Basically, the carrier concentration is much below the doping concentration. So there was also a lot of effort to try to solve this. And the two popular method, it's so-called millisecond laser annealing. So also like a flash lamp annealing, but it's a millisecond laser and developed by Applied Materials, and they call it DSA, Dynamic Surface Annealing System. And this is as grow without annealing. The blue one is as grow without annealing. The red one it's after annealing. You see the carrier concentration. It's really increased, but still after some value. So this is grown by PECVD grown phosphor doped silicon, and after the crystal quality is good, but the carrier concentration is lower, and after millisecond annealing, one can increase, but still you have saturation here. And in the same group, they also try nanosecond annealing. And here it's the energy density of the pulse laser, and this is the melting depth. You see at this energy, something like 602 millijoule per square centimeter, you start to melt, and at this around the depth, and if even higher, you over melt. And by SIMS, you measure the phosphor concentration. You see if it's over melt, you have diffusion. But if you don't over melt, and only partially melt, you don't have redistribution. But it's the redistribution is not so much here. And they also measure the carrier concentration depending on the power of the laser. And this you have a lot of data here. It's a different phosphor concentration. And you see at this energy density 600, so it's not fully melt, and you can somehow overcome this millisecond laser annealing. And with this nanosecond, you can go a little bit higher, but not so much. So you have somehow a saturation, and most of the carrier are basically dead. Most of the impurity are dead, and you have much lower carrier concentration than the impurity concentration. So that's that. Here in previous, what I show is a work done in South Korea, and in Europe, in IUAC, they also worked a lot, and with phosphor doped silicon goes to several percent, 5%, and this is as grow, and the resistance, you see it's large, and if you use the millisecond laser annealing, and one can reduce the resistance by around 2 times, I would say. So from around 0.6 milliohm and down to 0.2, and but also saturate at this temperature, at this concentration. So yeah, you can by annealing time and to increase activation concentration. Here at the grow, and with after annealing, you see the carrier activation concentration is increased, and but still below the impurity concentration. Yeah, and here it's also the work done in IUAC. Actually, by this, they use either spike annealing or millisecond laser annealing. Also use excitement laser annealing, and to check if there's diffusion. And you see by laser annealing there is a little diffusion, and also to check the crystal quality, also the lattice relaxation. So, and here is the resistance. What you can see at the grow, and it's higher, and by some processing, second annealing or millisecond annealing or nanosecond annealing, you can reduce the resistance. So by, let me say, the lowest by examine laser annealing will get something like 0.15 milliohm centimeter. So that's the challenge. That's how in the industry or in the research community try to solve it. So I told you, I said there always a problem. Even the impurity concentration is higher, but you cannot increase the carrier concentration anymore at very high concentration. So what's the physics behind? And actually, it's find out when the impurity concentration is higher, the impurity also becomes more and more nearby and close to each other. And if they form such a impurity vacancy complex, then the impurity are dead. So you see, if you form this phosphor 4, I mean, one vacancy trapped around 4 phosphor, then these 4 phosphor are dead. So, and this has been actually identified by positron annihilation method and another kind of nuclear method. One see the lifetime, and also this is S parameter. I mean, from here you don't. I will not explain in detail, but it's what I want to show. It's the after at the grow you have large S parameter. After annealing you have reduced, I mean smaller S parameter. That means the defects, the vacancy is reduced, but you still have some amount. So this is the killer of the impurity. And if we have such a situation, for instance, silicon, around silicon you have 4 phosphor, it's no problem. But if you have a vacancy and 4 phosphor, then these 4 phosphor are dead. So that's the physical problem at higher doping concentration. So how to remove this vacancy, it's the goal. What I talk about is for silicon. Basically, this is how to remove it. It's ongoing. I mean, it's not yet solved completely. And besides silicon, germanium is another very attractive material because it has higher mobility. So indeed, phosphor doping in germanium has a similar problem. If you have for instance here, it's to increase the phosphor concentration by tuning different growth parameter. You have the chemical phosphor concentration. It also can go to almost 10 to 21, 10 times 10 to 21. But the active phosphor concentration also saturate, and they will grow at very low temperature, and you can have high concentration phosphor, but you cannot have higher electron concentration. So actually, it is the same problem due to the vacancy. The vacancy impurity complex is the killer. So here in the same group in IUAC, they find actually for this resample, you see the carrier concentration and the phosphor concentration, and here is the vacancy concentration was measured by positron annihilation. And you see the phosphor concentration increased from here to here almost 5 times, but the carrier concentration more than it's much increased. I mean, for instance, this B and C, and this is a 2 times increase of the phosphor concentration, but the electron concentration is even reduced. So because of this sample has a higher vacancy concentration. So yeah, as I said, the challenges are still existing, and one also try to solve it to increase, to dissolve or to remove the vacancy. And the general view about this problem is, if we want to adopt semiconductor and to high concentration and to narrow junction, and we think about the diffusion coefficient and the temperature and its increase. So, and the activation and the defects concentration, this is the blue one. Generally, if you process your material at higher temperature, you will have less defects. That's a general paradigm. And less defects means higher activation. However, the diffusion is higher. So at the end, we have somehow the activation efficiency. At some point, you have higher, but at very high temperature, you also can have lower because the diffuse away. So it's not useful for us. All those become cluster. So that's a very general paradigm. And how to overcome the problem, it's what we have, the tools in hand. It's to change annealing time. And we can do at high temperature, but very, very short time. So that's tricky. And I also, okay, I will introduce a little bit using ion implantation. If we can also increase the impurity concentration and also the carrier concentration. So, I mean, for the previous work done at the industry, basically they are working with not ion implantation because it's so high concentration we can see, and they are using MB or PCVD to bond at very low temperature. This material, and using ions, we can actually don't care about the solid solubility limits, and we can anyhow introduce the impurity inside. And of course, the challenge is to annealing. It's the same challenge as in the ground material. So what we have the tools are flash lamp annealing in milliseconds, and we generally work in solid phase. And if we use the pulse laser, we generally work in liquid phase. We create a kind of soup on top of your wafer, and in nanoseconds, and you have the impurity as the soup in the material, and the cooling down. It's also very fast, and we hope to arrive at an epitaxial highly doped layer. So that's actually the message I want to send to you. It's short time, and one can try to maximize. The aim is to maximize activation at minimum rate distribution. Yeah. Okay. So by ion beam and also positron beam, we can understand the material at atomic scale, and we are pushing the doping limit from this to over several orders of magnitude, and we also try to understand why it works. Yeah. Okay. I just give you in very brief two examples. Another example is done by ourselves. It's we use this is a tellurium doped silicon. By RBS channeling, we find out it's very probably the tellurium they form a dimer, and they are substitutional. You see from the mapping, the tellurium in the position of silicon, but you have a little bit narrow in the channeling angular scan. It's very probably it's like a dimer, and with this, indeed we have the electron concentration. We almost go to the we almost break the limits. So you see for the implantation work for phosphor-arsenic, they all have a saturation at high concentration. And this is our work. Tellurium implanted silicon, and we use pulse laser mapping. And the carrier concentration, we don't see saturation yet. So it's almost close to 10 times 10 to 21 per cubic centimeter. So another example, it's phosphor doped germanium. As I said, they always have a problem. You have the phosphor concentration at such higher, like 10 to 20, 10 times 10 to 20, but the carrier concentration is lower. It's only like 30% are active. And this is what we have done. It's after flash lamp annealing using at millisecond. and we can increase the carrier concentration by like 2 times. So you see the red one and compare with the black one, and we can, after flash treatment, the carrier concentration increase by, like we say, 100%, and we think it will remove the vacancy. And yeah, this what we have done. It's with the positron annihilation lifetime measurement, and because actually you can see from the comparison, and all the other methods, I mean, are difficult to really arrive at the atomic scale. Only positron can really probe the material at atomic scale, and generally, if you have single vacancy, you have a shorter lifetime. Have bigger vacancy, you have longer lifetime. And this is if you have the calculate lifetime for mono vacancy, and if they are decorated with different number of phosphors. You see, if you have more decoration, the lifetime also increase a little bit. Yeah. So what we find out, it's central message. It's after flash lamp annealing, we could dissolve the vacancy phosphor clusters and release the phosphor to be active. So yeah, basically we process at high temperature. We will have more free phosphor, and we will have less phosphor vacancy complex. So by such a method, we can increase the carrier concentration. And yeah, so I think I'm done. And so I hope give you a message like using ion beam, we can attack the problem now actually exists in industry, to have a shallow junction and to have very high doping concentration. And with RBS channeling, we can, or positron, we also understand the material at atomic scale, and we know why it can work. So thank you.
Yeah, very nice lecture, Dr. Zhou, and you have given an excellent introduction to the implantation and trying to tell the latest things in this, and trying to push the semiconductor technology to the ultimate limits and the challenges in it, going for shallower, narrow junctions, shallow depth, high concentration, and what are the problems. Very nicely tackled. And I see one question by a participant. This is a question by Dirgha Mankar, and he asked that please clarify the difference between flash lamp annealing and rapid thermal annealing. So please address to this question.
Yeah, okay, I will come back to that position, that place. Yeah, rapid thermal annealing. It's you see here the time scale is a second. It works something like several seconds to several hundred seconds. And the flash, I mean, basically they all are white light. So the flash, it's here from this inside you can see it. This is the second, and the difference is that the second digital. So we have 1 millisecond actually. It's around 1,000 times shorter than the rapid thermal annealing.
Okay, so it's something like ultra rapid thermal annealing, so or some millisecond annealing kind of things, right? Sub-second annealing. Yeah.
Yeah, exactly. Yeah. It's you see the light just like it's a you can imagine like the flash in the sky. So and it's an external lamp, and so the light from the top, I mean only the pulse, I mean the length, it's we can tune from hundreds microseconds to 20 milliseconds here.
Yeah, And what is the typical power used in this flash annealing, flash lamp annealing?
Typical power, this depends on the pulse duration. For instance, if we use 20 milliseconds, we generally have energy density something like more than 100 to
100
square centimeter. So it's we always go to the temperature almost melt, but below the melting temperature.
Okay.
Yeah, arrive like that. So it's basically the temperature is higher than rapid thermal annealing. The working temperature is higher than rapid thermal annealing.
Yeah, I see one more question by Tarang Dehuri, and he's asking a basic question which you have addressed somewhere. I remember that what is the difference between normal doping and ion implantation? We can add other elements stoichiometry by doping. So
yeah, okay. That's a very at the very beginning. I think yeah, basically by diffusion, we are limited by the nature. So for instance, one dopant in one particular semiconductor, it has its own diffusion coefficient. So that for some you can diffuse inside, some of them you cannot. So this is one already the naturally designed challenge or difficulty for diffusion. For ion implantation, it's a kinetic process. You can shoot any ion into any material almost. So we are not limited by that. And another, for instance, for the planary structure, if you really want to create a planary structure, and the diffusion in most of the cases will not work. Well, you can see here. Here you want to only have a doping in this area, this small area, but the diffusion will go below the mask.
Yes.
Because you cannot, the nature will decide. If you go to high temperature, it will diffuse everywhere. But for ion implantation, this problem is much reduced.
Right.
Yeah.
Okay.
And so basically, ion implantation is the dominant technique. I mean, for produce this so complicated structure, diffusion will never work.
Yeah. And I see one more question now. There is time we can address. Yeah. We are talking about carbon co-implants, carbon cobalt co-implants. So are there any other co-implants possible? I think yes, but you can address.
Sorry, can you repeat the question?
The question is, we are talking about carbon co-implants.
Yeah.
Are there any other co-implants possible?
You mean the co-implantation?
Yeah.
Yeah, it's possible.
Yeah, in principle it is possible because you have a machine and you have change in the ion source and you can get it. Yeah. Right.
So, yeah, that's true.
Yeah. I have so certain.
Increase. I mean, basically block diffusion and increase make it more sharp.
Yeah. I have some curiosity, Dr. Zhou. This is very clear that for high density electronics and pushing the high density devices, we have to go for shallower, narrower junctions and shallower depths. But this high concentration, how high concentration is helping? Because whether it is a low concentration and high concentration, there is a possibility of lateral diffusion in any way. So how this high concentration is helping?
Yeah, the thing is here, if I mean, of course, for the really the 5 nanometer technology, there are many other challenges. I'm not able to address. So what I can, I mean, very directly to show it's here. I mean, before we have planar structure transistor, and now the main technology is fin transistor. You see here. And the source and the drain area, it's much reduced. If we compare with the planar structure here.
Mhm.
Yeah,
Okay.
and if you want to contact the source and the drain, the resistance will be higher. So we don't want higher resistance. It will introduce more problem. So to solve it, and since the size is limited, we cannot have bigger one. Otherwise, we have other problem, of course. What we can do, the tools, I mean, the accessible parameter, it will increase the carrier concentration.
Okay. Okay.
Yeah, that's but here the industry, they didn't use implantation. I think there is some basic problem also for this. And in IMAC, basically, for instance, also in South Korea, and what they use is generally a CVD, some kind of chemical vapor deposition. You see, they can go to even go to 6% of phosphor in silicon.
Yeah. So I think there is no more question. Marcel, do you have anything? No. Okay. So let me thank the speaker for a wonderful talk, wonderful lecture, and I am sure the students especially must have benefited a lot. I learned a lot from this, and if we have any problems in this, we'll contact you. Okay.
Yeah, thank you. You are always welcome, and welcome to Dresden. Hopefully next year.
Yeah. Okay. Thanks a lot.
Yeah.
Yeah.
Okay. Bye bye, and stay healthy.
Yeah. You too. Yes. Yeah.
Yeah. Thanks.
Bye, Zhengqiang.
Bye.
Bye.
We'll take a break for 15 minutes. Then we'll come.
Okay. So we meet here at 3:30, right?
Yes.
Okay.
Sir, 15 will be, I think, too much. We have to. The next speaker, Cuerno sir, is scheduled at
3:30.
Okay, then fine. Okay. I got confused. Okay, sir. Okay.
Okay. Fine. Yeah. Okay.
So, Zhengqiang, please convey my regards to Eugen and Stefan, okay?
Yes, I will do.
Yeah. Everybody is doing fine, huh?
Yeah, now everybody is fine.
Good. And your kids are doing fine?
Yes. Yeah. Now, I mean, since the winter semester, they are back to the school, and until now, not.
The schools have opened finally?
Sorry?
The schools are open now?
Yes, it's open since June already.
Okay, good.
Yeah, and since June they partially open, and after the summer holiday they fully open.
Good.
Yeah, so but now step by step, and it's like if there is one case in the class, the whole class will be sent to quarantine at home.
Great.
Yeah.
Hi, Rodolfo.
Hi, hello. Can you hear me?
Nice to see you.
Very nice to see you all.
Great.
Hello, Rodolfo. Good afternoon.
Hello.
Nice to see you.
Nice seeing you too. Thank you.
Everything fine in Spain?
Yes, fortunately, the second wave seems to be
going down. Okay, great.
Relative control.
Yeah. Okay.
Thank you.
And
I hope. How about in India?
India also, the first wave is still persisting but going down drastically. It has gone, almost less than 50% gone down, maybe more than that. It is down by 60% or so. So continuously it is decreasing. Yeah.
Yeah, fortunately it is decreasing quite fast these days. I mean, some dramatic decrease happened over last 2-3 days. Yeah.
I see.
So let's hope that it will go down. I mean,
it keeps like this, and then
northern part of the country has little more pollution, particularly in Delhi, and cold also. So other side, I mean, for instance, Bhubaneswar, now it is only hardly 20 cases per day or so. So that's pretty good numbers.
Great. And then prospects seem encouraging on the vaccines, right?
Yeah, that's really good. Particularly these mRNA vaccines, I mean, it's pretty encouraging to. Only the temperature factor, I personally don't know how much it will be useful for the common man.
Right. Okay. Not all of them require these very low temperatures. So, and I guess more will develop without these needs. But okay, at least they are making progress, which is
I mean, the very fact that there's a real feel good sense of safety is there now. It's a little bit that it's going to be finally a reality in few days time from now. Let it get started from London, but that's anyway. Well, lot of RAS will be there. People will get again. I mean, very worried to get it as fast as possible, but then good for good. Yep.
So I didn't quite understand. Sorry. So
what I mean is, I mean, there will be a lot of RAS. People will get worried that when will I get? And that will be the general feeling almost everywhere, But good part is, and that also many companies throughout the world have got into this when pretty final stage. So that's quite encouraging.
Yeah.
Hi, Amboj. Good afternoon.
Hi, good afternoon, Rodolfo. Hi, Som.
Hi, hello, Amboj. Nice to see you too. So okay, thank you for the initiative and the invitation. It's great.
We're glad that all of you could participate. We were looking forward to your lectures. It's always enjoyed by students. So we were very keen to see if you can join. So great.
Great. So, and I think it's a great initiative to keep things moving until the day in which we can again see us in person.
We thought. Initially we thought we will postpone it, but then gradually, once we had postponed it for a month earlier, we had planned in October. So we postponed it, hoping that situation will improve, but then gradually it became clear that we have to get used to in this situation. So we decided to go online.
No, Amboj, I would say that the right decision was taken at the right time, at least. I mean, now it gives us pretty good feel-good factor also, little though, So it gives a lot of positivity. That's good. Rodolfo, how are other colleagues? I mean, Javi and Mario and Raul and everybody there fine?
Everybody fine. Well, unfortunately, Raul's father passed away
because of COVID.
Yeah, he was already, his health condition was not very strong, and then at the beginning of the lockdown, this happened. But other than that, that was unfortunate. But everybody else seems to be doing fine. So a number of people have caught COVID, but no one neither is has been, I mean, undergoing, I mean, too strong conditions. So
actually, the initial days, the pictures we were seeing from Spain, it was really scary. I mean, so many people were suffering, like real wave.
Yeah, it was. So the first wave was really, I mean, it really hit us very hard. I guess Spain is a very big hub, in particular Madrid, for communications and travel, and then it spread out very, very fast. And then after the financial crisis, the public healthcare system was left in not such great conditions. So it was, I mean, that was a problem.
Yeah, I saw one heart-touching clipping. One doctor was crying, because of his helplessness. And
no,
he
it was really
very hard.
My niece, she's a medical doctor. Actually, she's a psychiatrist.
Yeah.
And okay, she was describing I mean, a pretty scary situation. But
Yeah.
okay, unfortunately, okay, we got over that, and the second wave, even though the numbers are actually even higher, not the deaths though.
The fatality rate
Yeah.
came quite low. In second and third wave also, it is quite low.
Yeah.
Yeah. No, because Ambuj, fortunately now everywhere, everybody has some time to prepare themselves. You know, I mean, that initial thing was completely, I mean, left everybody, you know, awestruck that what is happening. You know?
Right. And we didn't know exactly what to do, and doctors didn't know how to treat patients, and then the resources were also scarce. Yeah, it was a tricky time, but okay. So I would focus on the future and
everybody has to do that. I mean, this was really unforeseen and unimaginable kind of time. I mean,
yeah, absolutely.
The world is stuck up, completely stuck up, and still, you know, I mean, absolutely. And so these meetings, these interactions, I'm feeling very happy. You know, we at least we can see each other, we can interact with each other.
Yeah, and I mean, even life is going on in every possible aspect, in spite of the difficulties. It's really great to push forward different types of activities that, I mean, we try to promote.
So that's why special thanks, Ambuj, once again. And by the way, Ambuj, very happy birthday.
Oh, thank you.
You are welcome.
Oh yes.
Oh yes, many happy returns of the day.
Thank you.
Tomorrow is Dr. Avasthi's birthday, so we can wish him in advance.
In advance, Dr. Avasthi. Yep.
Oh, thanks a lot. Yeah.
Happy birthday in advance, sir, from me also.
Thank you.
Happy birthday.
Thanks.
So I guess there has been a break before this. No.
Yeah, it took a break of 15 minutes. Yeah. So within 3 minutes we'll start. Yeah.
Okay.
So Rodolfo, whenever I see you and whenever I meet you, I always talk about the festival in Spain, Tomatino, if I pronounce it correctly.
Yeah. Okay. Actually, in Spain, this is one among many festivals around summertime.
Yeah.
And I think, okay, they were all cancelled, but people still got together, and that has plays a very crucial role for the second wave in our case.
Okay.
In our case, the second wave was earlier than in the rest of Europe. We were among the first, and that has played really a very strong role, because it's like many people, they just cannot conceive the idea of not having these parties and festivals and so on. And even though the official ones were completely cancelled, then they got together in big, I mean, like lunches and dinners. And
here in India also there was a festival of light, Deepavali, and just after that there was a spike in the cases of. It was expected; everybody was expecting it,
right?
But still, people celebrate.
So people in Spain were coining the term something like non-festivals. So there were not festivals, but non-festivals were being held, which was like this, I mean, like a plan B sort of a festival. And okay.
Rodolfo, I think in 1 minute we will start. So maybe in the meantime, you can start sharing your slide, and I will take some time to say a few words about you to our participants, the new students. And although you are well known in your field, and all of us know here, but there are always new students joining. So for their benefit, I will say take some time. So you can try doing that, and I'll say a few words on that.
So are you getting the screen? My screen?
Yeah, visible.
Yeah.
Good. Thank you.
So again, welcome to this session, and this is my pleasure to introduce today's speaker, Professor Rodolfo Cuerno from Spain. He had his bachelor in physics from Universidad Complutense de Madrid and PhD in science in Universidad Autónoma de Madrid. And after 2 years of postdoctoral stay in Boston University, he became full professor since 2016, and is director for computational and applied mathematics master's degree, and person in charge for group interdisciplinary this system and complexes, and mathematics department vice head in 2009 he was. And among his research areas are statistical mechanics and condensed matter physics, with a special focus on growth phenomena and non-equilibrium interfacial processes. He has been principal investigator for several national coordinated grants, grouping experimental and theoretical groups devoted to the study of surface and interfaces and dynamics in various hard and soft condensed matter systems. And he has been advisor to 5 PhD theses and reviewer for more than 60 JCR indexed international journals. He is a member of the editorial board of Journal of Static Mechanical Theory and Experiment from 2004 to 2010, and review editor of Mathematical Physics for Frontiers in Applied Mathematics and Statistics and Frontiers in Physics since 2016. And he has been a Young Investigator Award 2011 by Conselho Social UC3M. So with this short introduction, I'd like to request Professor Rodolfo Cuerno to begin his lecture.
Okay. Well, thank you very much for the introduction. Thank you, of course, to the organizing committees of the school and the conference for the kind invitation, and actually for the initiative, as I said, to keep on the activity. I hope all of you and your loved ones find yourselves in the best possible situation in this tough crisis. Well, let's get started. So initially, the suggestion was that I talked on the nonlinear description of solid flow as to describe nanopattern formation by ion beam irradiation, and then I decided to extend slightly the scope to cover 4 alternative routes to nonlinear modeling. That will be the second talk today. But in the first one, I will consider, well, the conceptually simplest situation of ion beam sputtering of solids that become amorphous or are amorphous or otherwise become under irradiation by ion beams at low to medium energies. This is, of course, a well-known method for surface nanostructuring. And okay, this is simply a theoretical cartoon in which we have the angle of incidence theta that will be mentioned many times along the talk. Okay, of course, microscopically, the process is very complex. There are many processes taking place at many different scales, but as is well known, they lead to eventually the formation of patterns which are nanoscopic in typical sizes, like these historic patterns on glass observed by Naves and collaborators by irradiation with ionized air, which already, it strikes the eye the similarity with macroscopic pattern formation. Changing the symmetry of the experimental conditions, also changes the symmetry of the pattern, similar to what happens like on a sandy beach by the suitable incidence of waves to produce patterns on, let's say, sand. As probably, I mean, most of you are aware of, actually, I mean, it's interesting that this technique was associated in the very first paper that coined the term nanotechnology. Well, actually, Taniguchi in this paper back in '74 identified, as is underlined here, ion sputter machining as the most promising process to the ends of nanotechnology in general. And today, we're still trying to understand a number of basic questions about the process. So let me underscore a very important fact, that is that the production of these patterns takes place in macroscopic times. We have seen the MD movie before. That corresponds to microscopic scales, and there are many things going on at picosecond scales, but actually ripple formation takes macroscopic time to produce. As illustrated here for the silicon pattern shown above, we can see that the evolution of the surface roughness and the wavelength takes macroscopic times. The horizontal axis is in minutes. Moreover, there are a number of different properties that theory should explain, which is not only the static formation of ripples, but also, in principle, as complete dynamics as possible that includes a non-trivial motion on the target plane, which again takes place, in this case, well, you see that the velocity, so nanoscopic scales are covered, nanometers, in macroscopic times, seconds. So this actually has to do a lot with the theoretical difficulty to describe this so-called multi-scale systems. Well, as is well known, another feature of this pattern formation process is that it is universal, in the sense that very similar patterns are produced on different types of targets, like semiconductors, insulators, or metals. Many of the qualitative and sometimes even the quantitative features are shared by different ion target combinations, and they take place also in a relatively wide range of ion energies. So there's universality from that point of view. I'm sure already the school has showcased a number of applications of the patterns which can be produced by this technique. Many have to do with magnetic or optoelectronic properties. Let me just show a couple of images having to do with biomaterials. And as you see, ripple patterns, which are the small scales seen here, notice the arrow is 2 microns across. Largely, not completely, but they largely guide the proliferation of pseudopodia for some cells, which might constitute a biomaterial of interest, for instance, for medical applications. Likewise, one can try to look for the optimal wavelength of ripple patterns that allows to optimally align DNA tubes, so-called DNA origami tubes, which are basically like very large DNA-related molecules. And they, in the case studied by Teshom and collaborators, they found an optimal alignment for the 30 nanometer periodicity of the ripple structure, okay, as compared with 20 or 50. So one could conceive of many additional applications of, let's say, pattern, ripple pattern, sorry. Then when it comes to modeling, well, one has to make a choice. And okay, our choice will be continuum methods that in principle are typically able to access the largest both time and length scales of the systems as compared with other alternative methods. So that's today it's very difficult, even though very interesting efforts are being made to bridge the gap between different methods like Monte Carlo or molecular dynamics to mesoscale or continuum methods. But okay, this is a topic that remains to be developed for the future. Let me so probably maybe in the talks by Tapowrata-Som, some of this has been covered. Let me go briefly through the basics of the continuum description, the classic continuum description of these processes. And okay, they are originated in the energy deposition distribution as described by Sigmund in the linear cascade approximation, valid in the range of energies we'll be addressing where nuclear stopping is dominant. And okay, made into a continuum interface equation by Bradley and Harper a number of years, like 20 years later. Already Sigmund back in 73 noted that assuming that the velocity of erosion at a local position on the interface like this point or that point is proportional to the total energy that originates in energy deposition from collision cascades, well, that leads to a morphological instability because a local minimum focuses more energy than a local maximum. A minimum erodes faster, and then the distance, the difference in height between maxima and minima are amplified. So in the continuum, this was already Bradley and Harper's contribution. This leads to a morphological instability. So if h is the height of the interface, according to this mechanism, to the simplest approximation, it behaves like the diffusion or the heat equation with the wrong sign for the diffusivity, which amplifies differences. And then it was Bradley Harper's contribution to say, well, actually, this will lead to some ripple structure, but with a wavelength that is basically given by the typical penetration depth. So let's say a couple nanometers, but ripples are much larger than that, like at least 10 times. So we need a counteracting mechanism, and they were identifying surface diffusion. Surface diffusion, as in the classic description by Mullins, is a process that is said to obey a conserved law. Why? Because if we integrate this equation in space, because of boundary conditions, let's say periodic boundary conditions, the contribution of the right-hand side equals 0, and the total amount of matter is conserved by this process. And then assuming that this current minimizes a chemical potential that makes a difference between maxima and minima, particles on average tend to travel along the surface looking for highly coordinated positions at minima, and we take the chemical potential being basically the curvature, and then we end up with fourth order equation that, when put together in competition with the previous Laplacian, leads to this equation. This equation is actually linear. It can be easily solved in Fourier space, where each Fourier mode k behaves independently of the others, with a rate of amplification or decay, the so-called linear dispersion relation, that is a function of k. And because it looks like this, as one can plot this simple polynomial, then there's a k vector k star, which is amplified because it has a positive omega much faster than all others, and it leads to the production of, let's say, a dot structure or a ripple structure in the case that the system is anisotropic. We break the anisotropy between the x and y directions in the plane, and then this function is like this paraboloid with this inverted paraboloid with two bumps which are the maxima that lead to ripple structure with this periodicity, or depending on the angle condition, it can rotate by 90 degrees. Okay, that's the classical description, let's say by Bradley and Harper, of the ripple instability. But in more recent times, well, a number of insufficiencies of this description were elucidated. It took a while, and this is a summary of the most agreed, the basic morphological diagram for ripple formation in terms of energy in vertical and incidence angle in horizontal. And okay, the main feature here is that unless theta is above a critical value, the surfaces are flat. And then ripples appear for theta larger, let's say, than 48 degrees to normal. In this way, lambda is the ripple wavelength. And as you see, right at the transition, actually, the ripple wavelength is infinite, theoretically. And okay, it becomes smaller and smaller for larger angles, okay, like this, much larger than 45 degrees. And this exponent seems to be universal, to be actually 1/2. Actually, this speaks of universal behavior, like in continuum phase transitions of the second kind in thermodynamics, in equilibrium thermodynamics, where there's a typical scale, which is the correlation length, that is infinite right at the critical temperature. Then the critical temperature is not universal. It depends on the material and experimental conditions, like here with the value of the critical angle. But then there are features like the value of this exponent, 1/2, that seem to be universal, just like critical exponents in equilibrium, so-called critical behavior. This is actually an analogy, because we are far from equilibrium here, but in this case, in the pattern formation literature, this is called a type 2 morphological transitions that sort of suggest second order phase transitions. Then what additional important features should a theory account for? Well, actually, the form, this polynomial form for the linear dispersion relation has been eventually, not long ago, but it has been measured experimentally by Gisax experiments. And as these are the data for different colors correspond to different angles of incidence. And okay, it's hard to see, but as you see, this red color with 65 has a band where this omega is positive here, while for 0 angle, omega is negative everywhere. So all modes are stable. Then another important feature, and in this work by Umbach and collaborators played an important historical role. For many, let's say, semiconductors, the ripple wavelength is a non-trivial function of ion energy. And it roughly scales, and these are the data of Umbach and collaborators for silica. It's almost linear with ion energy. And that has played also an important role to favor or disfavor different models for ripple formation. And in particular, Umbach and collaborators were already advocating for the role of viscous flow, like in a fluid, confined to a very thin surface layer. So we will come to this in a moment. Well, if we want to model this process, of course, a natural option, because also computing power has increased so much in recent times, is to resort to very detailed descriptions like provided by molecular dynamics. Here we have an MD simulation by Norlund. And as we can see, basically, we see the formation of a crater by the incidence ion. And of course, this will have an effect on the surface morphology. And this is the basic idea of so-called crater function approach to this pattern formation process. And this is, for instance, an approximation to the morphological diagram by Norris and collaborators. And actually, through the I mean, the idea of the crater function approach is not only to use MD, but do some sort of multi-scale modeling in which the results of these crater estimates, statistics, are fed into continuum equations like this. But notice in basically all these type of approaches, there's one term here, which is the one, I mean, this equation, just by chance, happens to look the same as Bradley-Harper. Notice the terms are the same, but the physical meaning is very different because the contribution of sputtering to these coefficients nu x, nu y is very small in many conditions. And then this fourth order derivative is not surface diffusion as described by Mullins. It is actually surface confined viscous flow as advocated for by Umbach and collaborators. But now the problem is that this term has to be put in by hand, basically, in most of the crater function approaches, because it corresponds to this extremely slow dynamics, which is not accessible yet to MD or Monte Carlo. And then beyond some consistency issues of the initial proposals that have been dealt with by Bradley and a number of collaborators, okay, there remains a huge separation, let's say, from the modeling point of view, between the very microscopic modeling of collision cascades and crater formation induced by them, and relaxation by surface confined viscous flow. And a similar consideration applies to, let's say, crater function estimates not done from MD, but from, let's say, Monte Carlo simulations. There have been a couple of talks yesterday, I think, right, by Hans Schofsas. So then, but in a way, actually, on the other hand, all these mechanisms, let me again show this, what they, in a way, advocate for is the importance of momentum transfer. There is beyond the energy deposition that eventually reflects into sputtering rates, which are not so crucial in this ripple formation process. This crater formation is sort of controlled by momentum transfer. Well, if we want to model momentum transfer in the continuum, there's a canonical way to do that, which is the Navier-Stokes equations. Actually, this is just a sketch of a fluid element. That's the standard approach to discussing how the equations for a fluid look like. So let me assume that the ion beam has amorphized a surface layer, and this surface layer can be thought of as a fluid. If we want to set up the balance for linear momentum, then we have to consider Newton's second law. And then this is a continuum medium. So there are stresses like tau acting on each side of the volume element. And actually stress is a full-fledged tensor. It has a tensor character. And then there is hydrostatic pressure. And we have to put all of that together. And Newton's second law for a fluid just looks like this. This is the so-called total time derivative for the fluid velocity, v. Rho is the fluid density, in general not a constant. And this total or convective derivative, this is actually can be expanded. This is just using the chain rule for differentiation, okay? And this is, we are left with this, and this is the left-hand side of Newton's second law. This is acceleration, mass per volume density times acceleration. And this equals the net force. And the net force is a combination of the pressure drop plus the divergence of the so-called stress tensor. One has to do all this balance, and this is just a balance of linear momentum, where in principle F stands for so-called bulk forces, like imagine gravity, which are sources of the of momentum inside the bulk of the fluid element. Beyond that, let's try a simple approximation. We consider a incompressible fluid, which is Newtonian. Then we assume there are no sources of velocity inside the fluid element. The divergence of the velocity is zero. And moreover, the fluidic stress is just due to friction of fluid layers one against another. Okay, and there's the velocity has a gradient in space, and mu is just viscosity. Then putting everything together, this is actually today the 1 million problem of Navier-Stokes equations, just as Navier-Stokes for an incompressible fluid. You may have heard about this $1 million, which is offered for the Clay Institute in the US to anybody who either proves or gives a counterexample for the bounded evolution of solutions to this equation, in spite of the centuries passed since it was first proposed. Well, our view of these solid systems as nanoscale fluids is, is relatively widespread. For instance, back in, like 3 years ago, there was an interesting study on neutron irradiation of quartz substrates by molecular dynamics, whose basic conclusion is that the structure of correlations for irradiated quartz makes it more similar to a fluid than even to a silica glass. Moreover, it is well known that these days many classic macroscopic hydrodynamic instabilities, like the one leading to snowflake formation for ice growing from under cooled water, or on the right-hand side we have the classic Rayleigh-Taylor instability, in which we just painted a glass cover with oil. We turn it upside down, and because of gravity, droplets are being formed. There's a nice droplet pattern that is a macroscopic instability, but both instabilities have microscopic counterparts, like in the growth of epitaxial graphene for snowflake formation, or irradiation of gold samples by laser, and then laser irradiation, and then dewetting, as elucidated in these much more recent references. Well, in our case, this is a very detailed study of pattern formation on silicon by argon irradiation for different angles of incidence. And as you see, beyond, let's say, 45 degrees for D, ripple form beyond that angle. In this case, the sputtering is relatively important, but there have been more recent studies in which sputtering seems to be negligible, and nevertheless, basically the same ripple patterns form with, again, a critical angle, let's say close to 50 degrees. Well, yeah, something like that. And there are pretty analogous observations in many other experimental works. So what do MD simulations say from this point of view? Well, indeed, this is they show the formation, of this amorphized layer, as we can see in this relatively old one by Kalanasundaram and collaborators for the case of silicon. And this is a TM snapshot, and then the amorphized layer appears in white here. And then, from the point of view of viscous relaxation, MD simulations tell us that the fluid seems to be, on the one hand, highly viscous, very highly viscous, on the other hand, incompressible, and third, there is and in this, there are classic studies by Davis and others back in the 90s, where one thinks of the damage, which is irreversible displacement created by the ion beam, and then through Hooke's law, strain, this damage, is converted linearly to stress. And then the MD simulations, what they suggest, I mean, and this is, the errors are relatively large, but okay, I think the result is conclusive that the stress field created by the ions within the layer is not homogeneous. It depends on the depth. Well, then we will try to put all these ingredients together to have like the simplest possible model of momentum transfer within the amorphized layer and see how that affects the interface. So what we have here, that's the amorphized layer, and then this within, I mean, this is the irradiated layer, and there always remains, sorry, an irradiated bulk. And then, okay, remember our sketch. We will assume that in this darker brown layer, which is the irradiated one, that fluid is highly viscous and incompressible. And then this is Navier-Stokes equations become so-called Stokes equation, in which this zero in boldface corresponds to the so-called inertial or acceleration terms. Let's say the fluid is so viscous that inertia can be neglected. Moreover, doing just the standard scale analysis, dimensional analysis, as in fluid dynamics, one is left with the conclusion that, okay, Reynolds number has to be very small because the thickness of the amorphous layer is a few nanometers. Okay, and then on top of the high viscosity, then we just drop inertia. And then we are left with two contributions to the stress tensor, just the fluidic one, just hydrostatic pressure, and the terms corresponding to the viscosity. And then what we do is introduce in the simplest possible way a term that represents the driving, this stress induced by the driving. It reads like this. It is a tensor, but it's diagonal. It is traceless, so the sum of the diagonal elements are zero. And there's simply an overall factor that depends on the depth. And then we assume that the total stress gradient or stress jump across the layer is a fixed constant. This will be our parameter. And other than this, well, it's just, it has I mean, it's just a straight line, the profile for along the ion beam direction, which is the coordinate z prime. Then, well, we need to provide boundary conditions. We will set apply the effect at the interface of the ion-induced stress to be another constant, our second parameter. We will assume, and then that the fluid is relatively standard, so the interface has to pay an extra free energy to keep a non-zero area, and that is mediated by surface tension, the third parameter, sigma, and here kappa is just curvature, and this is just a balance of stress, where this is the stress due to the so-called Laplace pressure related to surface tension. And then what about the interface that we are observing in the experiment, which is the top one, H, up here? Well, we just leave it free. And free, this free interface term has a technical meaning in the fluid context. And so when describing modeling fluids, if the fluid interface is said to be free, if it can just, I mean, it is just controlled by the fluid flow. If the fluid undulates at the surface, well, that's what the H does. And this has to be written in terms of the total time derivative, but using the chain rule for differentiation, we eventually have here eventually this will be our height equation, where u, v, and w are just the three components of the velocity field. Other than that, the boundary condition for the velocity field down here will be assumed to be flat. So the interface, the amorphous crystalline interface, this black line here, we assume it for simplicity, analytical simplicity, it to be flat and impenetrable. So the fluid velocity at that position is 0. Then what remains is a little technical. Let me just give the main idea. The main idea is that in the end, the thickness of the amorphous layers can be seen here. The thickness of the layer in white is small as compared with the maximum to maximum distance on the ripple structure. So we will introduce so-called slow scales in the plane, xy coordinates. So which means that for x and y to take values comparable to z, the original scales x and y have to increase a lot because we consider them multiplied by a small quantity epsilon. And then what we do otherwise is just set up a perturbation approximation for the velocity and pressure profiles in terms of epsilon. Okay, let me just flash just the simplest case, the zero-order solution. The equations look like this. The Navier-Stokes equation just look like this, doing this approximation. Look, if one just thinks of them, I mean, these are simple to solve because they are linear. The boundary conditions look like this. They are also linear. We just put everything together and we end up with the solution in perturbation theory for the pressure and velocity fields. Notice, for instance, u depends on the depth, z, the vertical coordinate, and basically has a parabolic profile like the standard Poiseuille flow, because the boundary conditions, the velocity here and here is 0, as in the classic Poiseuille flow. And then the pressure depends on depth, and in particular, it depends on the height field, also pressure and velocity. And this is systematic to all orders. So in the fluid dynamics terminology, the pressure and velocity fields are enslaved to the height, which is to say the height reaches sort of a steady state in quotes much, much faster than the pressure and the velocity. And so it provides like a boundary condition for them, and their solution depends on the height. But this allows eventually to close when substituting pressure and velocities, because they depend on the height in the equation for the height, eventually we can close the equation for the height and end up with an equation all involving the height. This equation looks like this. Notice this equation, okay, is complicated, highly nonlinear. Let me just stress this term in blue here, which is the classic description of surface confined viscous flow, as in the paper, in the classic paper by Orchard in the 60s, that Umbach and collaborators quoted themselves when advocating the importance of this physical effect for the ripple formation. Okay, we have it here in full, not only at linear but also a non-linear order. Actually, if you think of this equation slightly, okay, all terms, this equation in the fluid dynamics community is called strongly nonlinear. Why? Because all the terms are nonlinear. This is quadratic in H and derivatives, cubic, fourth order, and fourth order. We can do, in order to simplify it, if desired, we can do a further expansion and assume that H is a small perturbation of a constant straight line, let's say. And in this case, we get an equation related with the previous one, which has now linear coefficients, like this one. Or, for instance, in blue, we have non-linear surface confined viscous flow, but also linear. And no wonder this is exactly the term, this one, used by Umbach and collaborators, the surface confined viscous flow, which is to linear order a fourth order derivative. There are many equations in the fluid flow context are related to this one, or a number of them, relevant ones. Let me skip their discussion and let me flash some predictions from this nonlinear modeling. Well, the predictions can be encoded in this sort of phase diagram, morphological diagram, rather, I would call it, where the axes are vertical, the incidence angle, and horizontal, just a non-dimensional parameter small g, which is the ratio of two stresses. This is the stress at the denominator applied at the interface by the ion, just the average stress there. And then this one is a gradient times a distance. This is the total stress jumps across the interface. Okay, so down there at the amorphous to crystalline interface. Then all these lines can be computed analytically from the model. There are predictions from the linear approximations, which are fulfilled by nonlinear simulations. Actually, there's another line that can also be computed analytically that separates ripple motion with negative or positive velocity. And then let's compare negative values of G that correspond to a less compressive ion beam along the ion direction with positive ones, more and more compressive along the ion beam direction. And in each case, there are two symbols corresponding to relatively low and relatively high angles. All of them, notice that if we fix, I don't know, like, for instance, if GB equals 0, then small g equals 0. This means the stress field within the amorphized layer is homogeneous. Then the prediction from this model is that the critical angle is 45 degrees, is the crossing with the thick line. And in such a way that if we keep G fixed, that corresponds to maybe some combination of ion and target materials at a fixed energy. Well, if we compare smaller values of theta, they are in the flat morphology region, and larger values correspond to ripple formation. So in the examples I will be giving next, I will only consider for each value of G theta angles with that show ripples. So one can compare actually predictions of the model with the behavior of the experimental behavior of the ripple wavelength with angle, and the lines fit nicely the data. And okay, these movies are produced using as estimates parameters extracted from the literature for argon irradiation of silicon at 1 kilo-electron-volt. And as you see, okay, conditions A and B correspond to this, C and D corresponding to these dots. And you may have seen, let me go back and start the movies again. In each case, the angle is smaller here than there, smaller here than there. And just the naked eye suggests that the dynamics are faster for larger values of theta. And we see the formation of anisotropic ripples at long enough times. We have some, we do have the information on the pressure field within the layer. And okay, this is the behavior of the roughness as a function of time. The qualitative behavior in 1D is sort of agrees with many experimental observations. Actually, the main mechanism for the instability, studying the pressure field, coincides with this idea that different parts of, let's say, an initial perturbation get different exposure to the ion beam from both sides. And because the fluid is incompressible fluid that accumulates on one side because it's flowing slower, eventually bumps out, and that leads to ripple formation. Well, of course, we would like to see the evolution for 2D interfaces, and these are like top views. And qualitatively, we have a similar behavior. Notice this red line in dash type corresponds to exponential growth. So we have some behavior, then exponential growth, the linear stages, and then after that, the roughness saturates to relatively small values. So the roughness of these structures, as seen, is not particularly large, as seen in the experimental pictures I was showing before. And indeed, the timescales are macroscopic. So the non-trivial evolution and saturation of these ripple features take maybe of the order of hours. And we have different behaviors corresponding to different, let's say, experimental conditions, which are encoded in the value of G. Again, let me go back. G, if I may, is the parameter that within this model encodes the full dependence of the experimental conditions. Because, fixing a combination of ion and target materials and an energy, in principle, the stress field has some features which we simplify into this very simplified linear behavior with these two parameters that give the total value at one point and the gradient, the constant gradient. Okay, and then the thickness of the amorphized layer is also known to depend on experimental conditions. These are for condition A, for instance. These are power spectral densities of the height for increasing times. As we see, there's, and also, of course, the naked eye suggests that there's some disorder in the ripple structure, both in the X and Y directions. And these are the power spectral densities along the X and Y directions, respectively. In terms of scales, just let me show you the, just for reference, one of the movies we were starting the talk with, which corresponds to the experiments by Alchemadi on gallium irradiation of silica, well, of glass, actually. Let me stress that we are not claiming quantitative comparison with these experiments. Again, the simulations I'm showing you on the left-hand side correspond to parameters for silicon. It would be nice, actually, to try and perform more detailed comparisons with other systems, but we think that basically the scales seem to be correct. Let me turn off my apologies for the bell. It was my email program. Okay, then because we were focusing on nonlinear effects, a number of nonlinear properties of many experiments, at least qualitative, are captured by this modeling. The amplitude stabilizes in realistic timescales. The wavelength may coarsen or not. Actually, this simulation so far show marginal, if any, coarsening. The amplitude to wavelength ratios of the ripple structures once produced are small. So let's say the wavelength is more or less 10 times larger than the amplitude. The ripples at long times are asymmetric. They have some sort of sawtooth structure. They show a motion in plane, which is non-trivial, and it depends on experimental conditions. Ripples show a substantial disordering, well, depending again on parameters. And once we are in the ripple formation phase, the surfaces show stronger fluctuations, stronger disorder for larger values of the incidence angle than for smaller values. Well, again, let me stress in particular that this fluid flow picture allows to associate the instability with this, well, what we call here an effective gravity, which is induced by the different exposure of different parts of the surface to the ion beam coupled with the viscous flow, similar to fluid flow down an inclined plane, which is a classic instance of fluid flow. But this being the case, of course, important additional features are maybe probably related with sputtering, and we're continuing our work in introducing sputtering as a competition with this main relaxation mechanism we just discussed. Before I conclude, I would like to give some minutes for potential discussion. Let me acknowledge my co-workers on the theory side, Mario Castro and Javier Muñoz García, and on the experimental side for basically our papers, which I've been discussing here. Well, sorry, in theory also Ana Moreno Barrado, and in experiments Raúl Gago and Luis Vázquez at Instituto de Ciencias Materiales de Madrid, and also Carmen Ballesteros and Beatriz Galeana here in my university. I belong to the, and well, Javier and I belong to the math department, and these two professors belong to the physics department. And then, well, I would like to leave you with some further reading. If you heard me before in some of these conferences of schools in this series, okay, I suggested this review paper, and more recently we have published together with Professor Jason Kim in Seoul in Korea a shorter and relatively wider in scope perspective rather than a proper review, which is already available and free for a few months in the Journal of Applied Physics. And with this, I thank you for your attention. I would appreciate any questions or comments you may have. Maybe there's something in the talk. Oh, okay.
Yeah, thank you, Rodolfo. This is a very interesting talk as ever, and any latest updates. And let me see in the chat box if some questions in this.
Hello, sir. I am Indra here.
Yes, hello.
So I would like to know if you can a little bit discuss about the application of biomolecules on rippling. So functionalizing the biomolecules, and so you touched upon it, but only one slide, I think 1 or 2 slides you have shown.
Right. Well, let me try to project here.
Yeah, that's a very interesting side of application of patterning.
Indeed. I think, okay, it is of course a very natural application these days, and of course challenging. Let me stress, for instance, I took these 2 examples from works by the group of Adrian Keller in Paderborn University in Germany, and he has done a lot of work and is still active in this context. So, for instance, related with, I just mentioned Raúl Gago at the Instituto de Ciencias Materiales de Madrid. He's currently, together with collaborators, working in, a very natural question is, can we control or engineer the surface so that we can facilitate or hinder the proliferation of material. Maybe, like in this context, this osteoblast, they lead to healing of wounds in bones, wounds due to bone fracture and so on. So in this case, we would like to facilitate, to look for conditions that facilitate the proliferation of the cells. But maybe we are thinking of doing some covering, some layering, protective, the word I think is coating. Oh, that's great to hear, Jerome. Well, I refer to Jerome's talk, but let me say that, okay, very general and not another very natural question. Can we hinder proliferation of, let's say, bacterial growth in some media due to alterations in the structure? Actually,
so why this question comes into mind is because sometimes the rippled wavelengths and the height are so small that whether you take a planar geometry or a rippled geometry, will it make a difference?
Right.
Suppose that they are very narrow and very small.
That's an excellent observation. And actually, I was relatively recently involved in a work with a group of researchers in Mexico City, and they had experience in implantation of gold into titanium and titanium-related materials, and they did it at high energy, I mean, like 1 megaelectron volts. But as it turns out, stopping is still dominated by nuclear contributions. And the nice thing is that the ripples in this case are much larger. The amplitude of the ripples reaches close to 1 micron.
Okay.
And then the wavelength is of course larger too. But then I think that's a first step maybe in the direction of first considering biocompatible materials like gold and titanium.
Yeah.
Then trying to tune the material properties and energies so that the scales are the relevant ones for bacterial proliferation, which, as you just said, are typically in the micron size. 1 micron is the typical approximate size of one living cell.
Yes.
So absolutely. And then, okay, so probably Jerome tomorrow will discuss.
Yeah, we will listen more about it tomorrow. Okay, thank you, sir.
Thank you.
Yeah. Okay, so tomorrow we will have more on this bio-related materials, on bio-related aspects of the rippled surfaces. And I am not seeing any question here right now. I have some query that this velocity of 0.3 nanometer per second of the ripple, this has been experimental observation, and then if it is, then it is by some in situ work must have been.
Well, this was the estimate in. Sorry, let me see here. This is the estimate by Alchemati already back in this paper. More recently, this is like 15 years old. Okay. There are more recent studies done, for instance, on silicon by, for instance, Hans Hofsas himself, by Herbert Nasser, also on silicon. And okay, the order of magnitude is this.
Okay. And
there's one. Yeah. Oh, sorry.
Yeah. Does it depend on the material also, the material density and such factors?
Yeah, probably yes. So the detailed figure, almost for sure, depends on the material specifics. But the order of magnitude is that one. And I have a very, okay, if you wish, that's it may be a coincidence or not. That's up to you to decide. But I can give you another system that has this order of magnitude of velocity, and that's a glacier.
Ah, yeah.
motion of a glacier
Yeah.
is the order of 1 nanometer per second. So, and technically, the modeling of very complex fluids like this viscoelastic fluid, ice, being driven down by gravity and so on. It is also a motion controlled, it seems, by defects, which in a way is what we are saying somehow implicitly by stating that the motion is driven by the stress field induced by the strain field created by the ion beam. So, if this is by chance or not, I don't have to say, but okay, that's another example.
Yeah, right. Yeah. Okay. Dr. Som, you have some question?
There was one question, right?
No, I just wanted to make a small comment in this direction. That Hans actually helped us to calculate for the velocity this thing using mostly SRIM SP simulation for SiO2. And that's the work Rodolfo published in your edited special volume in 2018 PCM. So this can be done, but I think Paul had done probably the experimental work, isn't it? The PRL work was experimental proof, correct?
I think so.
Yeah.
There seems to be a question in the chat. Shall I answer?
Yes, I don't find, but please, if you see, please tell. Yes. Sure.
Yes. The question is by Dirga Mankat. Kindly clarify what G stands for.
Okay.
Well,
okay, I see.
Why are we using the letter small g? Because our physical picture, extremely simplified, is this one. And I mean, you know the classical experiment of a fluid layer down an incline, and there is some undulations being formed, some sort of rippling of the fluid surface, and that's driven by gravity. But other than that, let me come back. Okay, here. I hope you're seeing this slide. Small g.
Yes, sir.
Thank you. We define small g as a non-dimensional parameter that is a ratio of stresses. Then let me just go back slightly. There are, small g is a ratio of two parameters. In terms, one is a product, GB times H0. H0 is the average depth of the amorphized layer, of the irradiated layer. Typically in experiments like 2 nanometers for 1 kilo electron volt irradiation of silicon. Then GB is the gradient of stress across the layer, which for us is a constant, because for us, the dependence of the stress with depth is just a straight line. So GB is the slope of that straight line. Then in physical units, GB times length is a stress, because GB is a stress derivative with space. And then the denominator is again stress, which is the reference value of a stress assumed to be a constant at the free interface. Then G becomes non-dimensional, and one can, in this paper, I quote here by PRB 19, we discuss in an appendix the reason why the behavior in this model only depends on two parameters, and that can be taken as G and the angle of incidence. And then, well, I was discussing, maybe I went a little fast, and if that's the case, I apologize. By the way, let me insist that I would be happy to answer any questions you may have. If not now, due to time constraints, through email or whichever. You have my email, and you'll be welcome to ask me any question that you may have.
Okay, so thanks, Rodolfo, for very nice talk, very nice lecture, and giving from the beginning and its applications, basic structure and everything. So now is the time to take a break. Dr. Ashokan, what time do we meet?
He has another, it's up to him to decide. Maybe 10 minutes if he wants, he can take 10 minutes. Yeah.
Okay.
So,
So break of 10 minutes, Rodolfo, is it okay?
Perfect. That's perfect.
Yeah.
Okay.
Okay.
Okay. So, so meet after 10 minutes, all of us.
Yeah,
Okay.
44, 45 approximately.
Yeah.
45, yes.
Yeah,
Yes.
Indian time, 16:45.
Perfect. So see you in 10 minutes.
Okay. So, well, we are back by the small tea break. So now, Professor Rodolfo, to continue, please take care, take charge of it.
Yes. Thank you. Let me try to share the screen. Let me first, well, because it came in the question by Indra. This
Yeah.
are my Mexican colleagues, and in this paper, for instance, as you see, they bombard, they implant titanium and this related material with 1 megaelectron volt gold ions. And okay, just let me flash you these are the type of ripples that are formed. And we did a later work in which actually the same type of modeling, well, or related as, okay, I just discussed, and I will also consider in my next talk, seems to be reasonable. It accounts for some of the experimental properties. Then let me change the presentation.
So, Rodolfo, this kind of material is of special interest to this aircraft industry.
Oh, I see.
Yeah.
Sure, because of, yeah, I understand. Their original motivation was bio implants.
Okay, okay, yeah.
But well, in principle, yeah, any technology that may benefit from the properties of this titanium and so on,
Yeah,
might be a potential source of applications. Let me just take 1 second to close my window.
Yeah.
Sorry. It's also because of noise, and it is cold out there. So we're having now low temperatures. Let me try to project. I hope you're getting the second presentation.
Yes, we see it. Yeah.
Yes, there is.
Thank you. So let me move on. Actually, one of the nice features of having 2 talks is that I can again thank the organizers. This is really a very sincere feeling for their initiative and kind invitation. Well, let me consider in this second half of my presentation, so to speak, a different approach to modeling, which is like in between. So if we compare the type of like models, like these interface models pioneered by Bradley and Harper, with modeling through the Navier-Stokes equations and so forth, there's something intermediate between these kinetic and hydrodynamic models. And this is centering actually the presentation in this second half. So the idea is that we will basically, it's a kinetic model like Bradley Harper's, let's say, but enhanced by the fact that we are sensitive to the description of the material which is being transported. So actually, as some of the movies I was showing before already suggest, the evolution of the interface is actually dependent on the many processes that are taking place there, and mostly on the transport of material. Then what we'll do is introduce a second field, R in red, which is in principle describing the density of species, defects, adatoms, and so forth, which are mobile on the surface. And then we will couple the time evolution of this within a continuum description to the time evolution of the height itself. And in this, we exploit very strongly the analogy with pattern formation in macroscopic systems like sand dunes, and so on, where this layer where material is taking place is very, very thin and is formed by basically a density of so-called saltation grains. Well, sorry, I cannot pronounce the correct word correctly. Okay, that's the density of grains which are subject to the process called saltation, which is the process which is actually implementing the action, the external driving by the wind. And then the height is just the height of the sand pile, which is evolving in time. These models actually are called hydrodynamic without quotes in the context of geophysics and, let's say, pattern formation, let's say for people who do so-called granular materials. As you may be aware of, okay, there's this domain of physics and science in general of so-called granular materials, from sand grains to rice grains to, okay, grainy structures, which are very interesting, very diverse in their behaviors. And actually, to date, there's nothing comparable to the Navier-Stokes equation for such systems. And in that community, this type of continuum model, okay, is considered relevant because they give a lot of insight on without being the full description yet. So let me express, so like Navier-Stokes equations themselves, the basic equations here are just an expression of conservation, just conservation laws for the height and the density of material. And then we can think that, okay, for the evolution, the local velocity of the height, okay, there are processes that tend to decrease the surface height, which are encoded in a rate. The dimensions are, let's say, length per unit time, gamma of excavation. And there are processes that locally increase the surface height, which we have to think that there are these grains. The grains, or let's say in our context, there are add-atoms or defects at vacancies subject to transport on the surface. If an add-atom decides to stick back to the surface, then that increases the local height. If an add-atom is excavated from the height, from the layer, is sputtered away, okay, that decreases the local height. But now there are processes in which atoms which are excavated, not all of them leave the surface. They are dislodged from their equilibrium positions, but they are left to move around the interface. So they actually increase the local value of R. And a fraction of them, 5 times gamma x, well, this is incorrect, I think, are sputtered away. And then whatever increases the height due to addition, okay, just decreases. It happens because that's mobile material that becomes immobilized. Okay, that increases H and decreases R, gamma at here with the different signs. And then finally, just this density tends to reduce its gradients, and there's diffusive motion from regions where the density is high to regions where the density is low, and that is done, and this should be also plus, sorry, just diffusion on the surface, which is then surface transport. Now, let me just, as an exercise in quotes, rederive like some of the well-known continuum interface equations for ion beam sputtering within this approach. Okay, we just assume Sigmund's Gaussian, and together with Bradley and Harper, we implement Sigmund's morphological instability in this way. So we specify that the rate of excavation, let's say sputtering, depends in an unstable way with the appropriate signs for these parameters alphas on the surface curvatures different along the x and the y directions. And alpha 0 is the average rate of excavation. It's not ripple motion, but excavation, sputtering. I mean, the etching rate, let's say of the order of 1 nanometer per second. Well, now let's add to that some Carter-Vishnyakov type effect. There are these like in the crater function approach. Well, these collisional events leading to crater formation eventually have a stabilizing effect. So we may add to the previous contribution another contribution, which is also sensitive to maxima versus minima, so it depends on the curvatures, but with the appropriate signs and geometrical effects. So this beta factor has to be corrected has to implement the correction of the ion flux, like due to the local inclination of the surface, and it has to have the right sign depending. I mean, it's just a projection of these currents implementing this ion ion momentum transport. And then on top of the other two, we may introduce surface diffusion, just Moulin style. So what we have is like a so-called Gibbs-Thompson effect that locally does the job as in our previous talk. So on the average, particles on surface maxima travel more towards surface minima, and that sort of reduces surface height differences. If we implement this in this way, where this addition rate depends on the curvatures, is like a surface tension-like effect. Well, because this is mediated by an additional derivative, actually, if we switch off the ion beam in this case and consider this mechanism, we end up with Moulin's equation. And that allows us to trace back the origin of some of the parameters which are being used here, like surface tension, the thickness of the average thickness of the irradiated layer, and so on. Actually, as I discussed in my previous talk, a term like this, in principle with the same form but different interpretation for the coefficients, is the one coming from surface confined viscous flow. So in a way, we could think this as a poor man's derivation of surface confined viscous flow that instead of using the full Navier-Stokes equations, uses these sort of kinetic-like arguments. Okay, now we put everything together, and okay, I will save you the details, the technical details, but again, let me mention that these equations, introducing these functions that we just discussed, admit a planar solution, just a front that erodes with a constant height. And if we do an expansion of everything around that solution, taking into account that the average excavation rate, the average rate of erosion, the etching rate, is small as compared with the addition rate due to surface diffusion. This is seconds and this is picoseconds. Just properly expressed. Well, we have a very small parameter here, epsilon. And then we do, again, a Taylor expansion using this ratio as a small parameter, which again implements a physical fact. That is that matter transport by surface diffusion or collision cascades and so forth, each is at a much faster scale. It corresponds to much smaller time scales, picoseconds, than the macroscopic changes in the height, which take place in the order of seconds or even more. Okay, that's again, once and again, this physical fact. Then let me expand my description a little bit. I mentioned in the context of the Carter-Viznyakov sort of term, the fact that the local angle of incidence is not constant along the surface, but it changes due to the local surface lobes. By the way, this relation is nonlinear in the surface height, and this is a standard source of nonlinear behavior. We are in the context of discussing nonlinear behavior in this type of systems. Well, this is one, and I can tell you this is the source of nonlinearities for my first talk. So if you look at the equations I was discussing, they are seemingly linear. Where are the nonlinearities? Well, in the surface inclinations, which are nonlinear in the surface height. Okay. Well, moreover, the aspect ratio is small, so of the ripples, so we can make a Taylor expansion in the surface lobes. And this leads me to introducing, beyond the terms I was introducing before, let me introduce this nonlinearity to the lowest order. And then this is enough. Implementing the Taylor expansion in analogy, this is, relatively detailed analogy with the case of Navier-Stokes equations, we can end up also here with a closed equation for the surface height. So let's say the field R, the density field, can be solved in a way, approximately, it's a perturbative expansion. But then we can input that solution into the equations for H and end up with equations that only involve the height field. We do that to the smallest nonlinear approximation, and this is the equation that we have. So this equation may be familiar to many of you. If we include all terms, okay, the terms in black are just, they look like the linear Bradley equation, Bradley-Harper. Then if we include the blue nonlinearity, this equation is the so-called Kuramoto-Sebezinski equation. And then by the present derivation, we have a term that competes with this lambda1 term, which looks similar but only has a second derivative upfront. It is also nonlinear. And then in many contexts, this is called as the extended Kuramoto-Sieraszynski equation. Let me say that there are many different ways to extend the Kuramoto-Sieraszynski equation, which is one of the most important equations, let's say, probably in nonlinear science. And I mean, in the context of pattern formation, for a certain class of processes. And well, this is one extension. Let me say also that if we try to derive, and this has been done, this equation from the, let's say, simple Bradley-Harper approach to sufficiently high nonlinear order of approximation, we run into trouble because we get an equation with the same form of the coefficients, but this minus sign in that derivation happens to be a plus. And I will not enter that discussion, but at least to many problems from the mathematical point of view. So we need a physical model which is the correct one, so that the equation, once derived, carries the correct sign for the coefficient. Beyond that, moreover, we can discuss what were the physical mechanisms involved in such a correct sign. And then we believe they will be relevant to the system at hand. Okay. Well, let me just review some results of numerical iterations of this equation. This equation, again, is nonlinear. Unfortunately, there are not analytical solutions available, so we may integrate it numerically and then compare to experiments. And for instance, these are morphologies. This is the surface as seen from above. For long times in the model where the inset is the surface autocorrelation function that sort of suggests short-range hexagonal ordering. We compare that with experiments of silicon irradiation by argon ions, in which actually the agreement is quite nice. Actually, also it extends to the surface as a function of time for different irradiation conditions, the different colors, or also the ripple wavelength, which grows with time, some coarsening, as shown below. And in these graphs, the lines correspond to simulations of the model, and the symbols correspond to experimental data. Actually, this agreement, we did this work back in 2010, and with our current knowledge, this agreement is relatively surprising. Why is that? Because actually these irradiations of silicon are done at normal incidence, while we just discussed in the previous talk that under such conditions, on clean silicon targets, there is no pattern formation. And indeed, that's the case. We learned later that actually the samples, the experimental samples in this experiment had metallic impurities that actually bring them into different contexts in principle. But again, let me say that that context also takes, from the modeling point of view, this exact same form, only with a different interpretation for R, which is the difference in composition between some parts of the system and others. And then what I can say is that as I advanced earlier, many times these evolution equations, which are meant to describe long time and large distances, they have universal properties, universality, that may explain, how come it explains so nicely these experiments where it was not meant to be found. Okay. Well, the equation can be generalized to off-normal incidence. And okay, for instance, this lambda2 now generalized where, well, if the incidence is oblique, that breaks the x and y symmetry in plane, and everything becomes anisotropic. Of course, this equation is very complicated qualitatively. Okay, that's the behavior. There's ripple formation, relatively disorganized ripples whose wavelength corsons with time, and this is down here the evolution of the surface roughness. But actually, these ripples compare rather nicely with experiments done by Flam and collaborators on silica substrates. So we may be now just describing accurately some experiments of clean targets which become amorphous. Now, okay, when dealing with additional nonlinearities, this can be seen, or if you wish, less mathematically, more physically, with additional nonlinear effects. This is an opportunity to go beyond these simple interfaces which are univalued, single-valued, and consider morphologies like this. These are so-called cauliflower morphologies, no wonder, but the term is many times employed in the literature, for instance, in chemical vapor deposition or other, like physical vapor deposition techniques. And okay, actually, the behavior of the system is highly complex. And in particular, it is one instance of so-called, let me replay the movie, of so-called secondary, secondary instabilities. Let me try to stop it. Yeah. Okay, this is early times. This is the realm of linear stability approximation, linear regime. We had an originally flat interface. I can tell you the model we are simulating here is a continuous model of still a different nature, so-called phase field or diffuse interface model. Well, anyway, we just run the simulation thinking we're doing an experiment, and at early times we have some ondulation that sets in with a typical wavelength, and that's in our erosion context, the ripple instability. This is growth by different technique, like chemical vapor deposition. Now notice this starts to go beyond linear approximation. Why? Because now the slopes on the surface are growing high. And I would say here, very high. But now what will happen is after this, there is what I call nonlinear instabilities. The ripple instability is called a linear instability. These are nonlinear instabilities. Why? Because with respect to shapes which are nonlinear, this is no longer a sinusoid. The sides of these high features become unstable to so-called structure formation. And these are called, you see, this is called side branching and tip splitting. Oh, sorry about, oh my God. Sorry about that. This, I also run into this trouble when I give my lectures online. Okay, and these are the long times that recall the cauliflower structure. But the point is that we have this side branching and further instabilities, which then are opportunities for further applications. Why? Because there are more features to the pattern shape than the basic linear instability. So for instance, this is a later study showing like a hierarchical self-assembly. So we can consider a pattern which has relevant information at different scales. In this case, this is done in a top-down approach by some sort of sophisticated DNA assembly. A simpler approach is like focus ion beam induce the wetting, in which we have layers of coatings which we shine with an ion beam. This coating the wets, and if it does in a proper way, we have a more complex pattern in which we have these rings of dots and rings of featureless surfaces. Again, this is sort of a top-down approach. Okay, it's like a mixture. Okay, and we did some time ago takes a similar approach in a way, but in the context of fully, only considering IBS patterns. And then the basic idea here is we consider a surface which is initially bombarded. This is a gold surface bombarded with argon ions at oblique incidence, theta. Okay, this is done in the so-called erosive regime for metals, in which ripples are formed by the ion beam and controlled by the ion beam. In this case, these are so-called transverse ripples, whose periodicity is orthogonal to the projection of the ion beam here. And then we stop this process. We have a ripple structure, and now we do a further second step of IBS, in which we take this surface as the initial target to bombard at zero incidence, normal incidence. And then the outcome are these, and these are the experimental images, so-called nanobits. This is the top view when we bombard a flat substrate. What do we have? Okay, disordered dot hole pattern. But if we do it on top of the initial ripples, and this is one experiment, this is the initial target. Now we bombard this target at normal incidence. Fluence increases to the right. And then what happens is that these dots and holes, they nucleate, but they do so preferentially along the ripple troughs and edges, so that for long enough fluence, a zoom of this is this, which is, as Professor Kim likes to call them, these are nanobeads. Okay, these are like nanodots, see the scales here, which are arranged preferentially along a straight line, and that line can stand quite long. That may be useful for some suitable applications, let's say. And then what one can do is consider, again, okay, it's not exactly that these are meant to be employed for biomaterials for the reasons we discussed earlier in the previous talk. But okay, it's a similar idea. Let's try to tune the properties of these structures with respect, in this case, to the wavelength of the initial ripples that were pre-patterned in the first step. Okay, and then as we can see, there's some convergence for different conditions. As you see here, they differ both in roughness. These are all experimental data, and these are the ripple wavelengths. These are the initial ones, different wavelengths and roughnesses. Okay, there's some sort of convergence, in quotes, to a sort of steady state for large enough fluence, okay, in which the system tries to accommodate the dynamics, taking into account the initial condition. Okay, we can try to actually set up a continuum model to describe these processes. And okay, I would say this is because we're dealing with metals, in a way we can think of this coupled system of equations, H and R, as a system for a density of, let me say, of species at atoms and at vacancies, whose thickness is basically one adatom size, basically. Okay, and then we are in the why? Because, as you know, metals are highly effective in recrystallizing, and it's hard to induce a proper amorphized layer. So we think of that layer not that as an amorphized, but as a activated layer for surface transport, where the ion beam is excavating. Part of it is sputtered away, but part of the excavated material remains on top and redistributes through very highly efficient surface diffusion that eventually leads to no proper thickness of an amorphized layer. Okay, then it is known, this comes from the nice, already relatively old review by Chan and Jason on ion beam sputtering. Well, metals are well known to have a so-called erosive regime, where for appropriate values ranges of temperature and flux, one can have Bradley-Harper type behavior controlled by the ion beam. And it is in this context that we can set up a couple-to-field model and end up with, lo and behold, the same equation I was discussing before. Actually, nonlinearities are crucial to describe. One could think of the experimental behavior maybe of a linear type behavior, because in the linear instability mechanism discussed, the classic one, let's say by Bradley and Harper, there is a competition of ripples, let's say with different wavelengths, and eventually one of them wins over. And one could think of this as being relevant here, but no. Okay, we simulate the continuum equation for, the continuum linear equation for different initial conditions, sinusoidal or the proper experimental ones, which are actually not sinusoidal. Well, the roughness just increases exponentially with time. So there's nothing like that. Okay, there may be some intermediate behavior, but eventually the roughness does not saturate, as we see in the experimental samples, to a sort of a steady state value, in quote, irrespective of initial conditions. Let me show you some simulations of the full extended KS equation, nonlinear, with the two nonlinearities, conserved and non-conserved, for different experimental conditions. And let me stress the fact that we found it relevant to use, and this can be done for simple models like this, or relatively simple models like this. One can use the actual experimental initial condition as the initial condition to integrate the height equation. What are the initial conditions experimentally? We just take two AFM snapshots, just these two, for the conditions called A and C in the experimental diagram that I showed you before. And then on top of this, we run the simulations. And okay, we can see that actually the ripple wavelength in condition 1 is very narrow. We are bombarding at normal incidence, and the dots, in quotes, would like to be wider, and then the surface becomes less organized. And in condition C, it becomes more organized along a given direction. This is an experiment comparison, sorry, between experimental above and simulated morphologies. And okay, we can see that there's some alignment of the, let's say, the nanobits. But if we look at the specific one, okay, of course, there's a lot of room for improvement in the quantitative behavior. But if we look, for instance, for this nanobit here, it has a sort of not very well defined, but some hexagonal disorder, or like this cell is surrounded not by 4, while if we compare the nanobits arrange themselves more around with a square-like arrangement. Well, something to improve, some effort to improve this aspect of the comparison can be done. Let me first compare the previous simulations with the experiments. Experiments are on the left and the simulations are on the right. And parameters can be found that, okay, can account reasonably well for the experimental values and the change with experimental initial conditions, both for the roughness and for the wavelength of the ripples that sort of remain on the surface. Let me skip further comparison and let me just show you briefly some further improvements we took, attempts we made, I would say, to try and improve the comparison of some aspects with experiments. One very important one, a natural one, is to take into account the fact that, okay, even in the Rutherford regime, still surface diffusion in metals is known to be highly anisotropic. And our treatment of surface diffusion so far was fully isotropic. So there are ways to compensate for that. On the one hand, for instance, this term, which is correct, this is a minus times this minus here gives a plus. And okay, this is basically the diffusion term for R in the equation for R. Well, in general, that surface diffusion, there's an easy direction and a hard direction for surface diffusion on this crystalline surface. So the diffusion coefficient D is not a constant, as we used before, but rather a tensor, a full-fledged tensor, let's say with constants suitably related, let's say with temperature and activation barriers on the microscopic system. And let me also take into account anisotropies in surface tension, which appear here in this sort of Gibbs-Thomson effect that mediates the rate of addition, which we displayed before. Okay. Then the separation of length scales occurs just like before. The equation is even uglier than the anisotropic one I was showing you before. And let me simplify it by considering normal incidence, because in this case, the system with respect to ion beam erosion is isotropic, and only anisotropies to surface diffusion remain. And they survive in this way. We have an unstable Laplacian due to the sputtering, for instance. We have the standard KS nonlinearity, and then we have these linear and these conserved nonlinear terms, which have been generalized to anisotropic, because K and lambda 2 are tensors, simple ones, but tensors nonetheless. And in this way, we can, if we consider different conditions, different weights of the various nonlinearities and the anisotropies in the nonlinearities involved, let's say in this anisotropic surface diffusion, well, we can find values of those which actually we can tune between sort of a ripple-like to square to then dot-like symmetry. This is hexagonal. This is more rectangular, almost square, and this is basically ripples, very anisotropic. And that can be quantified by additional sort of order parameter functions. But okay, this would be our attempt to at least account for the the more square type ordering of the nanobits on the experimental surfaces, which from this point of view would be due to the nonlinear effects. Remember, we are interested in the context of these talks in genuine nonlinear effects, well, these are induced by the anisotropy in surface diffusion for metallic targets. Okay, let me, okay, I know maybe this is a lot of information. I'll try to show even less equations, but let me finally consider one last example in which this extended KS equation happens again to occur, to be relevant, or at least provide some insight into genuine nonlinear behavior, okay, that goes beyond previous equations. This is recent work done in collaboration with a group of Professor Jason Kim in Seoul, and it deals with the fact that most of the, let me go back to the fast to ripple structures we have seen before, like these experimental ripples, A1 and A2. Okay, this is a pattern, it's a typical wavelength, but they are very disordered. Okay? And then depending on the application one has in mind, it may be desirable to try and avoid such a strong height disorder. Okay, this has motivated the number of, oh, sorry again, various proposals. So for instance, there's one by Adrian Keller and Stefan Fasco, in which what they do is a two-step IBS process, sequential IBS, in which they take the ripple pattern they have produced by, let's say, of normal incidence and rotate it subject to very glancing incidents and eliminate defects. That's one possibility. But another, which is sort of intriguing, maybe it's like, I mean, it requires a single step, is rocking the substrate. What I mean is we have the substrate and we make the incidence angle oscillate between two values, alpha and beta. Okay, this is the situation, and this is actually a theoretical proposal by Harrison and Bradley. And sorry, the year of the paper is not 2006, is 16, okay? It's like 4 years old. And this is a standard morphology produced by, let's say, the anisotropic KS equation. Now the idea is, let's make the coefficients in this equation. We just take this, the AKS equation. Now let's make the coefficients in the equation oscillate in time. Why? Why do they oscillate? Well, it is known when one derives the equation, this new x, new y, new x, new y, lambda x and lambda y are functions of the angle of incidence. If we rock the substrate, the angle of incidence changes with time. We can do it, let's say, continuously. It's alternating, it's a sinusoidal signal between alpha and beta. Okay, then the coefficients become time periodic, and then again, lo and behold, this is a simulation of this nonlinear equation that produces these disordered patterns for a fixed substrate. Well, if we rock the substrate, we eliminate the defects, as you see, and for longer times and longer. Okay, all defects have been eliminated. Okay, well, of course, as they say, there's no free lunch. A crucial, and let me focus on this one, a crucial aspect here is that, well, normally in the derivation of, let's say, lambda x1 from the standard derivation of the AKS equation, it depends on the angle and it becomes zero at some angle. Well, the observation by Harrison and Bradley is one needs to rotate the target around that angle. Why? Because when we rock around that angle, there's some instant when the lambdas become zero. At that time, the surface becomes unstable, and that sort of amplifies the disturbances. And then again, the lambda becomes non-zero again, and that stops the increase in height. Well, that happens in such a way as to eliminate all defects. Then the idea by Professor Kim was, okay, let's try to consider the behavior of experimental systems under such rocking protocol. This is a case in which, notice, well, let me focus like this. This is 62 and 70 relatively disordered interfaces. Notice the power spectral densities, not very well-defined peaks, but let's focus on condition F of rocking. C to H differ by the frequency of the rocking, slower or faster, okay? And then, okay, in this case, behavior is pretty much, so let's say the optimal condition is either E or F, as can be seen by measures of disorder or of order, close to the range in which the proposal by Harrison and Bradley predicts them to be. But this is not the case for 2 keV krypton, because theta L is 75 as estimated, as Harrison and Bradley suggest. But this rocking around that leads to not so good surfaces, and I show you rather rocket surfaces around 62 and 70. These are, okay, relatively close by angles, and the optimal is F, which is, you see, far from the frequency where in the pink area the simple argument by Harrison and Bradley predict it to be. Well, the point is that how come we can explain defect elimination in a region where the AKS equation does not predict it to be, okay? Notice these are simulations of both the AKS on the right column and extended AKS on the left column for different rocking protocols for lambda. Here lambda changes between 6 and 2, so it does not change sign. It does not become 0 anywhere. In that case, the AKS equation of Harrison-Bradley does not eliminate defects, but the extended AKS equation does. And similar for many rocking conditions. Additional rocking conditions and even experiments like on amorphous carbon are provided in the paper together with the Professor Kim's group. But the main outcome is that we may be witnessing something analogous of these secondary instabilities, in the sense that defect elimination, which is for these experimental conditions, krypton 2 keV on silicon, cannot be well described by the standard AKS equation. Well, that requires further nonlinearities. Moreover, these nonlinearities carry this Laplacian in front, which accounts probably, or possibly, I would say, for flow-related behavior, which, remember, is conservative, is the derivative of something else. Well, I would rather like to stop here. Of course, continuum models still hold promise to describe basic IBS properties and more elaborate ones through suitable enhancement, and which is the type of modeling when putting together the two talks are relevant in a specific case. Well, okay, it depends, of course, on the available information and the type of predictive power one would like to achieve, whether qualitative, let's say in terms of universal properties, or more quantitative entering more as material specifics. And of course, a very challenging line of development is to insist in this combined development of continuum with other modeling approaches like molecular dynamics and MD, as has been mentioned in the character function approach, our hydrodynamic approach, or even in these more kinetic type models. Well, let me, with this, at least appreciate again my work in the references I was mentioning with various people, in particular here the team in Korea led by Professor Jae-Sang Kim, and recall the various aspects covered in these general references. Let me insist, I would love to hear of any questions, comments, or suggestions you may have either now or through email, or hopefully not far from today when we can see each other in person. And with this, I really thank you for your attention.
Okay, sir. Thank you very much for such a nice, elaborative explanation of the theories being evolved over time on surface patterning. So, any questions, students, from participants?
It can be through the chat or...
Yeah, please, if you have any questions or queries, please email through email to Rodolfo sir, or anytime if you want to interact with him. I think...
Let me show you my email again in case. Oh.
Is this the real picture? Or a poster?
Okay.
It's really beautiful.
Like a poster is the background of my desktop. Sorry, I sort of lost my presentation. Let me, 1 second. Now, and then let me leave you with this.
Okay, so you can note down his email address. So if you have any query or you want to discuss some of the things on simulation, please email to him. So thank you very much, Rodolfo sir, for accepting our invitation to deliver such lecture at a shorter time in this school. We are really thankful to you. So, yes, sir.
No, but again, I found it like a great opportunity, and I'm myself.
So it is always a pleasure, in fact, to hear you. So let us thank Rodolfo sir. And now we will be breaking. So tomorrow, let us meet at 9:20. Participants, try to log in before 9:20 because the session has to start at 9:30. So every time we are just getting, the sessions are getting delayed because of late logins. Okay. So goodbye to you all.
Goodbye.
Bye, sir. Bye, sir.
Bye-bye. Keep safe.
You too. Bye.